get through some of the preliminaries here. First thing is just want to make sure, did everybody get connected up as far as Wi-Fi? It's the same SSID as yesterday, Spark Summit, and the password is East 2015. There was a little bit of trouble I saw associating to Wi-Fi. There had been a little bit of trouble, but I think it's resolved. So just want to make sure that everybody's connected. And then number two, the other tutorials are upstairs, so registration's upstairs. For the tutorial here, everyone needs to have a slip of paper, a password slip of paper that the registration people handed out. Does anybody not have that? If you don't have a password, just need to drop by the registration desk, and they'll give you one of those. And then thirdly, the slides that we'll be using today, you can download those. I recommend downloading them, having them in your browser, because I'll be switching back and forth between some different screens, so it makes it easier to be able to follow. But it's at training.databricks.com/workshop, sparkcamp.pdf. And that'll just be the slides for today. It's got a lot of links. We try to err on the side of having too many links, so there's plenty of different material to drill down on if you have an interest in any particular area to dive deep on it. The other thing is, I'll introduce some of the other engineers here. Any troubles downloading? Is that working okay? Good, good. Any troubles logging in, actually? Is everybody able to get the logins to, pardon? Okay, actually, Chris, can you help out? Vita, Chris, can you help out right here? Anybody else having troubles on login? Alrighty. Well, I'll introduce the other engineers here. Everybody's got, the Databricks folks here have admin on these shards, so if we need to override any of the passwords, we can. Meanwhile, let me start out. I'd like to introduce two of the engineers from Databricks who will be assisting here, mentoring on some of the coding sessions and all, and helping out in general. First up, Vita Ha and Chris Fregley in back. And Vita and Chris are two of the engineers at Databricks working on Spark. And in particular, if you're calling in for customer solutions, they'll be helping you through a lot of the interesting integration types of work, getting you onboarded, troubleshooting, resolving any problems you have. So you'll probably be talking with them a lot if you're using Databricks Cloud as a customer. Let's see. Great. We got enough chairs. We got a few extra chairs. Good. Okay. Let me go through a little bit of an outline here while we're getting set up. The main thing is we're going to be running off of Databricks Cloud. So as was discussed in much more detail yesterday, there is a PaaS offering based on AWS, running Spark, running cloud-based notebooks for Spark in the cloud in AWS. So all the materials will be on Databricks Cloud. We'll go through onboarding there, getting used to navigating through, looking at some of the reference materials for Databricks Cloud. Actually, Vita is one of the main authors, Chris as well, on some of the reference materials that are online. And then we've got a series of different coding exercises as far as introduction to Spark. We'll go through a progression of 4 of these different exercises. And along with that, I'll have a few lectures sprinkled in there in terms of looking at how Spark runs on a cluster in detail. And then also looking at the history of this. Where did Spark come from, and how does it fit into the context of open source big data frameworks? We'll also cover a bit more about notebooks, taking a look at really conceptually how do we leverage these, at least how we're seeing people leverage these. It's still definitely a work in progress there, but I've been doing a lot of work with notebooks over the past year, actually prior to coming to Databricks, and I'm really excited about what that means for teams. We'll also go through a tour of the Spark API in general, taking a look at both the Scala and Python side. I should mention that the coding exercises here are primarily in Python. We do also show some examples in Scala, I think a little bit in Java as well, but mostly it's Python. We'll try to, after lunch, we'll try to organize a little bit of a tradition where we have an extended Q&A session called Ask Us Anything. I'm going to try to get some of the other committers who are in the Advanced Data Science course upstairs, get some of the committers, the tech leads from Spark to come down and just have an open forum for any questions you may have. I know that we've got Michael Armbrust, who's lead on Spark SQL, TD, Tathagata Das, who's lead on Spark Streaming, Shangri Meng, and Reza Zadeh, and others who are leads on MLlib. So we've definitely got a lot of great expertise right here, and we'll try to get some of them in. Later on in the afternoon, we're going to look more at workflows, look more at the different layers that are built on top of Spark in terms of Spark SQL, MLlib, Spark Streaming, graphics, and how to really tie these all together. And we'll also have some exercises that consider machine learning, visualization, what you can do with the notebooks again, leveraging these. And then we'll wrap up later in the day with a look at some of the production case studies in terms of what are people doing with these kinds of tools, what are some of the production use cases that have been reported. We also have other information, community resources. We'll step through some of those. So actually, to start out here, now, the lights are pretty bright, so I'll probably be doing this exercise quite a lot today. But are there any questions just getting started out? Yes?
Just some problems logging in.
Problem logging in, OK. Chris or Vita can help out then. Yes?
After that, what we do is we get some slides.
Oh, pardon?
After you log in,
Yes?
there are some slides that you watch.
Oh, no, the slides are up here, this PDF. So the URL right there, training.databricks.com. If you grab that PDF and have it in a browser window, that's recommended. Good stuff. And please interrupt at any point with questions. I love questions, and I like the dialogue especially. Although it'll be a little hard for me to see who's asking. There, yes.
The cluster will be available after the class.
That's a great point. Yes. We'll talk a bit about how this is organized, but the logins and the resources that you have, this will be available after class. They'll be online for some period, at least a week. But during that time also, there'll be a follow-up message if you want to convert your counts over and move into Databricks Cloud in general. These are slightly special training shards, but it has pretty much all the features you'd see. It's just there's different pricing and packaging for Databricks Cloud, the commercial version. Ready? Other questions? OK, good stuff. I have a question that I always ask. My boss always asks me. But I'm really curious, how many folks come from more of a analytics or data science, business intelligence kind of background? OK, cool. I will say about 20%, maybe 15 to 20%. How about more from application developer background? OK, so we'll give that at least 30 to 40. How about coming more from systems engineering, sysadmin, SRE kind of background, DevOps? maybe 10-ish%. Making some mental notes about this. Let's see, how about people who are more from product management or stakeholder kind of background? Okay, give it about 5%. Okay, great, thank you very much. It's really helpful to get to know more about the audience. Spark does address a lot of these different areas, so we want to try to understand how that breakdown works out. Now, so step one, everybody has password slips, hopefully. If not, we can take care of that. But step one will be, through the browser, log in to the different shards that you've been given. So there'll be a URL listed on the password slip, and then there's also a username and password. You'll be prompted for that when you first get in. This will take you to Databricks Cloud, and we'll have a series of different notebooks that we'll be using for the course. There's actually more examples than we'll be able to cover today, but there's more if you want to explore around as well. We find that the cloud-based notebooks are a really great way to get started using Spark. It really cuts down a lot of the overhead as far as management of clusters, and just gives a lot more power for being able to handle some pretty large jobs. I work more in machine learning. My background is I did machine learning work in grad school quite a long time ago, over 30 years ago. And it's been fun to see the field progress. I also did work in distributed systems, so I have kind of a combined background. And for about 10 years, I led data teams working on large-scale recommendation systems, social networks, anti-fraud, et cetera. And trying to work with cluster computing resources, it's challenging because there's a lot of moving parts. And I do find that the collaborative nature of using notebooks is a really big win for teams trying to pick up this kind of technology, because it just cuts down a lot of the overhead. So we'll hopefully show some examples of that throughout the day, but definitely in machine learning work, we see this to be a really great boost. So to start out, when you first get logged in, let me cut over here. Okay. I'm right here. I'm in Databricks Cloud, and up in the top left-hand corner, there's a navigation menu. Should always be present, but if you click that back and forth, it'll open up the workspace. And then underneath that menu, you've got the workspace list of folders and subfolders, which is where you get to the notebooks. As well, down here, there's a list of accounts, so everybody's account should be on there. By the way, is the typeface big enough? Can you see that okay in the back on the screen? A little bigger? Okay. How about that? Is that better? Okay, great, thank you. The other thing here is clusters. If you go to the nav menu, I'm going to look at clusters. And you'll see here there's a list of all the different clusters that we've provisioned for this particular shard. So right now I'm on a shard that's called class 70. And there are 7 of these different shards that we're using in this class. But in that context, there's a number of clusters that have been allocated. I've got one that I'm using for the instructor right here, eponymiously named Paco, and it's, 11 gigs for that? So it's got 2 nodes, a master and a worker node. There are a number of other clusters as well, student 1 through student 50. And so whatever you've got on your password slips as far as the username for login, there should be a cluster with the same name. If for whatever reason a cluster goes away, it's not really a big deal. It's very simple for us to allocate another one. And frankly, these are large enough that more than one person can be on the same cluster. We just, as a convenience, try to have a different cluster for every person. So workspaces, accounts, and clusters. Those are the main things we'll be looking at first off. And in terms of workspaces, I want to show some resources there that are on Databricks Cloud in general. So if you go to the nav menu right here, and then go to Workspace, under Workspace, there'll be a list of different folders. And we'll have everyone create their own folders here in a bit. But the first thing I want to point out is Databricks Guide. So if you go here to this folder, Databricks Guide has about a dozen different sections. You can see here, if you click on any one of these, it'll bring up the notebook. This is a general purpose reference manual for Databricks Cloud, as well as a lot of great material about getting started with Spark. And at any point in time, if you click up on the upper right side of the menu here, it's also got a link to Databricks Guide. It'll bring you right back to this point. We should also have a search capability. I'm trying to see if that... So if I want to look for SQL, great. So the other thing would be up in the top left, close to the nav menu, there's also a search icon. If you click on that, you can search for any particular topic, MLlib, Iris. Great. So that's also helpful too. This will search all the different notebooks that are available within the workspace that you have. So that includes searching through Databricks Cloud. It's a handy way to be able to drill down and look for particular material. Righty. So the first up, I'd like to look at 01 Quick Start, part of the reference manual here. Okay. So if you go to Workspace, Databricks Guide, and then down here, 01 Quick Start, this will show an overview of some of the main UI features being able to navigate through. And talks about notebooks. One of the things that is changing is, for right now, this is a fairly open workspace. We're all sharing the same workspace here. In the very near future, we will have some additional security controls on here, ACLs, such that people can lock access for particular notebooks or particular file resources. But for right now, it's one big shared space. So in this interim period, while it's all one big space, it'll be interesting because I'll be working with notebooks that are unlocked, and 100 people can all come in at once and be running them. So I would ask that while I'm actually running the examples, please don't execute them so that I can have something consistent to be able to show. But pretty soon we'll be able to have this all partitioned off. Question?
I have something that says connecting at the top. I don't know that.
That's a good point. The projector is kind of jumbling things up, actually, the projector resolution. But up at the top, there should be, as you're seeing on your browsers, there should be a status bar up here that will talk about, for any given notebook, it'll talk about what cluster it's attached to, or if it's in a detached state. It'll also describe whether or not the notebook is locked or not, and whether or not it's connected. If you get that message that says connecting, it just means that it's trying to talk back to the server resources. The client side, the browser side, is trying to talk back to those server resources. It shouldn't be a problem. One thing you might want to do, though, is just refresh the browser. If you hit refresh, it'll probably help out. Did I see another? Yes.
Can you define what is a notebook?
Yes, very definitely. Let me see here what... Actually, that's an excellent question. Right to the next slide. So in terms of notebooks, how many folks here have worked with IPython notebook? OK, great, great. How about other notebooks? I'm just curious. Zeppelin? Anybody worked with Zeppelin or Spark Notebook? How about R Markdown? Some? OK. Well, there's been a growing movement, if you will, but definitely IPython Notebook has done a lot of work on this. And the follow-up now is being called Jupyter. The notion of a notebook is a shared document that's browser-based. And so I find that there's a good analogy with, say, Google's spreadsheets, something like that, where you could have a document that's in the browser. It has some server-side resources, some cluster computing behind it, but a number of people can all be in that document at the same time and working on the different cells in the spreadsheet. So with these notebooks, we have the notion of cells, and it's basically, they're linear, starting from the top down. And so you execute in order. And the cells could be either source code. In this case, with Databricks Cloud, the source code can be either Python, Scala, SQL, and now R is also coming online as well. In addition to having source code, when you execute the cell, there's output. So you can have an output cell, or show the output in a cell. And that may be just some sort of text, like you would have off of a console, or alternatively, it could be some type of a graphic, perhaps even an interactive graphic. So that makes it very nice to be able to build interactive analysis, dashboards, things like this. In addition, you can also have Markdown. So if you're familiar with, say, GitHub-flavored Markdown, like you would use on a README in a GitHub code repo, Markdown is a way of having essentially hypertext content. So it can be HTML, it can have JavaScript embedded. I believe most of the notebooks will support LaTeX. You could also have videos embedded. I've been working on a project at O'Reilly Media over the past year and a half, where the O'Reilly authors and editors at O'Reilly use a content platform internally. It's called Atlas. And we edit the books as different chapters of Markdown. And one of the things that O'Reilly did was to be able to take a chapter. Our books typically have a lot of code in them. So we can take a chapter and export it as IPython notebook. And one of the things that we did at OSCON and Strata over the last couple of conferences was to have tutorials that are based off of these notebooks in the cloud. Literally taking the books, exporting them as notebooks, as shared documents that people can execute in a tutorial setting like this. So Databricks is, over the past year, actually going on 2 years now, Databricks has been working with the same metaphor to come up with shared notebooks that have cluster computing resources behind them. You can spin up a Spark cluster, the given size. You can spin them up and spin them down within seconds. But the notebook itself is what maintains the state, the collaboration that the team is working on. We'll talk about that in more detail, but it is a very rich environment and also very good for a team.
Just a follow-up question on that.
Yeah.
Like you gave the analogy of Google Docs, right?
Yes. Yes.
So if the cluster goes down, is my notebook also gone?
No, that's great. That's great. So let me actually see. Let me cut to that in just a moment here. I've got some other slides that talk about the notion of the shared state and sort of a separation of concerns about state. One thing I will say, though, on this slide, before I move on, though, one thing that's really important is that we want to make sure that there's no lock-in to this kind of environment. So any notebook that you have, you can export. You can both import and export. If you export an entire folder, it'll be a zip file. You'll see it have a .dbc signature, and I'll show some examples of that, but it's a zip file. We do a special signature because then we can do the signing and get through some of the security standards. But it's essentially a jar or zip. If you export an individual notebook, though, it will create a source module in that language. So if you have a Python notebook, it'll give you a Python source module. A Scala notebook will give you a Scala source module. And any of the Markdown will just come out as comments. So we want to make sure that whatever you're doing inside of this Databricks cloud context here, you could take and export this and run this in Spark in general. Alrighty. Let's see. Let me go to context here in a bit, but I want to get you started using these notebooks. If you go to the workspace menu on the top left, glasses. go to the workspace menu. Up in the top left here, and click on workspace. There'll be a menu, a drop-down menu, little triangle off to the right side here. And if you click on that, the drop-down menu shows how to create a new notebook, dashboard, library, folder, etc. Start out by doing a new folder. And so what I'll ask is, it'll prompt you for a name. And so I'll ask that everyone create their own folder with some unique name. And then as we're going through different notebooks, and you can clone the notebooks that I've created and put them in your own folder. So great. OK, I'm seeing a lot of folders getting created here. Perfect. And now, once you've got a folder, let's, before we get into some of the other lectures, we want to do, I call it a pre-flight check. We want to make sure that everything's working correctly, logins, etc. So navigate over here to Workspace, and then up at the top, Spark Camp. And inside there, there's a notebook called Pre-Flight Check. It should be locked right now. Great, that's showing up. So the first thing then is to come up here to pre-flight check, and if you hover the mouse over it, there'll be a drop-down menu on the right-hand side. Click that and say clone. And that will prompt you for where to put a cloned copy of this notebook. And just go in and change the path to whatever your folder is. Put my folder. And whatever name you want to have there, and hit clone. That'll give you your own version of this notebook. Cancel out of that. Okay, so that will create a clone, and the next thing up is once you've got that clone version. It's going to be a little bit hard to read. Let me drop down the resolution. I'm going to unlock this. I had it set locked before. Once you clone it, let's see if I can boost this. Great. It'll come up in a detached state. So up in the top status bar here, you'll see where it says detached. If you click on that, then it will pop up a list of different clusters and attach to your cluster from there. Pardon? Yes, yes. If you go back to the notebook that you've cloned, the copy that you've made, then take it and attach it to your cluster. And let's make sure that's working OK. Because we're going to do this over and over, creating notebooks and then attaching them to your clusters. Question? Yes?
My question is, how come I can see the cluster of everyone?
Sorry?
Like, is it designed that way that I can see the cluster of everyone?
Yes, it is. That's just a temporary thing. It's not the best, very definitely. One of the problems here is that we've got 100+ people and 7 different shards. So we've allocated all these clusters for different people. So one of the main challenges I see right now is being able to actually scroll through that list of clusters. If that's posing a problem, we will create some other clusters on the fly. So that's a good point. That's another workaround for right now because of the lack of being able to scroll through there. If you zoom out like that, then when you go to attach and detach, you'll at least be able to get a longer list. But if that is causing any problems, what I will do is just go in and create a lot more clusters. I'll create larger clusters and put them up towards the top. Does that answer your question, though, about that?
Well,
It doesn't show all the clusters.
it's designed that way.
Yeah, no, that's definitely that's a big hindrance on the UI right now, in my opinion. And the UX people are working on that to change that around. The idea is people have those.
UI perspective, but from security perspective.
Oh, certainly. This is just a temporary thing right now. We are putting in ACLs, and once the ACLs are in place, you would only see those clusters. Yes. Yes. Hi, Chris or Vita. Can you help up here? Right. He's going to push her. Great. Yeah. So with ACLs, then this would all be locked down, and then you'd only see the resources you're working on. So if
You currently have ACLs available, or it's just not configured for this setup?
it's not configured for this setup, they are going in. I've seen this work, but it's not available for the training shards yet. But that's especially in terms of finance and government, healthcare, et cetera, that's a huge priority to make sure all that security is set. Yes, question? Okay, Chris, up here. Or Vita. Okay, other questions? Alrighty. Let's see here. The next step. Well, I want to show some coding first, and then I'll get into a little bit more of the theory of how this works. So as far as the pre-flight check, the main objective here is to show really 3 lines of code. Boost this up a little bit. 3 lines of code that will be used over and over as a design pattern for almost all of the Spark apps that we look at today. So what we've got here is a notebook, and the first cell in the notebook, if you click on yours, you'll see that there's a cell that starts out with %MD. That means it's a markdown cell. And so whatever follows from there would be marked down, again, similar to what you'd see on GitHub and other places. And we have the notion of executing a cell. So if you click within a cell and press down Shift key and return, it will execute it. For markdown, what that will do is cause the markdown to be evaluated and print out the text for that. Now, down here, somebody created an empty cell. Let me kill that one. If I go to the next cell, it's also marked down, and it's showing an initial program to run. Let me kill this one. So I've got some code that's just commented out. But the first thing that I want to show about Spark is, first off, let's create a data source. In this case, a data source within Python. So there's a list here. It says data equals X range 1 to 10,001. So that would create a list of the integers from 1 to 10,000. And basically just, it's already been done, but you can see down here there's another cell that has this code in Python. And if you click within that cell and hit Shift Return, it'll execute it. And if you take a look at data, print that out. Let's say print. Okay, it prints out the X range. So it's an iterator in Python. Now the next thing is, this has not used Spark yet. All it's done is worked in the native language in Python. So we want to take that data and create an RDD out of it. We'll talk about RDDs in much more detail, but it's the basic data abstraction in Spark. An RDD is a resilient distributed data set. So you can think of it as being a collection that's been distributed across a cluster. And we can apply functions to those RDDs, which is where the notion of closures and functional programming comes in. Question in the back, yeah. Not returning? Might just, depending on the connection, it might just need to be refreshed. But I think Vita's right back there. Does it, if it's not returning, is it coming back and saying cancel, like with a progress bar? Yeah. So well, let's try a refresh on that. But And also, we are working with some fairly small clusters. We're working with 5 gig clusters here. So it could be that if we need to create some other clusters, we'll do that on the fly too and give you larger resources.
I think there's a general internet problem.
Pardon?
There's a general internet speed problem. It's not just this, but if you go to any other site, I had to disconnect and then connect back.
Really? Okay. So that's a good point. There's an Ethernet up here, so I'm connected over Ethernet. I'm not seeing what the wireless is like. Okay. Let's see if we can contact the hotel staff, find out about the Wi-Fi if that is slowing down right now, because we absolutely need that fixed. But while we're doing that, let me show a demo here at least of what I want to work through with this first notebook, because this is really foundational for Spark. So the main thing is we create a collection in the language, not in Spark. So in this case, we've got the integers 1 to 10,000. And then next up, we take that data and we're using a built-in handle called SC. It stands for Spark Context. It's built into the notebooks. If you're using Spark in terms of Spark Shell, it's also built in there. Typically, when you write a standalone Spark app, the first thing it'll do is to create a Spark Context object. And that keeps track of dependency injection, really. It's got configuration. It knows what cluster resources you're using. And all the API hangs off of Spark Context. When we start working with Spark SQL and Spark Streaming, these other abstractions on top, they will take and subclass the context and have their own richer kind of context. So what I do here is to say sc.parallelize Spark Context, and I'll call the parallelize function, and use that to take my base data, the Python collection, and create an RDD out of it. So the new RDD is going to be called distData, distributed data. Now, an interesting thing is nothing happens. All it does is give you essentially a pointer to this RDD, and it begins to build out what we call a lineage graph or an operator graph. It builds a graph of what needs to be computed. So as we apply more and more functions, we'll extend out this graph. And when we finally get to a point of needing a piece of data, then that graph will be executed out on the cluster. This is a process called lazy evaluation. We don't execute the commands right away. Rather, we defer that execution so that we can take a look at the larger scope of what needs to be done. That allows for more optimization. It allows for fault tolerance, parallelism, etc. So there's a lot of benefits for lazy evaluation. It's quite similar to what happens under the hood when you're running a SQL query, say on Oracle or SQL Server. Very, very similar principles are being used. So we did the first step to create the base data. Step 2, we parallelized it to create an RDD. And then step 3, we apply some functions. So in this case here, first off, we take distData, the RDD, and we use a filter function. Inside of the filter, there's some business logic here. It's a lambda expression in Python, an anonymous function in Scala, you might call that. But the lambda says for all elements x, only keep the ones that are less than 10. So the logic of that would be we've got 10,000 integers. We're going to discard all of them except for 1 through 9. So we apply a filter. And again, this extends the operator graph. It doesn't execute it right away. But then we've got another function at the end of that there called collect. Collect is different. It's something that we call an action. And whenever we hit an action, that's when the graph gets evaluated. And the computation runs out on the cluster. It's effectively going to return the result set. So we say distData, filter, and then collect. And running that, great, I didn't define the other. Perfect. Let me run this. Okay. And then I come down here and run this. Great. So I said distData, filter, collect. That comes, produces a list as output are the numbers from 1 to 9. Now, the thing here is that there are really 3 parts to this. There's the base data, specifying where to get the data from. There's different transformations that are being applied, in this case, creating a filter. And then there's some type of action that triggers the whole thing. These 3 steps we'll see applied over and over for almost all of the Spark apps. This is the essential design pattern. And again, it gives us parallelism, fault tolerance, as well as means of being able to do a lot more optimization. Alrighty, as you're running these on your notebooks, is this working okay? How about the Wi-Fi? Is that working any better? Okay, good. I saw a question in the back there. Okay, no question. Hi, yes.
So what's the lambda there? Is that a keyword of alpha?
Well, lambda is in Python. It's a way of creating an anonymous function. I could define a function, but in Python, there's a notion of being able to do a function inline. So what's going on here is we're using something that's called closures. And closures, we'll see this in Scala, in Python, Java, other types of languages that allow for some expression of functional programming. Java, not so much, but Java 8 is starting to have these kind of features. So the idea is that inside of what you're calling for the filter function, you have some type of business logic, some type of code. We're just defining on the fly by using a lambda expression. I could create a function that says filter 10. I do a define, and then just apply that function right there. So it's just kind of a convenience. But the whole thing is called a closure. And the closure is very interesting because what it says is whatever code that I reference within that closure, that's what gets put into the graph. So as I'm building up a Spark application, we're starting from the endpoints, the base data. And right here, it was just a very simple list of integers, but you could think of the data being some large data set in HDFS or Cassandra or HBase or something like that. And you might have a lot of these. And you might be doing some type of ETL or joins to bring all your data together. The logic inside the closures is what goes into the graph, and that's what goes out to the cluster to be computed. So, yes, question?
Can you explain the concept of graphs a little bit more? Is there one node which has the graph, or what is it? Can you explain a bit more?
Great. Well, I mean, we'll go through this in a lot more detail, but this is essential right now. So this is typically called a directed acyclic graph. And in terms of computer science theory that's being applied for distributed computing, for a lot of big data frameworks, you see this notion over and over. And the idea is that you start from some sources of data and you apply different operations, joins, selects, filters, things like this, until you get to the results that you want. So in terms of big data, it might be that you were doing, say, MapReduce on Hadoop. There's a very similar notion if you're using Hive or Pig or cascading, scalding, all of these, they use DAGs. And so the graph is essentially the logical layer representation of a query. When the system goes to optimize this, then it has to plan and come up with a physical representation of the query. And we see the same thing in SQL. When you write a SQL select statement, you have the different fields you're selecting, you have that as a projection. You have the from, all the sources of data. You have the where clauses, et cetera, et cetera. All of those are used to create a graph in SQL. And then the SQL optimizer will do some movement of predicates at logical layer. And then physical layer, it's mapping it all down to different B trees that are being accessed, typically in a relational system. In terms of big data frameworks, we're working typically with clusters, as you're saying, with nodes. So in terms of big data frameworks, we know where to get the base data, and then we know how to parallelize the operations. So the graph essentially allows us to capture all the business logic and determine how to parallelize it. In the case of Spark, the graph is being sent out to every node. So every node will get a copy of this serialized code, And then the nodes will be working on their own partitions. And this is a real key feature about Spark, is that we're assuming the data can be parallelized. It's out in HDFS or something. And so every node will have its own partition. And if we lose a node, we can simply take that piece of work, that unit of work, and send it to some other node that will grab the base data from a neighbor and reapply the graph. And so by using this abstraction, we're able to do both the parallelism and the fault tolerance, and as well be able to have a lot more kinds of optimization. Does that answer?
So then, when you do this operation, it doesn't pull the data into the Spark memory?
Right, very good.
When you do collect, it actually pulls it in?
So we'll look at that in much more detail. I've got some illustrations on that. The notion, though, is that out in the cluster, we're assuming the data is out there or can be getting out there. So it's more a matter of taking the code and moving it out to the data as opposed to the other way around. In reality, though, the nodes that we're talking about in our clusters, they have a lot of resources. They have disk, maybe they have SSDs, they have memory, they have multi-core, et cetera. And so a lot of the rhyme and reason of Spark is to use those resources. Some of the operations happen on disk, but also you want to leverage the memory as much as possible. And so there is, if you're familiar with operating systems, there's the notion of working set theory, being able to get just the right amount of memory being used. And you see this in virtual memory systems and VMs and whatnot. We have a similar notion here. So as we are calculating the graph, there are ways to take and persist the intermediate calculations. So take the data that you'll be using multiple times and cache it in memory so that we can access it again at memory speeds as opposed to getting it from disk speeds. The thing is that looking at these big data abstractions, typically there's some type of distributed file system, like HDFS, being used. And accessing data from disk is actually more expensive than just regular local disk. So you want to limit that. It's orders of magnitude faster to get it from memory. So we'll take a look at how that all works, but the graph mechanism is what manages it. Good question. Other questions? Yes?
So when you're joining two data sets, does the data get shipped to combine? Like, possible that?
Right. So we talk about having data partitions, having the data distributed out through the cluster. And if you're just doing some kind of linear transformation, not a problem. You just bring up the partition and run your functions on it. However, once you start to do some type of cross, some type of join or other type of aggregation, then there's going to be a need to do shuffle. So that's where the data is being redistributed across the cluster. And that's actually the thing that we know we have to do, but we want to limit it as much as possible or make it as efficient as possible. So a lot of what we see in Spark, when you look at the applications and want to tune them for performance, typically how do you partition for shuffles is one of the first questions of how to optimize something. How to serialize is the other. Those two questions are usually at the top of the list for performance. So we'll take a look at those. Good stuff. Other questions? OK. Now, I keep losing my glasses. There we go. OK. We'll be working with Python. We'll be showing some Scala. I'll switch back and forth. Realistically, the APIs look very, very much the same between the two. It's just a matter of the code inside the closures will be different. If you don't have a lot of background with Scala, Holden is also one of our engineers, and she's also the author of a couple of books, or co-author of a couple of books about Scala, Spark. And she had put together a crash course on Scala if you want some background on that. Real quick question. How many people have Python programming background? OK, good. So I'll say at least 50, 60%. How about Scala? Probably more like 10, 15%. How about Java? Aha, great. Lots. Another question. How about R? OK, good. Let's give that about a 20 to 30%. Another thing I should mention too, in all of these shards, there are notebooks already pre-populated that have all the code examples from the Learning Spark book. So Holden, Andy, Patrick, and Matei. A lot of folks from Databricks had put together the O'Reilly book, Learning Spark. And it should be up towards the top, right here, Learning Spark book. They've got the different code exercises from it. Just as general background, we're not going to be working with those too much here, but just want to show where that's available. OK, let me jump to a bit of an illustration then of what's going on with the cluster and how does this graph evaluation work. And hopefully this will reinforce some of the questions we had earlier about the operation. Now there's an example. I'm going to show it in slides, but if you want to take, you can look at SparkCamp 01 log example and clone that notebook, clone a copy into your folder if you want to run this. It'll step through the different parts I'll be illustrating. So I want to show a typical kind of log operation here, slicing and dicing some log files. So you'll see this a lot when you're doing ETL, extract, transform, load. So we're going to start out up at the top. We'll say SC text file, and then give it a URL. In this case, it's a path. I've got an S3 bucket that I've mounted that has some log data in it. It's a fairly small log file, just so we can be able to look through the example and the results. But you can imagine that this might be pointing to Cassandra, or might be pointing to HDFS, someplace where you have a lot of logs aggregated. So at the top then, it says sc.textfile. Textfile is a general purpose function that we use to import data. And it uses the Hadoop input format connector by default. So we bring in the log data. And in this case, we'll say that it's some TSV, tab-separated data. And from there, we say .map. So we apply a map function. And inside of the map, we've got another Lambda expression that takes, for every element of the log file, splits it on a tab. And so tab-separated data, this will give us different columns out of the data. Now, this is going to create an RDD. We're going to call this a base RDD. What that says is that this is an endpoint. This is a starting point in the graph. And if for any reason we lose a node in the cluster, we can just go and get that partition from a neighbor and reapply this endpoint to recover that partition of the data. So the base RDD is called lines. Now, if this is a log file that uses like a log4j kind of format, then we'll assume that the first column gives you a log level. So you've got error, warning, notice, et cetera. And in this case here, we just want to look at the errors. So the next step is we're going to take the base RDD lines and apply a filter. And we'll say lambda x0 equals error. So looking at the first column in the data, just peel off the ones that are errors. And that gives us a new RDD called errors. So we've transformed it. We've taken the first RDD, applied a filter to transform the data. Again, nothing happens. It just creates a graph. Yes?
Is there any way to pick at the RDD, just to take a look at what is in the RDD, like
Yes?
a column, columnar kind of way?
Yes. So at any point in time, you can take the RDDs, and there's a function called toDebugString. We'll show this example here. At any point in time, you can take and print out what is the lineage. So effectively print out the graph. And it'll show step by step how to reconstruct up to that point.
What about the RDD itself, like the data itself, like the table?
And then there's metadata for any point where you've got effectively what's the schema. So you know what the type is, if it's known. If it's just unstructured data, you don't really have a lot of knowledge yet. But typically, while we're writing these programs, we start to apply some type of schema. So yes. And the other thing, too, is that at any point in time, you can take the RDDs and you could sample from them. You could say, take 2. Give me the top 2. It's like doing SQL limit. So if you want to explore the data a little bit, you can do that. Question? Ready. Okay. So we go from lines to errors, and then next step, messages. We'll take the errors, and we'll say, OK, we know the first column is error, so we can throw that away. All we care about is the actual message of the error, the text there. So we're going to grab x1. That's the second column. So zero-based tuple. And that creates a new RDD called messages. Now, again, nothing has happened. All that we've done is to construct this lineage graph of what needs to be computed. But that gets us up to the point of an RDD called messages. And this is something that's going to be used more than once. We'll use it in a couple different ways. So that's an interesting decision point as a developer. If you're going to be using an intermediate piece of data more than once, then we want to persist that. And that's where we start to take advantage of the memory, take advantage of this working set notion. So the next line says messages.cache. And that's the default setting for that is to persist in memory, but then recompute results. We'll go into much more detail about caching. But again, because I'm going to be using messages multiple times, I want to put that kind of in-memory checkpoint. Yes?
Cache and collect.
Collect is an action that will actually cause the graph to be evaluated and drop the result set down to your output. So collect is something you use when you're working interactively with a small piece of data. If you're working with like a terabyte, you would not want to collect because that'll throw an out-of-memory error. Cache is a directive to take that RDD and it tells the worker nodes, if possible, cache your partition in memory. Now, when you're working out on a cluster in a multi-tenant environment, you don't know exactly what resources are out there. You could have different shapes and sizes of servers in the same cluster. But if at all possible, cache it. There is a LRU. There's a least recently used mechanism along with the caching, so you will get evictions as well. But effectively, cache is just directive. It doesn't actually happen right away. It only happens once the intermediate results are computed. Now, yes, question?
I have a question with exactly what you were saying. Is that similar to materialized view?
Materialized view, that's a really good question. It's not exactly that, but a similar notion. The idea is that when we get down to the point of messages and then we cache it, it's effectively the same kind of idea. We've got this projection, and it's more of a logical description of what the data will be at that point. But you can think of it as almost checkpointing in memory, is what we're saying. And then we can use it in multiple ways, so we'd have a similar usage as materialized view. Materialized view, though, would, in my opinion, would have a stronger notion of schema. And here we haven't done that yet. We're assuming that we bring in some log files and that they're text. And we're assuming that they're tab separated because we did a split on tab. So all that we really know is that we have multiple columns that are text. They're strings. So the schema's pretty light there. We'll see other examples as we move into Spark SQL, where we have a much stronger notion of defining the field names and types. And at that point, it begins to look a lot more like materialized view, yes. Good questions, yes?
Assumption with text file that line return, carriage fee means end of.
That's a great point too, yes. So log files like this, using the Hadoop input format connector, it's assuming that, yeah, you're hitting a end of line is where you're going to split.
Is that work both Unix, DOS-based?
Well, it's more an artifact of Hadoop, actually, because we're using the Hadoop connectors by default.
Or maybe if you have a file that contains n characters, how will it determine? It seems like there's an implicit assumption.
Yeah, there's definitely an assumption. Although the thing is that you can also change out the connectors there. You can reconfigure that or write others. It could be some other type of serialization. As opposed to just line-oriented unstructured text, it could be JSON. It could be Parquet, Avro, Thrift, et cetera, et cetera. So, as long as you have those connectors defined, you can use a wide variety of different data. But that's a good point, because what we're assuming is that that Hadoop input format connector is smart enough to know where to split. Because if you have this huge text file, then you want to split on a line boundary. Yeah. Yes?
Yeah. When you say messages got cached, is it persistent or it's only in memory? So if your cluster crashes, the cache goes off, right?
Yeah, we'll go into that in more detail, but that's a good point. You're persisting in memory. So if you lose that node, you'll have to recover that data, that partition for that node. And the way that we're persisting by default is by recompute. I'll talk about that in a bit more. It's kind of looking at this generation of hardware, it makes the best sense. But let me, actually, let me move forward on, unless there are other questions. Yes, in the back. Not in this case. Well, I'll take that back. Yes, it is. I've got it. What I've done is to take and mount. Sorry. I mounted an S3 bucket where I have the error log data. And so from Spark's perspective in the notebook, it's out in the cluster. Realistically, it's an S3. So that's just for this example. Typically, yeah, if you were accessing HDFS data, then yes, it would be out on the cluster. Yeah. OK, so let me show these last two lines, though. Just a real important point is that we've got action 1, action 2. So the first one says messages, we're going to apply a filter. In this case, we do xfind MySQL. So we're going to basically peel off all the error messages that have to do with MySQL, and then count them. At the end of it, it says count paren, so there's another function, and it'll basically take that RDD and just count the elements. So what we're saying is, assume that we have some sort of web app that we've been running, and it's got different pieces to it, some PHP and MySQL backing, the data, et cetera. We're going to count the errors that are related to MySQL, and then in the next action, we're going to count the errors that are related to PHP. We'll just come out with a couple of counts. But what this does is to illustrate that messages, that projection of the data, is going to be reused. It'll be used twice. And so this will illustrate what goes on with Spark in terms of leveraging the cluster and the caching. Oh, and by the way, I mentioned before that you can print out the operator graph at any point. So here, as we get up to the point of taking a look at how many MySQL error messages there are, I did print x2 debug string. You can print that out for any RDD. And it shows what the operator graph looks like. In Python, it doesn't have as rich a data, I think, as, say, you'd see in Scala. But effectively, they're the same. You read these from the bottom up. So from the bottom, it's saying that it's going to read in error log text, and then it applies different transformations to it. OK, so I'd like to illustrate how this works out. Initially, we've got some sort of cluster. And so in the cluster, there are these different worker nodes. I'm showing 3 of these here. But there's also the driver. And the driver is the client side. That's where you're submitting your code. So in our case, coming from a notebook, the driver is in the notebook. Now, when we get up to this point here of saying messages.cache, all of that business logic has just helped to build out the graph. Nothing has executed yet. So effectively, nothing has really happened other than this being evaluated on the driver. Now, we're assuming that data is out in the cluster. So let's say that we've got blocks of data for each different worker node. When we get to the first action, that's when the wheels start turning. And the graph that we've created, that gets serialized out to the cluster. So the driver is going to send that out to all the different worker nodes. Each worker node has its own block of data. So it's going to go out and read from whatever the source is. Here, it's saying HDFS. In this example, it's actually using S3, but a similar kind of idea. So all the partitions will be, all the worker nodes will be bringing in their own partition of data. They'll process that per the graph. They're executing the serialized code. And because we persisted the data, they will all be persisting their own partitions in cache, in memory. Now, what this program is doing is counts. So it's, we're going to take the partial counts off of each worker and bring those back to the driver and sum them together to get the full count. That's the first action. Now, when we get to the second action, we already have the intermediate data, messages, RDD, has already been cached in memory out on the worker nodes. So rather than grabbing the data from disk, instead it can just process it from cache. And then it sends the partials down and gives us the full count. So there's a lot less processing that has to happen on the second action. And if I cut over to showing this in the notebook, I'll go to log example. And let me, no, I did not want to lock it. Unlock that. And let me attach this. OK. There. So if I run this, I'm going to say run all. Run. Oh, goodness. Prompting me for something. Foo. Somebody changed this. Aha. Now I really wish there were those ACLs on here. OK. Let me go through and execute this one by one. So I'll take the first line in, and OK, great. It's showing 0.07 seconds. And then the second one here, it's also going to be very quick. It's just building out the graph. So there's nothing really to compute yet. I come down here, I can print out the graph, great. And down here, MySQL, great. So the first time through, it took 1.72 seconds. You'll see this on your own notebooks. And it told me that there's 7 MySQL errors in that data. Now, if I go to the next one and I look at the PHP errors, great. That's going to come back with 0.17 seconds. So it's an order of magnitude difference by using in-memory as opposed to having to go back out to disk. And this is a really important point with Spark, is that by taking the graph and sending it out to the cluster, doing the lazy evaluation, we're able to get fault tolerance, we're able to get the parallelism. By having the persistence, we're able to leverage the resources in terms of multi-core and memory, et cetera, and be able to get much faster speeds as we go and reuse some intermediate data. That's effectively a kind of pipelining, similar to what you see on processors with pipelining. We're trying to get the best throughput we can off the cluster, so we want to try to take these workloads and really get pipelining. That's really important when you get into more complex kinds of applications. You could think of perhaps some machine learning algorithm that's going to take an intermediate piece of data, an RDD, and iterate through thousands of times or millions of times. Being able to reuse that data from in-memory resources will really give a lot better pipelining. OK, question in the back, sorry. Sorry, bound partition? I said the log file. Yeah? Where is that? Can you see it on here? How did it get up here? The log file. I'll show examples a little bit more later, but the source data it's coming out of an S3 bucket, and the S3 bucket has been mounted into Databricks Cloud so that it appears as if it's part of a distributed file system. It's a little bit of voodoo there, but effectively it's making distributed access across S3. Okay. Question, yes?
So it looks like the driver is the supervisor here for all the workloads. So
Yes.
Is there a single point of failure in
Very good. It can be, although it's also hardened. We can do, there are a few different types of clustering modes with Spark. We'll talk about those in more detail. In this case, it's something called standalone, which means that Spark itself is managing its own clustering. And the driver in standalone, you can actually restart. If we lose a driver and we've kept its metadata around, we can restart it and still recover.
What if it's in the processing, in the middle of the processing, if the driver goes down?
Well, no, that's a really interesting point. I mean, here you've got this back and forth because you have some different counts that are being brought back down to the driver. So the driver is actually capturing some of the state. If I were doing more complex processing, though, I'm probably not doing that. Realistically, I will have whatever computed results I have, maybe a large data set that I'll want to write in parallel out on the cluster. And so in that case, the driver is not really going to be holding the state. It's more a matter of being able to recover talking with all the different worker nodes. So you see this especially when you get into, say, for instance, Spark streaming, where you have a lot of moving parts and potential failures at every stage. Streaming is very complex this way because you have upstream, the sender and receiver, you have the metadata of the topology, you have all the data in flight, et cetera. So with Spark streaming, we actually have the means of recovering a lost driver, as well as the other parts. Again, it's a little more crucial in real time than it is in batch, but there are mechanisms for that.
So can the other worker nodes become drivers, or does the driver that went down has to be the driver again?
Interesting. So in a large cluster, I definitely have seen configurations where you can be running the driver out on the worker nodes. It really depends a lot on security and what the environment, the compute environment is like. In this case, we've got different EC2 nodes in AWS, and some of those are running the shards. That's where the state is. And so we can get rid of the clusters and still preserve the state. I'll show that in a little bit. But perhaps if you were doing a private data center in finance, they would probably have it very much locked down. The driver would probably be out inside of the locked part of the cluster. So it really depends on the environment. Question, yes?
In the first action, the syntax is slightly different than in the second one. The first one we did just X colon MySQL and X. The second one we did the find. Is there any cells?
I noticed that too. It wasn't supposed to be that way. Somebody went in and rewrote it while I was talking. So no, my apologies about that. But yeah, another good reason for ACLs. In Python, there's two ways of doing a substring search. One is to actually take it and say in, and the other, which is more implicit, and the other is more explicit, where you say string.find greater than or equal to 1, or greater than or equal to 0. So those are equivalent ways in this case. There are some subtle points where that wouldn't work, but somebody had just rewritten it to see if it would be the same. Yeah, yeah. But I could do it both ways. Yes.
I was wondering if you were going to talk about how that Spark context is created,
Ah.
the one that's used to get the initial RDB.
Well, we'll show some examples of that, but effectively it's an object. It's just part of the API, and there's an object that's instantiated. And I mean, there's defaults for it, but it will pick up the configuration. So there are ways programmatically you can go in and change the config, or just specify a particular config file. But then the other side of it is it needs to know what cluster resources you're going to use. So in this case, when we're attaching and detaching to clusters, that's effectively telling the context which cluster to use. So, yes?
Basic question. You talked about sort of pipeline, process pipeline, and master worker pattern here. How does
Yeah.
Spark pair with MapReduce from sort of the data flow?
Excellent question. Although I've got a whole other section coming up about that. Short answer is that, well, actually, the next slides here will show. Short answer is we can look at this from another perspective. If I use the term applicative system, anybody here worked with applicative systems before? There was a great paper I'll show in the history section coming up. But in the mid-'70s, there was a lot of early work on functional programming. And not Lisp per se, but some other, more specifically, functional programming languages like Miranda, FP, et cetera. And the idea was that if you take an array, or a matrix, if you will, but some array of data. If you can take and specify an algebra of a way of applying functions to an array, then we can take and parallelize that. So if we did have a multi-core kind of environment, we could take a large chunk of data as an array or a matrix and apply a sequence of functions to it, run this in parallel, but then have guarantees of how the results will be correct. And that notion came out in, like I said, the mid-'70s. And a lot of compiler optimization theory is based off of this. A lot of SQL optimization is based off it. It's part and parcel of Spark. And Spark really, I'll talk more in the history section, but there was an earlier project called Dryad Link from Microsoft. I don't know if anybody's seen that before or read about it. But Microsoft Research had done a project moving beyond Hadoop, more sophisticated than Hadoop. And for whatever reasons, Microsoft canceled this. But it was really excellent work, and it did help inform Spark and some others that are in category. So we'll look at the compare-contrast between Hadoop and where Spark is at, but it's specifically about a later generation of hardware. How can we really get the pipelining? Does that? Well, I'll go in more detail, but I hope that starts to answer it.
Yeah, I think basically, well, let's see what you come up with.
Okay, sounds good. Yeah.
You're asking that people not have their phones connected to the Wi-Fi to help with
Oh, yeah, that's a great thing. Okay, great. So the request was if you have cell phones or other devices connected up to Wi-Fi, if you could just focus on having the laptops instead, not having the phones connected, but just the laptops, then hopefully that will improve some of the bandwidth problems that they were having. Okay. So I want to introduce the notion of how to look at evaluating a graph, an operator graph, as an applicative system. So if we start out, we've got some endpoint, some base data, and we're going to define an RED pointing to this base data. And then we've got some series of transformations. There's lazy evaluation, so the transformations don't happen right away. All they do is to build up the graph. So we keep applying these transformations. In algebra, we call this function composition. You take two functions and put them together into one. And that really helps out when it comes to optimization. At some point, though, you need to get a piece of data. You need to actually get some results out to make an evaluation. So you can think of that as being a kind of decision point. And so we call those actions. When we hit an action, that's when the graph gets evaluated and we get some results out. So again, think of having arrays and matrices of data, applying functions to them, and then at some point getting the results out. And so going into the history, where this came from. I definitely want to point to a really fundamental part of the history was in about Q3 of 1997. There were 4 teams working independently. They didn't really know about each other. But there was Randy Shup's team at eBay, Greg Linden's team at Amazon, Eric Brewer's team at Inktomi at Berkeley, which later became Yahoo Search, and Larry and Sergey at Stanford. They were going to spin out the next year as Google. And all 4 teams were working on this notion of horizontal scale-out. So in the late 90s, you know, if you're building web apps, by the way, how many people were building web apps in the late 90s? Anybody do CGI? Ah, yes. Okay. You know, back in the good old days, if you wanted to scale your web app, you would buy a bigger and bigger server, probably a Sun server, and a bigger and bigger Oracle license, and just scale up. What these teams realized, I believe at the time eBay was 4 servers, and Amazon similarly, they just had these ginormous Sun servers, and they didn't have a lot of them. But they realized in Q3 of 97, they came to the realization that if this e-commerce thing really grew, they were going to be in trouble because they wouldn't be able to handle the load. And effectively, Sun and IBM and Oracle and others would be taking the money off the table. So all of these teams have published, but in particular, Greg Linden's team at Amazon and Randy Shup's team at eBay have done some great retrospectives publishing what they were thinking at the time. They took their workloads and they effectively parallelized them and rewrote them so that they could run on commodity hardware, Linux, on commodity hardware. And they made it such that as they needed to scale, instead of buying larger servers, they would scale out horizontally. They would just add more commodity hardware to their cluster. Like I say, Amazon and eBay in particular got this in place in Q3 of '97, which was really great timing because Q4 of '97 is when the first big tsunami of e-commerce hit. So that holiday season of Q4 '97, Amazon and eBay were in place to be able to use horizontal scale out and absorb all that traffic and become, mega billion-dollar companies. But it was really interesting from the perspective of the technology. By having horizontal scale out on clusters of commodity hardware, what this meant was they were capturing a lot of log files off of these web apps. And this was back before we really had a formal notion of middleware. Middleware came in a few years later for web apps. But effectively, we were collecting, at the middleware layer, we were collecting a lot of log files about how people are interacting with these web apps. And what Amazon, eBay, Yahoo, Google, and others did was to take those log files, machine data, if you will, take those and aggregate them, and take the aggregated log files, feed them into machine learning, and then create classifiers, recommender systems, et cetera, data products, which were in turn fed back into the web apps to make for richer interaction. So you get this kind of virtuous cycle based off of machine data. And at this point in time, the late 90s, actually the data that you saw on the web up to that point was mostly entered by people. Somebody had written an HTML page, or somebody had entered data into a database that was building an HTML page. But after this point, the machine data began to eclipse that, so that most of the data you were interacting with, more and more, was machine generated. You get this kind of virtuous cycle between the web apps, the social interaction of the web apps to log files, aggregation feeding into machine learning creating data products to make the web apps smarter, better recommendations. People who bought this book also bought this other book. And by virtue of that virtuous cycle then created more and more machine data, more and more need for larger scale clusters. And of course, this led right away to what we saw with Google and others. To put it on a timeline, early 2002 period, 2003, Google was working on MapReduce. They published it in 2004, and Spark definitely falls out of this timeline. In particular, so this would have been 5 years afterwards, Google had been doing horizontal scale out, and they had some fairly complex workloads, machine learning workloads to compute PageRank, to crawl websites, et cetera. And one of the problems is, if you're just rolling up log files and doing some fairly simple reporting, doing that in a distributed fashion on a cluster of commodity hardware is a no-brainer. But once you start to get to more complex workloads, you have the risk of failures actually interrupting your job to the point where you can't complete it. So for instance, if you're doing a large machine learning workload on a cluster of, say, 2,000 nodes, let me ask, what's the expected failure rate for a 2,000 node cluster per day? How many servers would you expect to have dying? Any takers on that? 5. Yeah, that's good. Good, excellent. And this comes out of John Wilkes, who runs Omega. The Omega project at Google is their cluster management. And he reported this recently, that the average failure rate, daily failure rate at Google currently is 10 servers per 2,000 node cluster per day. And that's current hardware and current practices at Google, which are quite good. You can imagine that in 2002, it was a fairly higher rate of failure, largely because of spinny disks. So if you have a large machine learning workload at Google in 2002, and spinny disks are failing underneath you, the probability of, oh, I just lost some servers, let me restart them, the probability of actually completing the workload drops to 0. because you're just restarting so much you're chasing your tail. So what Google did was, number one, to build out the Google file system, get a nice distributed file system so they could get through some of the problems with spinning disk failures. And then over the top of that, they built MapReduce. It wasn't so much about speed, it was more about fault tolerance. MapReduce, how many folks have read the original MapReduce paper? Anybody here yet? Sanjay Gemawad and Jeff Dean and all. If you look, the first paragraph, they talk about functional programming, how they had borrowed concepts from functional programming to build fault tolerance. And in particular, the math for this goes back to the 1930s when Alonzo Church and Haskell Curry and others were working on the notion of combinators and lambda calculus. They came up with patterns of being able to define what could be computed, even years before they had digital computers to work with. But lambda calculus in particular has some different patterns. One is called a map, another is called a reduce. There's several of these. But to create MapReduce, they had gone back to the math of the 1930s. And it's what Spark is based on. This work was done in 2002, 2003, published in 2004, and of course, very famous work at Google. I've got some of the primary sources if you want to read about where this came from. But let me ask another question. What has changed since 2002 when we take a look at data centers and hardware that we use for commodity computing? What's different today than we would have been working with back then? Any takers? Yeah. Yeah, definitely the disks have changed a lot. Memory's cheaper, a lot more memory. Multi-core. Multiple clouds. How about networking? Speed, definitely. Yeah, gigabit. We would have had much slower networks. Wouldn't have SDNs. We talked about memory sizes. Right now, the cost curves on memory spaces are dropping. It's almost getting hard to distinguish what's memory and what's SSD. So the bottom line there is that significant changes to what is commodity hardware today versus what they had back in 2002. Hadoop was based on this. And Hadoop was largely about the trade-offs circa 2002. MapReduce was about avoiding the spinning disk failures based on that kind of hardware. Great. Now, MapReduce, like I say, it borrows heavily from functional programming. And it really did get us past a lot of the original problems with horizontal scale-out. But it did introduce some other difficulties. Number one, there's the problem of programming in MapReduce directly. So one of my teams had the dubious distinction of having the largest Hadoop instance in the cloud back in about 2008, 2009. And our team was a guinea pig for Amazon to come up with a new service, is now known as Elastic MapReduce. It was called Project 157 back then. But the problem was that it was very difficult to find people, even today, people who can think in terms of maps and reduces for very complex applications. It's a staffing problem, if you will. Since late 2007, there have been a number of different abstraction layers that have been put on top of MapReduce. Cascading was the first, and followed shortly by Pig, and Hive and others have come from that. But again, they're still based on top of MapReduce. The other thing is performance bottlenecks. Definitely working with a MapReduce framework, you have a number of types of performance issues. One of the big ones is key value skew. So for instance, if your Twitter, the average number of followers on Twitter is like 205, the last published that I saw. And so for hundreds of millions of people, as Twitter is calculating, working through their social graph, in MapReduce, the reducer tasks will have somebody's Twitter ID and then 200 plus values, right? So it's not a lot to be able to compute in that one task. And they chunk through that, but then they hit Lady Gaga and Justin Bieber and Katy Perry, people who have 20 million followers. And so you get this really large skew in terms of the number of values per key. And what Twitter would see in that case would be that for most of the hundreds of millions of people, those reduced tasks complete relatively quickly, seconds or minutes. But then they encounter one of the heavy hitters, like Katy Perry, and those reduced tasks will linger on for hours. And the artifact there is that your cluster utilization rates drop to 0 because you have millions of tasks, but then only a couple dozen that hang on for hours. So the asymmetric skew problems of especially doing shuffles are a real performance bottleneck on MapReduce. A lot of ways to try to work around that. In short, though, MapReduce doesn't really compose well for large, complex applications. As a result, again, since like 2008, 2009-ish, there have been a number of specialized systems that have emerged. And the general pattern is Google will publish a paper, and other people will scramble to create the open source version. So Google published MapReduce, and of course, that got picked up by the Nudge project, became Hadoop. Yahoo sponsored that in 2006, and the rest is history. Google also published about bulk synchronous transfer, the Pregel paper for large-scale graph processing, and an open source version of that would be, say, Apache Giraffe or GraphLab. Google published about nested tuples in the Drummel paper and Apache Drill as a result. F1 going to Impala. The Google project for streaming real-time analytics is Millwheel, and we see things like S4 and Storm, et cetera, from that. The takeaway is that MapReduce itself doesn't really work for these specialized use cases, so other types of systems have evolved. But the downside of using a specialized system is, number one, it requires more cluster compute resources. Number two, there's also the issue of getting the operators, getting the ops team who have the specialized skills to manage these at scale. That's very expensive. If you are Google or Facebook or Twitter, you have armies of highly specialized ops people. If you're a 20-person startup, good luck. Hiring that kind of talent is very difficult. And so the more types of specialized clusters you have, the more need you have for the ops component. That's usually the limiting factor. Number three, another problem is training. And having run data science teams over the years, training your people on all these different types of specialized systems is a real nightmare. And then number four, probably the biggest killer on this, is if you're taking and ingesting your data as it comes in off of, say, Storm, and then from there moving it over and doing some roll-ups in Hadoop, and then from there dropping that data out into a graph processor in Giraffe. If you're bouncing the data across all these different clusters, you pay a wire tax. Moving the data from one to another incurs a lot of latency. And in some types of businesses, finance, advertising, you can measure revenue loss in milliseconds. And so the wire tax, the latency, is actually a real killer. So what they were looking at circa 2009-ish was MapReduce is great. We've got some excellent use cases that we've built up. It would be a lot better if we could just have a more general way of pulling this together and working on one cluster, doing a general engine for all these types of use cases. And so at that time frame then, Mate Zaharia was an intern at Cloudera and had been working on Hadoop, did some fairly well-known work in Hadoop, fair scheduling and all. But he'd definitely seen a lot of these use cases, and other grad students he was working with had also been working at Cloudera and Yahoo, Google, and they definitely seen large-scale Hadoop use cases. There was a project called Mesos. Actually, at the time it was called Nexus, and Ben Hinman had been an intern at Google. Ben Heinemann, sorry. Don't mean to mispronounce Ben's name. Ben had been at Google, and he'd been working on cluster management. And I was actually out at Google Seattle visiting Ben the day that his Google managers came in and said, we're not going to move forward on the project. We already have our own cluster managers. So I took Ben and his team out for beers that night because they were rather depressed. But they went to Berkeley, and they started in on a lab It was called RadLab at the time. Amazon and VMware and Google and others were sponsoring this, but there were quite a number of PhDs, actually a fairly large lab, and they were all working in distributed systems. And they had this project that's now known as Mesos to be able to take commodity hardware and run different types of workloads on it. At the time, they had 9 Linux boxes being shared by, I think, 40 different PhDs, and all of them wanting to do MPI and Hadoop and these large distributed things. So they needed to share resources, and that's what Mesos is about. Matei and others from the Spark project were working on Mesos then originally. Once they got that running, Ben's family comes from part of Colorado. Some of my family comes from as well, near Aspen. And Ben took part of his team back to his parents' cabin there for spring break. And they came up with the first Mesos framework, dedicated framework in Mesos. They were looking at how to build something faster than Hadoop. And so Matei was working in Scala on top of Mesos and came up with an alternative to MapReduce, which is now Spark. That was the origin of Spark. Originally, it was a very, very small amount of code. It was leveraging a lot of what was already there in Mesos, and also what comes in Scala. But that was 2009. It was pushed open source in 2010, and since then, it's really grown wildly. It's become one of the most active projects in the Apache Foundation. I've got numbers up here about, I'm sure these numbers are out of date. There's more contributors and organizations now. But really picked up steam. Here's a couple of the original papers from 2010, 2011, 2012 about Spark. And again, the thing is that this is picking up a decade later after Hadoop, after MapReduce. And there's a much later generation of hardware, and there's more sophisticated software practice of being able to leverage these new resources. So the thing about it, Matei's thesis then was he wanted to generalize MapReduce to be able to handle those other types of use cases. There were really 2 changes that needed to happen. Number one, fast data sharing. Being able to take the later generation, the contemporary generation of hardware, and be able to share data across, effectively the memory caching, if you will. That was a big game changer. And the other was general DAGs. DAG means directed acyclic graph. So being able to generalize the notion of a graph, do the lazy evaluation, be able to get the fault tolerance and the parallelism and the optimization. The latter point, again, came out of a project called Dryad Link at Microsoft Research. But by doing 2 reasonably small additions, you could generalize what was going on with Hadoop and come out with a much more general purpose engine. And so that's the notion here of Spark, is we've got this core engine underneath it, which can be used in a number of ways. On top of that, we can build other abstraction layers. Spark SQL maps very directly to the functional programming. Spark Streaming, we'll talk about that in more detail. MLlib builds on these concepts for machine learning, GraphX for graph computation, et cetera. So this is the way of getting around having a lot of specialized clusters. And again, a real game changer. Yes?
So you mentioned about, like, if you're processing so many tweets and, it's like all others, nobody's getting a chance to win. How do you solve with this if you can?
Well, so one of the things is being able to parallelize the problem very effectively. But also, so getting back to an earlier question here, if you're just going through a linear map or a filter, you're working on a partition at a time, that's a fairly easy thing to manage. Once you start taking a look at, say, joins, or some type of aggregation, again, going back to the driver for this was to take a lot of log files, aggregate them, and feed them into machine learning. So we see this over and over. When you do the aggregation, typically you have to redistribute the data. And so the question is, how can you leverage this more contemporary generation of hardware to distribute it in a much faster way? As it turns out, Spark has much less overhead for doing shuffles compared with MapReduce, compared with Hadoop. That's the real quintessential difference, is that the shuffles are handled in a much smarter way. And so it means that when you have to do that redistribution, hopefully you can be much more efficient. If you handle your partitioning correctly, you can reduce the requirement of the shuffle altogether. That's a real key. But a lot of it gets back to the point, let's see, I'm not showing here. In Hadoop, in MapReduce, the challenge was spinny disks failing. So what they did was to create synchronization barriers. If you look at a MapReduce job, there's a map phase and a reduce phase and a shuffle sort in between. You've got synchronization barriers through that. Number one, you're going to lift your data doing what's called a flat map. You lift your data up from distributed file system into memory and do some processing. And then you've got a synchronization barrier where you've completed that and you've done your sort out to your reduce tasks. You've got another synchronization barrier, then completion of the reduce tasks. So there's 3 synchronization barriers per job. Now, if you think of, I mean, going back to 2008, running large-scale machine learning for advertising, we had the largest Hadoop cluster in the cloud. And that application there had like 15 Hadoop job steps that we'd written. It's a fairly complex app. And what you see is you've got all these synchronization barriers. Realistically, though, it's not always map, reduce, map, reduce, map, reduce. It's more like map, 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 filter, reduce. That's a typical kind of pattern. With Spark, you can take and relax the constraints that Hadoop had. We're not quite as paranoid about the disks failing at this point. We've kind of handled that, especially with Cassandra. But what we can say then is that since we know that we're going to be doing map, 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 filter, reduce, we can take and apply some abstract algebra, going back to what they were working on in the 1930s and the 1970s. We can take the abstract algebra and apply function composition. So we can say the map, map, map filter is actually composed together as one operation. Now that's reducing 3 synchronization barriers at each step. So by doing this lazy evaluation, you can actually optimize and apply the abstract algebra to come up with a much, much more efficient pipeline, if you will. That's a real change. Good stuff. Other questions on those lines? Question in the back, yeah.
Is there any work going on in reshuffling the data on the storage?
Yes.
Based on the learning that is going on based on that, or these jobs that are being?
Well, yes. I mean, how do you repartition? That's a big question. And often you can go back to the math of how are you using this data. We'll take a look at a case study from Spotify, in particular, that I would point to, where they went and took their main workload, recommending music. They'd been running on a Hadoop cluster, and they'd grown. They'd been successful. They got to a point where they wanted to cut over to Spark to save money. And the first cut, they did a fairly naive translation from Hadoop to Spark. And it was faster, but they felt it really wasn't leveraging the features. So they went through 3 successive iterations, and they showed the source code at each stage. And also the math of how they were reformulating it. But they went back to the actual matrix math, the linear algebra that was used in their recommender system. And they looked at the math and said, OK, this will guide our partitioning. And if we know which rows and columns we're going to be working on, we can partition in a way such that we don't have to shuffle. And we can throw memory caching at the problem and cut down the shuffle requirement and just blaze through the data. So we'll show that a little bit later, but it's an excellent illustration of this principle.
Exactly, so that they're partitioning?
Well, the idea is that you've got, for instance, with music recommendations, you've got a lot of customers, and then you've got a lot of songs.
In general,
Yeah.
At the file system, they're partitioning?
Right. So the idea is repartitioning the intermediate results. If you're just bringing in the raw data, it's a no-brainer, right? Every different worker gets its own little slice. But once you start to enrich the data, once you work through the graph, and you do some joins, and you do some maps, some transformations, you do some machine learning, the intermediate stages of the graph become more complex. And the data essentially will be clumped up in different places. Repartitioning at that point is the key. So if you can do it in a smart way, knowing what math will be applied downstream, then you make the downstream processing much more efficient.
But repartitioning at what level? At the way that you apply the maps,
Ah.
et cetera, or at the way that you save the data, or do you cache it?
So typically when you get into the more complex processing, you're looking at keys and values. We talk about RDDs, and the RDDs that I've shown so far were fairly flat. It was just a log file with a tuple. But as I get into more sophisticated use cases, I've got key value pairs. And so we have this notion of a pair RDD, and there's other functions that are available in the API for that. And it's the key values that are the killer, because you aggregate on the keys, right, all the values. But if you have skew, that becomes, you get hotspots in the cluster. So by repartitioning where the keys are, you can get great benefits. Also, when you do joins, you've got this cross product, right? You've got left-hand side and right-hand side. You join on the keys, but then you have to evaluate the values across. And there's a lot of network traffic. If you can make sure that the values for both the left-hand side and the right-hand side for any given key are in the same place, you eliminate the network traffic. And so I don't even know what time it is, so let me see how far behind I am. So, OK, we're a little bit behind, but we're OK. This is a key point. If there's a generational aspect to cluster computing, if you were back in the early 2000s, suddenly disk became cheap. The cost of storage became really cheap. We had a bunch of data we're collecting because it was so easy to just get more disks. And if you have really cheap storage, then you want to distribute your data, right? And so you had this notion of replication for distributed file systems. Now, an earlier point, though, going back into the 90s, right before that, the thing that happened was networking became cheaper. And so if you wanted to do a distributed problem, you could just make a URL call. You know, somebody over there has the data I need. I'm going to access it remotely. So there's this generational change between reference and replication. So as the next engineering trade-off came in the 2000s, you had cheap storage. Then instead of doing compute by reference, you did distributed compute by replication. You'd save the results in a distributed file system, Hadoop. Now, getting into the 2010s, you get other types of resources becoming cheaper, multi-core memory. And so there, the trade-off is, if you can, recompute. And so you see this generational series of trade-offs. If you have cheap network, compute by reference. Cheap storage, compute by replication. Cheap multi-core and memory, recompute. So what that means is with recompute, you know, if I have some simple results in my graph, I'll just recompute them. It's a lot cheaper than making a reference. I want to eliminate the shuffles as much as possible. It could be 5 years from now, networking has some breakthrough, and it becomes cheaper, again, to compute by reference. So we'll see where that shakes out, but that's the driver. OK. Let's see here. We're probably up on time to do a break, so I think I'm almost done on this history section. The main takeaways are that with Spark, we do have the batch, the interactive, real-time, et cetera, all within a single framework. And we also apply native integration for Java, Python, Scala, SQL, now R. There's also a binding for Clojure called Flambeau. And it really is native. When you run Python in Spark, you are running the native Python out on the cluster. That's great because Python has things like SciPy, NumPy, NLTK, very sophisticated libraries, and you're actually running those natively. Another point is that this is a higher level of abstraction than you'd be working with in terms of Hadoop, or even in terms of things like Pig and Hive. And also the math. We're not just using map and reduce. If you go back to the original MapReduce paper by Dean and Gemawat, they talked about leveraging the map and reduce out of lambda calculus. With Spark, you're actually using more of the different types of patterns in lambda calculus. And I've got a list here of distinctions. We've covered all of these so far, but a lot of it comes down to generational difference in hardware. And proof in the pudding, you probably heard about this already, but recently, last November, Spark set the world record for something called the Gray Sort Challenge. Yahoo had held this previously, but it's sorting 100 terabytes of data. And the previous record had been done by Yahoo based on Hadoop. They had used approximately 2,000 nodes in a cluster, 2,100 nodes. Spark was able to beat this record with a little over 200 nodes in a cluster, 206. So it's 1/10 the size of the cluster, and Spark ran 3x faster. So across the board, the metrics are about 30x faster. Another change is that Yahoo never really published what their hardware was like. They did this in a dedicated data center. With the new world record, the code is like 3 pull requests, and it was done on Amazon, AWS. So it's repeatable results. If you want to grab those PRs and redo this, if you want to pay for that much compute time on Amazon, it's definitely doable. Another thing that's important to point out is to be able to get apples-to-apples comparison with the previous world record. Some of the features of Spark were effectively disabled. We did on-disk sort. We could have used memory a lot more, but we turned that off to make a fair comparison. So realistically, Spark is faster. Now, 100 terabyte sort with a large cluster, we could do that with memory resources. But we also wanted to push further, so we also did a petabyte, 10x the size. That would not have been possible to do in memory. We would have had to do that on disk anyway. But it's pretty interesting across the board how much faster this is. Now, another thing is taking a look at the curves here. We pulled this recently off of Apache's log metrics, but you definitely see this spike in about just before, it's about Q3 of 2013 that you start to see this hockey stick emerge for the amount of activity on Spark. Another thing I'll point out is O'Reilly did a survey recently of data science and salaries. Definitely Spark comes out with a higher median salary for data scientists. So it's a good way to tell your bosses about that. By the way, those are not error bars. There's a range here that they're representing. So that's more of a bar chart. But definitely some interesting analysis. Friend of mine, Danny Burkholz, writes for RedMonk, and he pulled numbers off of Stack Overflow. And just taking a look at the amount of activity, you also see this hockey stick effect just right before 2014 kicks in. So definitely there's been this huge uptick. It's a really interesting article. RedMonk published this recently. But Donnie had looked at not just Stack Overflow, but other types of online systems and comparing these metrics. And probably the most sophisticated, TypeSafe did a survey across the industry, much larger numbers than what O'Reilly had used. But it's pretty interesting to see the breakdown between Scala, Java, Python, what people are using in these production workloads with Spark. So I definitely recommend that. I don't know if I saw a hand. Yeah, I did see a hand, yes.
What is the reason of that spike?
Yeah, that's interesting. So Spark went open source in 2010, and then was incubated at Apache roughly around that time, and became a top-level project early in 2014. So by the time that it matured enough to be part of Apache Incubator, that's where the real traction started, in my opinion. I had seen this years ago, and I'd been working in Hadoop. I was working on a project called Cascading and then Mesos. And I hadn't really jumped into it until about a year ago, about the same time. I don't know if that's just the general zeitgeist of the industry, or if it's really that Spark was starting to really hit enough traction. I think that a lot of it too was you start to see the premise of having a unified engine and a lot of use cases on top. Up until late 2013, you definitely had the in-memory computing and the iteration, but you didn't really have things like Spark SQL or streaming and all these put together. And at the moment when all those use cases were put together, it was much more compelling. Yeah.
Another question is, so after all things that you've said, do you think that like within 5 years, Spark is just going to take over the Hadoop implementation? Or is it like that some things are just good with Hadoop, some things are just good with Spark?
No, that's really good. Well, I'm on record. About 18 months ago, I wrote an article saying that Hadoop had 3 years. And I, sorry, I need more water. I wrote that 18 months ago, and I was just looking back about it. And the argument I was making was Spark, actually. I was saying about the generation of hardware. And it was right when I was starting to get interested, but I hadn't jumped into Spark completely. But I was working on the Mesos project. And I said, looking at the trend lines of where Hadoop is at, there's been a lot of inertia because, for one thing, the committer base is split between two large companies that I won't mention. And so that's, there were periods in Hadoop where just nothing happened. There's all these PRs, but we weren't really moving forward. We were stuck at like 0.18 for a long time, 0.20. And getting out to Hadoop 2x took forever. So I was really feeling that just in terms of the efficiency of the open source project, Spark was a win. But also looking at how it was leveraging hardware, it was much better, much more sophisticated. So the thinking there is there are large places that have huge yarn clusters. You go to eBay or Twitter or whatever, they're not going to get rid of those tomorrow. And so there's a lot of great reasons to be using this infrastructure of Hadoop, reusing it. However, if you're a 20-person startup and you're in the cloud and you never had an army of ops people running your yarn cluster, why start? And that's what we're seeing. Actually, that was something that surprised me at the last the last Spark Summit was the number of people I talked with who said we bypassed Hadoop stack altogether. We were able to run Spark directly off of S3 in the cloud or on top of Cassandra, and we never really needed to invest in the Hadoop stack. We don't really see the reason for it.
So some companies are doing Hadoop with Spark.
Oh yeah, definitely. I mean,
What is the use case for that?
well,
Just because they had Hadoop and
no, I mean, definitely it's there. I mean, if you are a large company that has made the investment in Hadoop, then that's your operational practice. That makes all kinds of sense. Your data is there. And you can run Spark on top of this very conveniently. Spark runs on Yarn very nicely.
it's doing the same thing, right?
Well, the MapReduce part. I mean, to be fair, when I say Hadoop, I should clarify because Hadoop is pretty large. MapReduce is just a portion of this. All the plumbing, the connectors I mentioned, Spark is reusing those. So a lot of the code is actually being used. The distributed file system, you're going to have some sort of storage. Spark doesn't have storage. As far as data at rest, Spark has no notion of this. So it must be married with some other types of storage. So that's a very compelling reason to use something like Hadoop. Cassandra's a great fit, other things as well. In my opinion, I think that when we start to move more into real-time use cases, that becomes a question mark. At that point, I seriously consider if Hadoop is moving fast enough for the industry requirements. But that's just my opinion. Yeah?
Is any file system more better than the other, like HDFS versus Cassandra?
Oh, that's great. Well, there's a number of them. And I have seen some large labs working with very sophisticated distributed file systems. If you're working with the intelligence community, if you're working with certain parts of the federal government, let's say, one of the first things they'll probably ask is, can we flip out this distributed file system with something more secure? And you can go to IBM and buy those. There's definitely things like Gluster and whatnot that, other types of distributed file systems that are better performance. And I've talked with friends at some larger labs who've done a lot of evaluation of Spark on those. So it's pluggable, is I think what the graduate students usually say is it's pluggable. Other questions? Yes?
It seems like when setting up a Spark cluster, there's a trade-off between the amount of RAM to allocate to each node
Yeah.
and the number of nodes.
Absolutely.
So can you talk about that trade-off?
Yeah, no, that's really interesting. I mean, when you look at more contemporary hardware, if you have 128 gigs of RAM, you're not going to just throw that all at a JVM. That'll just cause a lot of garbage collection. And so one of the things with Spark is to use more sophisticated ways of leveraging the memory space, do more off-heap. And so, for instance, when we talk about the shuffle being more efficient, one of the things subsequent to the world record sort was to have a shuffle service. So leveraging Netty and doing an off-heap shuffle service that's actually persisting beyond the actual tasks. So yeah, definitely managing the memory becomes a challenge. Since you have multi-core, it makes sense to be leveraging containers, using C groups, and for Linux containers. Spark came out of Mesos. And the notion there was if you have a machine with 24 cores and 128 gigs of RAM, you could parcel that out in terms of multiple containers. They could all effectively look like their own nodes. But it's a way of getting rid of virtualization. So, I mean, talking just a brief aside about Mesos, in contrast to Yarn, or in contrast to what we would do with VM practices, Mesos is about using C groups and actually working directly on the metal. And when you get a really heavily loaded cluster, especially with services, virtualization is a killer. So Google doesn't use virtualization. They use something similar to Mesos called Borg and now Omega. And they do dev, QA, production, all in the same machines. They just mix and match. But by virtue of having containers, they can isolate. So that's a big thing about Spark is you've got a new class of hardware, and the containers are a real game changer. Yeah, question?
Okay, if Spark runs on a Hadoop cluster, then Yarn becomes a resource manager.
Right, yeah.
If we run Spark not on a Hadoop cluster, what serves the role of a resource manager?
Right, well, so there's three types. We'll go into that in a little bit. Actually, first off, I've got a section about that, so I want to go into much more detail. It's 11, though. We've been up for about 2 hours. Let me take a bio break first. How about we'll let everybody go for about 10 minutes, and we'll come back. And we'll thank you, Vita. Great. OK, great questions during the break, and great questions all through. I think that the interactive part of this is really fun. I want to go through some coding exercises here, and hopefully this will reinforce some of what we've discussed in the questions, start to show some of how these parts work. So first off, I can imagine everybody's heard of word count before here, or has everybody heard of word count, I should ask. I call word count a canary in a coal mine. The thing about word count is it has just a few steps. I show some pseudocode for doing word count and MapReduce over on the right-hand side, and it's just a few lines of code. But within that, it has parts that are symbolic, parts that are numeric. It has parts that are relatively easy to parallelize, and has parts that are relatively hard to parallelize. And so if you can do word count efficiently in parallel at scale, then you know that you have guarantees for a much broader class of interesting problems that can also be done on that framework efficiently in parallel at scale. So for instance, word count is just a few steps away from doing, for instance, TF-IDF, which is the keyword ranking algorithm inside of Lucene or Solr or Elasticsearch. So it's pretty close to very interesting workloads. Now, if we take a look at word count that ships with Hadoop, there are 53 lines of unapologetic Java. And I don't know if Dean Wampler is here today, but one of my friends from TypeSafe, Dean Wampler, gave a great presentation on how much that example word count resembles what we used to do with something called enterprise Java beans. Anybody worked with EJB? Yes, OK. So that style of coding is well known. If you go into functional programming, in Spark, the same word count can be expressed in 3 lines of code. And this is something we see across the board. Doing the functional programming, we see a dramatic decrease in code volume. And from purely a software engineering perspective, putting on my engineering director hat again, if my team is responsible for an order of magnitude less code base, then there's less opportunities for bugs, less code to relearn. I usually have to go and relearn my code every 6 months anyway. It's easier for teams to pick up the business logic because it's very streamlined. So this is one of the real benefits we see for functional programming with big data, and a lot of the rationale for using languages like Scala and Python, et cetera. Definitely, we see this out of Spark a lot. So let's try word count in Spark here. If you go to the Spark Camp directory, Spark Camp folder, under that there will be a notebook called 02 WC example. Clone that into your own folder, and then attach it to a cluster and run. I'll show my examples here. OK. Let me. So here I've got a word count example where I've got other strange stuff that's been added. Good. So first off, I've got a README file. And I loaded this out of an S3 bucket. But it's just a simple README file for the Spark project. So I do sc.txt file, read the README file, and create an RDD called lines. And here I'm going to say lines take 10. You can always take an RDD and say take. It's like doing a SQL limit. But it'll just drop out the first several lines. So let me change this a bit. Let me do take 4. And I do shift return. That'll evaluate. So it drops out the first 4 lines out of the README file. And so this is an RDD of type string. Each line is a string element. Next up, I'm going to bring in a library for Python. There's an operator called add, a very simple part of Python. But you may have heard the term monoid. Anybody been reading about monoids? Some. OK, so add is a monoid. It's an associative binary operation that has an identity element. And that comes in really handy for parallelizing. We'll show that in a moment. OK, so the real logic here for word count is we're going to create an RDD called WC. So we'll take lines, which is an RDD of string elements, and we'll apply a flat map. And inside of the flat map, we've got a lambda expression that says for each line, take that string and split it on space. And so that will create a list of keywords, space-delimited keywords from that line. Now, a flat map is interesting. If we look at the map in MapReduce, in functional programming, we call it a flat map, actually. A flat map says you take one element and you have 0 or more output elements. A map formally says take one element and have one output element. So the map in MapReduce is actually a flat map. So what's interesting here is we're going to take a line and split it into 0 or more keywords. It'll be a list. By doing a flat map, what this says is just flatten out that space. So we'll have an RDD of lines, strings, and then from there we'll create an RDD of keywords. Now, if I didn't do that, if I did a map instead of a flat map in the first part, what I'd end up getting eventually would be a list of lists as I do each transform. And that's a bad thing, because then you have to go and navigate all through those lists. So we're flattening out the space to make it simpler to operate on. Also, that's interesting when it comes to repartitioning, because now we've got these other elements, and they'll have to be distributed across the cluster. So I've got keywords, and then I'll apply a map. And inside of there, I'm going to reshape the data. I'm going to create a key-value pair. I mentioned this before. Key-value pairs are very important here. So we've got lambda x goes to x comma 1. And that's how MapReduce works. Sorry, how word count works is we're going to take for each keyword and give it a count, 1. And then in the next function here, we call reduce by key. And that's where we apply the add monoid. We'll say that for each key, grab all of its ones and add them together in parallel. Now, by virtue of using the monoid add, what that says is we're going to start out, take all the data, and look at it as a tree. We'll just take 2 elements, add them together, and then take the results, add those together, and just climb up the tree. What that means is that the add can be done completely in parallel. Now, with addition, this is very trivial. We know that we can add integers together. If you add 2 plus 3 plus 4, you can either add 2 plus 3 plus 4 or add 2 to quantity 3 plus 4. You can change the associativity. If you have a monoid like add, what this implies is you don't care about the order that the data comes in. So you don't really care so much about the partitioning of where the data is distributed on the cluster. You can add stuff together in parallel. It becomes much more interesting when you have more complex data and more complex operations to use things like monoids, but I'll talk about that in more detail later.
Equivalent in Java?
Pardon?
The equivalent for that in Java?
Yes, yes. And in fact, in JVM languages, there's a really nice library called Algebird that has a large number of different types of monoids for this kind of thing. It's very easy to define in Scala, and in Java, you could reuse that library.
You didn't see the parallelize in this because you just create the.
That's a really good point, parallelize. So yeah, no, coming back up here, and we'll talk about this in a little more detail, but up here we used text file. Text file and parallelize do the same work. So parallelize says I have a collection in the native language, and I'm going to parallelize that collection to an RDD. Text file says I have some stored data, and I'm going to bring that in partitioned as an RDD. So there's really two different ways to create an RDD, depending on where the data is coming from. It's effectively the same thing, though.
And assuming it's coming in from a Spark context, it's always an RDT.
Right, exactly. So the thing is that Spark Context is where all the API hangs off, and when you bring data in through Spark Context, the result of that is an RDD. Yeah. And then as you apply transformations, the results are RDDs. Yes, question?
So yesterday, a lot of people were talking about data frames.
Yeah.
How much of that stuff now is going to be changed into using straight data frames versus using RDDs?
Oh, that's great. Yeah, that's a great question. Data frames are being introduced now in 1.3. They're turned off by default. So you have to enable it, and it'll be more the mainstream way of handling things in 1.4 or somewhere around there. What data frames are a higher level of abstraction. They have RDDs under the hood, but data frames are thinking of the data as a table, if you will, and you can apply operations to them in a much more compact way. So I can say, okay, for the third column, find all the elements less than 7 or something. So it gives you parity with how you handle data frames in R and pandas and all this. It's virtually the same.
Do you see people moving into that type of design, just going straight to data frames instead of talking to
Yeah,
RDDs?
absolutely. We think that data frames will probably be the first step forward for a lot of these applications. You can always get to the base RDDs and do more sophisticated things in functional programming with them, but for a lot of the use cases, probably data frames is what you need. The thing about it is that with the lazy evaluation and with the higher level of abstraction, there's more opportunities for optimization. So data frames actually allows more of what you would see with, say, a SQL optimizer. A very similar kind of thing happening with lazy eval there. So, yeah. Good question. Okay, so let me run the word count, and I'm getting old enough I need my glasses. So, let's see here. If I do this one here, great. And of course, I hadn't, I don't know why, but I'll define lines. Somebody ran something. That's what I think. Okay. Okay, so I run this cell here, and this gives me WC defined as my RDD. Nothing has happened yet because I've just created the operator graph. I haven't evaluated it. But now I'll go down here and I will collect the results, wc.collect. And that's when the graph gets evaluated. And then you see the output there. You've got key and value. And the key is the keyword, and the value is the count. So that's an interesting thing. When you come out of word count, you've got a key value pair. Is that working okay for everyone? Good. Question, yes?
Well, I seem to get the same number of words, word count, no matter how many lines I feed it.
Oh, really?
Yeah.
Wait. So.
I changed a couple above to 2 lines, got 4 lines.
I got you. So right. So there's some side effects. Let me describe. The take is just it's just a way of a measurement. It's not actually part of the workflow. So I could nuke this. That was just for me to be able to look at things. Very good point, though. Lines, the definition of line stays constant there. Okay. Alrighty, let me go to the next part here. Join example. I definitely want to try to cover this before lunch. So if you look under the folder Spark Camp, there is 03 join _ example, and we'll go to that one. Great. And let me attach this. So same thing, take this notebook and clone it into your folder and attach it to your cluster, and we'll run through this. In this case here, we'll use a slightly different shape of data. Say that we've got a marketing funnel. So you've got some kind of web app, and people are seeing or they're seeing some kind of advertisement. They click through the ads, they hit a landing page, and then some number of people that visit the landing page will proceed on and register for a service. So we've got log files at the different stages of the funnel. We've got logs for the click-through on the ads, hitting the landing page. And then we've got log files for the registrations downstream. And so to construct a marketing funnel, we're going to count the number of clicks and then join those to the registrations. And typical thing working in big data, doing these kind of joins on log files. So first off, let's start with the clicks. Here I've got a file Again, just pulling this out of my S3 bucket, but it's called click.tsv. So we're going to do sc.txt file, load that up, and then we're going to split on tab, because it's tab-separated data. So run that. And now, let's just take a look at it. We'll do a collect. It's just a couple lines, a couple rows. But you can see there, I've got a timestamp, I've got a user ID, a UID, and then I've got an add ID. Where did it come from? So to be able to do some work with joins, I want to reshape this data into key value pairs. I need to do that to do a join. So here, I will take the tuples from the clicks data, and I'll reshape it. I'm going to do a map, and then the lambda expression inside the map will say that for every tuple x, I'm going to peel off the second column, which is the UID. That will be my identifier. That will be my key. And then I'll have the tuple as the value. So I'm reshaping the data into key value pairs. Great. Now, we'll take some registration data. Again, further down in the funnel, we've got registrations. And here, again, we've got the log file. We'll take and split it on tab, because it's tab separated. And then we take a look at the collect. Again, just a couple lines, a couple rows. But it's got a similar format. It's got a timestamp, a UID. It's got some other registration info, package ID, latitude, longitude, et cetera. So the thing that these have in common are the UIDs. Those are the keys. So as I reshape the reg data into a key value pair and collect it, you'll see the results down here. Great. So now I've got the clicks as a key value pair, the reg as a key value pair. The keys are common, the UID. So to do a join, it's quite straightforward. We say reg pairs join click pairs. So just take those two RDDs, join them together. And that will take and create another key value pair. You've got the common key, and then the left-hand side and the right-hand side as the values. Let's see that right here. Now, of course, if you're familiar with SQL, there's a number of different flavors of doing a join. In this case, it's a very simple default case of inner join. But there's a number of different calls for joins. There's a rich variety of joins you can do. This is just a very simple case. But I wanted to show how programmatically in functional programming, how a join is accomplished. And this is important to be able to illustrate a shuffle. So the next point here is to say, now if we take a look at the graph, illustrating the graph across the cluster of this data, we've got the click data as a stage. Remember, I talked before about how in MapReduce you would have map, 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 reduce kind of patterns. So we have something similar here. We have map and map before we get to the aggregation. The two maps on the click, those can be composed together. Those can be done in one fell swoop. And so they are an independent unit of work that can be performed. The registrations, similarly, there's map, map there, and that can be done independently. So I can be running both stage 1 and stage 2 clicks and registrations, preparing that data, reshaping it into key values. I can do that in parallel. And so that's what Spark is doing. It's taking the graph and doing the lazy evaluation so they can tell, I can take these two steps and compose them together. That's a nice optimization. Now, what happens then is we've got these two different data sets with key value pairs, keys in common, and we're going to have to do a shuffle to be able to do the join. So that's where you get some network traffic on that shuffle. Because I'd done this in a very default, very naive kind of way, I didn't have any specific information about the keys or how to partition them. If I wanted to do a much more high-performance kind of join, I would have provided that information. But here, by default, you see where the left-hand side is being compared with all the values of the right-hand side for each key. You get all this shuffle traffic. And that's a very important point about understanding Spark. This illustration also tries to show something about caching. It's just really what it's saying there is caching, you try to do caching. There aren't really a lot of guarantees because you have a number of things happening out in the cluster, and you have different RDDs being evicted based on their usage. But if you can get the caching, it's great. Yeah, question.
The cache, is that something you can actually allocate a certain space, or is it like it's always allowed you?
Yeah, no, you could get evictions. There are other ways of being able to externalize an RDD. So one of there's a way here that you can persist off heap, and that way multiple applications can share it. There's something called Tachyon, and there's a company that's based around that, but it also came out of AmpLab. And so effectively, you can think of having like an in-memory distributed file system. It looks like HDFS. HDFS crossed with a RAM disk, basically. But it has those kind of operations. It has path structures, but there are RDDs that have been externalized. And that's a way of being able to have multiple applications share the RDDs. Yeah. Other questions? Yeah?
Will this graph be different if you can't fit everything in memory?
No, it'll be the same graph. The only thing is you could think of having to chunk through the data. So if you can't fit everything in memory, you may have to take a portion of the keys, sorry, a portion of the values for a given key, process them, and then drop in a disk, and bring in another one, process them, drop in a disk. You might have to chunk through the data. If you were doing Hadoop, if you're doing a join on very large data sets in Hadoop, you typically do something called spills, which is chunking through the data. Very much the same process. Does that answer your question?
Yeah, I'm just trying to think if you chunk the data, then when you do the join, you need to see the complete list on both ends
Yeah.
to the join, right?
Yeah.
What if your partial, the piece you want to join is in the memory, but on the other file, the piece that you are looking for is actually in the disk? So how does the join work?
Right. Well, that's complex, but it also leads to some optimization. One of the things you can do with joins is if you know that the left-hand side of the join is, say, very large compared to the right-hand side, there are other flavors of join. You could be doing, for instance, something called a hash join or in-memory join, where you just take the right-hand side and broadcast it out across the cluster. And in that case, what you're talking about then is you could chunk through the left-hand side because it's big. The right-hand side is all in memory. So in that case, a join becomes a map, and it's much more efficient. That's one way to optimize a join, and we'll see some examples of that. There's other flavors of that, too. You can do Bloom filter joins and things like that. So, good question, yes?
Who makes that decision how to optimize the join?
How to optimize the join? Great question. Right now, that's the programmer. Application developer is making that decision. With data frames, there's something called Catalyst that's optimizing and beginning to make that. Now, to really be able to optimize a join, you need to have query stats, table stats.
That's why I was wondering.
Yeah.
I mean, you have to collect those ones, you have to compute them so that
So I mean, we'll see this, but when you run a more complex Spark application, we can drill down into the cluster that you're running on and look at its UI, and it has stats for the different stages. So for each stage, you would have calculated metrics of how effective the caching is, and other types of resources, how they're being used. From that, those are effectively query stats. And so that information can be used for optimizing. Very good point.
And will Spark SQL optimize that?
Well, right now, not. I mean, there is something called Catalyst, which is, we'll go into Spark SQL a little bit later, but one of the reasons for doing Spark SQL as opposed to Hive was Hive has both the logical plan and the physical plan are done at the same time. They're conflated. So it's hard to really optimize. SQL, usually you do a two-pass. So one of the reasons for doing Spark SQL was just to get past the Hive optimization. And so they came up with a new optimizer called Catalyst, which is open source, is being used by their projects. And so the thinking is with data frames, that becomes more and more automated. Okay, other good questions here on this point? Great. All right, I want to, we did that. I want to get to the last coding exercise before we go to lunch, if possible. But first, I need to talk a little bit more about notebooks. So to introduce this part, how to think in notebooks before we do the exercise, I first want to stress about Databricks Cloud. It is Spark. It's open source Spark. We don't make any changes to Spark specifically for this. There's no open core. There is proprietary code in terms of the platform, but that's more about managing the AWS resources. using spot instances and EBS and all of that magic under the hood. There's proprietary code. And that wouldn't really translate outside of AWS. But the Spark part is entirely open source. A few key concepts. I probably should have had this earlier on. But when we talk about Databricks Cloud, everybody here is logged into shards. Those are web apps. You log into the web app. And that's keeping track of your state. It knows about where your login is. It knows what tables you have. It knows about S3 mount points, all these kinds of things. It knows where your notebooks are, basically. The clusters, on the other hand, are ephemeral. You can have more than one cluster per shard. It might be that your team has a bunch of small clusters that individuals use for day-to-day work, and then maybe a large cluster that you would only use part of the time. Maybe the large cluster comes and goes. Sometimes we'll spin up really large clusters to do a machine learning workload and run them for a couple minutes and shut them down. So a big advantage here is that by separating the state between the shard and the clusters can go away, no big deal. You'll have to reload some data, but no big deal. You want the clusters to be ephemeral because, frankly, you don't want to have to be paying for a really large cluster all the time. If you have to do some really big unit of work, get it done, get rid of the cluster. Go back to something smaller. And that's always going to save you money. The notebook, we've talked about notebooks in details, but this is the shared document. There's also another level beyond that, another abstraction called a dashboard. You can take a cell and publish out of a notebook into a dashboard. And you can actually take several of these and compose them together into the same dashboard. And it's like what you would see with BI dashboards. A lot of the visualizations that you want for reporting and the code that's driving it. OK, so we've seen about notebooks, essentially different cells that are a series of commands. They can be Python, Scala, SQL, R being added now too. You can take those cells and reorder them. And that's really great for being able to develop the code that you need to run. You can also export and import. The clusters are attachable, detachable. And in the training shards here, we're actually using slightly smaller 5 GB clusters, which is essentially just a standalone small cluster. But this illustration is what I want to show. So you've got the shard, and you've got multiple people on your team coming in through browsers, logging in. And you can import and export local copies of your source code. We're working out ways to be able to sync the source code with a repository, like Git or GitHub, so that you can do versioning of your notebooks directly into your source code control. The shard has the state, the results of what have been calculated in a notebook, has more than one notebook, and the clusters can be attached or detached. That's a real important point. Now, let me move forward here a little bit. A couple things I should note. Comments on the notebooks are similar to what you'd see with Google Docs, Google Spreadsheets, and whatnot. So it's interesting to be able to have a team working in a notebook. I had an experience a couple months ago where I was preparing a notebook for a course, and I was doing some machine learning examples, and we were having troubles on one of the clusters we were using at the time. So while I was putting together the exercise, I called out to a friend, Shangri, who's one of the leads on MLlib, and I had a problem with an algorithm, so I was working on the code in the top of the notebook. Shangri was down in the middle of the notebook rewriting some of the MLlib parts, and then wrote a unit test to show what he'd done. And meanwhile, the ops people were working further down to troubleshoot a problem they had with the cluster. So we had 3 different teams working simultaneously in one notebook. And we were all in different locations, which is really cool. We see that kind of collaborative nature with notebooks, I think, is a very interesting paradigm change. And I just want to throw a few resources out here. There's feedback and forums, a couple of great resources for learning more about the notebooks as you're interacting with Databricks Cloud. So to get to the coding exercise, I want to talk about thinking, and we'll have an exercise based on this. Anybody run across computational thinking? Anybody out of CMU here? OK. There's this great thing. The chair from CMU, Carnegie Mellon, the chair of computer science was one of the authors of a kind of instructional rubric called computational thinking. Google has adopted this for a lot of their instruction, and Google and CMU have both put together a lot of great instructional resources for like K through 12 and whatnot. The idea is to have computing be like reading, writing, and arithmetic. It's another top-level fundamental skill. And we'll show how to use that here. I also want to make an aside to a contemporary artist, David Hockney, who does snapshots and then stitches them together. It's a little bit like that when you're building notebooks. You build up these cells and you bring them together to get the overall result. So it's a lot like Hockney's art, if you've ever seen that. And I've got a couple links here about computational thinking. The gist of it is you want to have a structured way of taking notes. So you start from a problem statement that's essentially textual, verbal, and from there you iterate until you get to something that's computable. But it's a way of having notes that can be essentially computed by you and by other people on your team. It's a way of going from a thought process into algorithms and being able to get there in a structured way in stages. So computational thinking has 4 parts. One is take a complex problem, decompose it into smaller chunks that you can think of as standalone problems. And then from there, for all of those different smaller problems, apply pattern recognition. There's probably things off the shelf that you can use, parts of an API that can be used for the smaller tasks. And then from there, take a look at how to abstract the different parts up into more of a pipeline, a workflow. So take the individual calls and build a workflow out of it. Take the different cells in a notebook and have a process out of them. And then from there, a higher level of this is what we call algorithm design, be able to go and articulate an overall strategy of why this pipeline achieves a given result. So if you can think about taking notes in this way, you can come out with something computable that can be shared across a team. That's computational thinking. Now, to apply it for notebooks, I'll give Andy Konwinski credit for this, but as we've been working with notebooks, we've tried to come up with like a computing paradigm. How do you think about notebooks? So the first step is create a blank page, a new notebook. Number 2, take the assignment, the problem that you're working on, the description of it, and copy it as markdown in a cell. Number 3, take that and start to decompose into individual cells. Split the markdown into different smaller tasks. And then for each step, begin to apply the Spark API to accomplish those tasks. There are well-known patterns, and we've shown a lot of these already this morning. And then take a look at how can you start to assemble these different parts into a workflow that accomplishes the overall strategy, the overall algorithm, if you will. So to try out this, let's take the last 4 coding exercises that we've seen. So got a couple of files. We've already seen the README file, and then we've got changes.txt. We'll take those 2 files. For each one, create an RDD to filter out for the keyword Spark. Once you've got those RDDs, then for each branch, both the branches do a word count, and we'll come up with key value pairs off of both branches. And then from there, take the key value pairs and do a join. So this will pull together the last 4 coding exercises. And the final thing is just be able to count how many instances of Spark are there in those respective files. So use this as a way to apply the computational thinking for notebooks. Create a notebook, copy this statement here, begin to decompose it, and start to cut and paste from the last code examples to be able to do the individual tasks and pull them together into one workflow. Sound good? Now, as far as time, OK, we've got like 10 or 15 minutes before lunch, which is probably ideal time. Vita, Chris, and I will be around. We'll walk around, help you out with any questions you have. But let's take this as an assignment. I need water. Sound good? Okay. Sound good? Hey. So let me show a quick example. At any point in time, if you're in a notebook, then there will be the last cell that is accepting input. So for instance, I can type something here. I'll say markdown, this is a test. And if I evaluate the markdown, it'll format it. And once I evaluate the last cell, it'll kick me into a new cell. So that's always a way to append a cell at the end of a notebook. The other thing is that when you have multiple cells in a notebook, you can go to the middle. And if you hover over the middle, there'll be a plus sign that pops up. And if you click that, it'll create a new cell. And you can also go over to the right-hand side and delete them if you need to. All right, great, thanks. I'll circle around some more. And what I'll do is pick up on tour. Good. So I don't know, if anybody is joining us, let us know. There's some slides to download for this. But I think that Vita had to take off, and Chris will be back in a moment. He was picking up lunch. But I'll go through a lecture to start off this before we go into the next notebook. I wanted to cover a tour of the Spark API, just a high-level view of what's in the API, different parts. And we've got a couple of notebooks put together, one for the Scala side of this, and the other for the Python side. So if you look under the Spark Camp folder, under 05, there's Scala API, Python API. If you want to follow along, I've got the code cut and pasted into my slides here. So I should show those, though. If you go to Spark Camp, and under here, Python API, if you want to follow along, there's all these different code cells that will have executable code for the examples that I'll show. Okay. So I want to cover in more detail about Spark Context, the driver, the different types of cluster managers, resource managers, if you will. Go into more detail about some of these concepts that we introduced in the first part. Talking about Spark Context, it's an object. It tells Spark how to access a cluster. There's the handle SC that's built into the notebooks. Also, if you're using Spark Shell or using PySpark in the REPLs command line, then the SC handle will also be built in. Otherwise, if you're creating an app, a standalone Spark app, generally one of the first things you do is to use a constructor and create a new instance of Spark Context. And so just some examples here, Scala versus Python, pretty much the same thing. Wherever you're at, you can type SC and evaluate it. It'll show you the object that's been created, and then from there you could access the fields to see what's inside. One of the main fields, of course, is master. And this points to where your cluster resources are. And there's a few different modes for this. If you have master set to local, if you're running Spark Shell just locally on your laptop, master set to local will be just one thread. You could do local star, and it'll take all of the cores in your laptop. And frankly, when I'm developing, a lot of times I'll do that kind of thing. I'll work just off my laptop. In the cloud, when we're working with Databricks Cloud and the notebooks, then we're connected up to what's called Spark Standalone. What that means is Spark itself is managing the cluster resources. And so that's the next line down here. It says Spark : Spark Standalone cluster. This is all going on behind the scenes with Databricks Cloud. Alternatively, you could have it connected to a Mesos cluster, in which case the URL is pointing to either a Mesos master or a Zookeeper quorum for Mesos masters in high availability, or it could be pointing to a Yarn cluster. So there's a lot of different configurations for this, but master keeps the information. Now, before I'd shown a diagram of the driver and the worker nodes. Yes? Yarn cluster. It would be a different URL. I didn't have that listed, but you'll have a URL. Hi, Riza. We got into a different one. Actually, I'll bow out. Okay, thank you though. I appreciate it. Okay. So I don't have an example right there, but there'd be a different kind of URL to show where the resource manager is for that. Yeah. Question.
In terms of running Spark like on a laptop on our desk, right?
Yeah.
I just downloaded the binaries and I was
Yeah.
running PySpark.
Yeah.
And I had the whole thing.
Yeah.
So when do I actually run Spark? Or when?
Well,
when
if you're running PySpark, that is actually running Spark. The only difference there is the master is set to local, or local star probably. And so an interesting thing there is, yes, you can develop your applications and then point it to a cluster. So, question, yes?
Yeah, I didn't quite get that. So when I wrote something, it was set master, set local 4, whatever it was.
Yeah.
Instead of the training or the book. Then actually set the host where the actual Spark is running. So there is const.set host something, and then there is a set master. So can you explain that a little bit more? Like concept of
Yeah.
setting a master and then as a parameter I'm giving local something 4 or something?
Right. Well, local will be the master setting. That actually sounds like two different settings. But local 4 would say use 4 cores, 4 worker threads.
4 worker threads.
Yeah.
But it's not running locally on my machine. It's running still. What does that mean local?
Were you evaluating inside the notebook what the SC master is?
This was connecting from Java to Cassandra where the
Ah.
Spark is running.
Interesting. So that would just be a local mode wherever it's running. I'd have to take a look a little bit more, but you can run in standalone mode. That's not a problem. I've seen some different usages. I mean, you can connect up to a remote cluster. You could embed inside of a web app. There's a lot of different kinds of patterns. Question. I saw some other hands up, I think. Okay, good. All right. So this gives more detail on an earlier diagram. We've got the driver. The driver has the Spark context. That knows how to talk to a master. So there's some type of cluster manager. Some resource manager is the term that Yarn uses. Master, or quorum of masters is what Mesos uses. Out on the worker nodes, a little bit more detail. Each node will have an executive process. And the executive process is really what does the heavy lifting. The executors they manage the cache. They're the ones that receive the graph, and then they're given tasks to run portions of the graph, different stages of the graph. So really, the executors are the main cluster resource. Another point there is that the executors do talk with each other. There's some peer-to-peer communication, and you need that at times, particularly like doing broadcast. You want the worker nodes to talk with each other. So the driver will connect up to a cluster manager and get resources allocated across, and then apply those. Sorry. And it'll run executors out on those resources. And the executors are, again, doing the heavy lifting, running the tasks, caching the data. The driver will serialize the graph out, the application code out to the executors, and then it will send tasks out for the executors to run. Now, to look at RDDs in a bit more detail, RDD stands for Resilient Distributed Dataset, and it's the main abstraction. Most all of the API is working with RDDs. There's a few other cases of things we'll talk about, broadcast variables and accumulators. But most of it is RDDs. There are two ways to create an RDD. One is to take a collection that's already native in the language and call parallelize. So we saw this with a Python list to parallelize it to create an RDD. That could be useful for doing something like, say, a Monte Carlo simulation. But generally speaking, a lot of what we see is where RDDs are being created out of some data set that's in a storage framework, such as HDFS or Cassandra or wherever. So data at rest in some external storage. And typically you can use the Hadoop connectors for this, or there may be other types of connectors. More recent versions of Spark SQL have a very flexible, very general way of creating new connectors. Now, the types of operations that can be performed on RDDs. Number one, there's transformations. Number two, there's actions. The transformations are lazy, so the compute doesn't happen right away. The actions are when the computation goes into effect. And then a third thing, number three, persistence. RDDs can be persisted into storage on memory or disk or some combination. Just an example here of parallelize. As far as building up RDDs, I just want to reinforce that Spark knows a lot of different formats. You can be taking data from HDFS, S3, Hypertable, HBase, Cassandra, etc., local file system. It could be flat files, it could be globs, it could be sequence files, JSON, Parquet, a lot of different serialization formats. Okay. The transformations are lazy. Yes? There's definitely Avro support. I was trying to think if it's native in there, but I've seen a lot of companies using Avro, yes. We'll look later, but there's a collection of different third-party contributions called Spark Packages, sparkpackages.org. And I believe there's Avro support on that. Good point. As far as transformations, we've seen some of these before. We saw a map and a filter and a flat map. Another thing you can do is a sample, either with or without replacement. But that's interesting to be able to sample from an RDD. A very powerful construct is union. If you have a number of different RDDs that have the same schema, you can take a union across them to create one RDD. And this is very useful in a couple ways. For instance, in streaming, you might have data coming in on different receivers. So you've parallelized the real-time ingest of data. You could take the union across those D streams and be able to get one RDD to apply your business logic to. Another case would be, again, in streaming, say that you had data rolled up from different time periods, and some of it was cached in memory, but more historical data is maybe stored out on HDFS. You could take and do a union across some time window and then have one RDD that represents that whole window. So maybe you have 5-minute increments in memory for the last 12 hours, but then the last 5 years you have on disk. You can take a time window across that, take a union, and that's a way of being able to blend real-time and batch. So if you've heard the term lambda architecture, it definitely would be leveraging a union. I have mixed feelings about terminology lambda architecture. We can talk about that offline. Distinct is another type of transformation if you want to find just the unique elements. But then a lot of what we do with transformations has to do with key value pairs, working with pair RDDs. So these are typical types of transformations on keys. Reduced by key, we saw that with word count. And reduced by key and group by key are similar in terms of what they accomplish. Generally speaking, you want to use reduced by key. Group by key, the name is familiar in terms of group by is in SQL, or a similar construct in PIG, say. But group by key has some memory constraints. Group by key is basically saying, for every key, create an iterator for all of its values. Now, if there are too many values to fit on one machine, you'll run out of memory, you'll get an out-of-memory exception. Whereas reduced by key can be parallelized. We saw using it with the monoid earlier, and generally speaking, when you're doing these kinds of aggregation, you want to use reduced by key. Any questions about that? Sort by key, also kind of similar. I don't have an example of that. But join and cogroup. Join is actually a cogroup under the hood. A cogroup says for each key, get both the left-hand side and the right-hand side values together, and then apply some sort of operation to them. And there's a lot of flavors of join. Cartesian would be a way of doing a cross product. That comes in pretty handy for a lot of algorithms. There's a number of other transformations. This is just a sample of them, but the typical ones. Any questions about that? Yes?
The number of tasks is the number of parallel
Ah, interesting. Well, no, I mean, that can definitely be different. You could have over-provisioned where you have more workers than tasks that are needed, but some sort of multi-tenancy of different apps. Or you could go the other direction, probably more typical, where you would have more tasks than you do have workers, and they just basically, it's like slots are used in MapReduce. So basically, you have some number of workers, and they'll get sent tasks to them until they complete all the tasks.
So why would somebody need to specify this? I mean, it's like, wouldn't Spark take care of these pipelines?
You may want to have programmatic control over the number of partitions. So numtask will, so you may want to split it up very explicitly into a certain number. There may be algorithmic reasons for doing this. So I was trying to think of a good example off the top of my head, but definitely simulations work. I could see some ways of doing this. Other questions? Sorry. I have to get adjusted to the lights here. All right. We've seen this with the earlier log example, transformations. We talked about closures. So basically, whatever business logic is inside of the function call, that's called a closure. That's what's being serialized out in the graph. And actions. So we've seen a number of these already. Actions are when the graph gets evaluated. So we saw collect, we saw count, and take. You could also do take sample with or without replacement. An alias for take one is first. So you use the takes basically to examine what's in an RDD. It's a good debugging effort. Collect will grab the entire result set and drop it down into your console or into your output cell. Reduce is interesting. Reduce is a kind of aggregation, and it will require a commutative associative monoid. There's some algebra requirements for what kind of function can go into a reduce. But again, that's so you can do the reduces, the aggregation, in parallel. Now, typically when you're working with actions and you've got some large-scale aggregation, you probably don't want to drop it down to your console or drop it into your cell. Instead, you want to be able to do some sort of save in parallel. So save as text file, save as sequence file for Hadoop format. You can also do save as JSON, save as Parquet, et cetera, all these different formats. That will allow you to do the storage in parallel, which is a more typical pattern. For each down the bottom, that's a very interesting one. For each is going to iterate through an RDD, iterate through all the elements as they're out in the cluster, perform some logic, and then bring the results down. So that's a good way if you want to take and create a report, say, where you iterate through all the final results of an RDD and then pretty print them or something. OK, so just some examples here of doing actions, doing collect, doing a for each. Now, as far as persistence, let's shift a little bit to the caching. There's a lot more detail, actually, if you look at the programming guide. I'll point to that. Definitely, well, I'll go through this in a bit more detail. But there's some pretty good notes here, tech notes, as far as how to use this. The main thing is, when we used cache before, when we saw the earlier example of log files, and I had cache, cache is an alias for persist memory only. And so what that's going to do is store an RDD as deserialized job objects. If it doesn't fit in memory, whatever partitions are not cached, they will be recomputed on the fly when they're needed. And if the transformations that you're doing are relatively simple, recomputing makes a lot of sense. If you've got a very complex graph and you've got some machine learning algorithm upstream or some large-scale join, something that's expensive, you probably don't want to recompute that if you lose a node. So that's another thing to think about when you're designing an app. Once you get past a very expensive operation, probably want to cache it. You can think of it almost as if it were checkpointing. Now, an alternative to this would be to do memory in disk, which says that store as deserialized Java objects if it doesn't fit in memory. and spill them to local disk. This is much more like how you would do a large-scale join in Hadoop, where you're chunking through the data, spilling to disk. Yes, question? Invalidate cache. Excellent. So what you can uncache, you can unpersist if you want to force some eviction. So you're using some RDD for a portion of the workflow, and then you get into another portion where you want to have different RDDs cached. So you can control that programmatically. Does that answer? Question?
If you persist it on the disk, can the underlying data source get removed? Would the
Ooh.
RDD still stay? Like
That-
can I publish the RDD out and get rid of the underlying data source?
Well, ostensibly, yes. I mean, it is a problem in the sense that if you were to lose a node and have to go back in the graph all the way back to the endpoint, to the base RDD, if the underlying data storage is changing, like if that was deleted, that would be a problem. But if you had persisted at an intermediate point, then yes, you wouldn't need to go back all that far. That gets interesting if you have a storage framework underneath that's changing. So for instance, if you have log file ingest directly into Cassandra, and then you pull some data out, maybe you lose a node, you go back and get that partition, it may have changed. So that's something to consider as well. Other questions about that? Now, some other forms here. You could do memory-only serialized. So it's a trade-off between CPU and memory, whether you deserialize or serialize the objects. Keeping in mind that a deserialized string, for instance, in JVM, is going to take up a lot more memory in JVM than it does on disk. So if you have 100 gigs of text in disk, it's going to be a lot more than 100 gigs once it gets into memory. And so memory-only serialization, memory and disk serialization. If you want to, you could force it all to disk, which is, of course, the default in Hadoop by doing disk only. You can also do replication. We don't see a lot of use cases for this except for streaming. So when we have a streaming app, when the data first comes in onto the receiver, then we take and do a two-way replication in memory. And the thinking there is you're holding the hot potato. If you lose that partition that has the data that's just come in off the receiver, there's no way to get it back usually. So we want to replicate to make sure that we have some better fault tolerance. But otherwise, I don't see that pattern quite as much. Another one that's experimental is to take the RDDs and serialize them off heap. So this is a way that could be used with, say, Tachyon, being able to take the data or take the RDD and expose it. That way, more than one application can consume it. So this is another thing to think about. When you're working with RDDs, you can only access the RDD within that Spark context, only within that application, that Spark context. So if you have multiple applications that you want to share the data across, how do you do that? And off heap is one way, as opposed to writing it out to storage. All right, any questions about this? Other questions? Okay. Clear as mud. Moving right forward. Broadcast variables. Okay, this is fun. If you've worked with, say, a distributed cache in Hadoop, there's this notion of having data that you want to use in your workflow that's out of band. Say, for instance, you've got a machine learning model that you've created for anti-fraud scoring. You might create that model offline and then put it in a distributed cache in Hadoop, and then you can do your scoring at scale reusing this model. Broadcast is a similar kind of idea in Spark. We can take any object and broadcast a read-only version of it out across the workers in the cluster. So again, if you had some sort of machine learning model, that might be a really good usage. Maybe there's a lookup table for some type of transform that needs to happen. Different types of things, data that you want to reuse a number of times, but it wouldn't make sense to propagate it through the pipeline. Something out of band. So broadcast variables can be really whatever type of variable that you can take and serialize out. Also, the different nodes, the worker nodes, can do some peer-to-peer communication. So there's fairly efficient broadcast algorithm. And so as an example of this, I will take, and here we say sc.broadcast, and then whatever type of data is inside of broadcast, that will be referenced by a new variable, broadcast var. And anytime we want to access it, we just say broadcast var.value. That'll bring back the read-only copy. Another thing you could do with this would be like a hash join or some more complex type of join. You could take the right-hand side, the relatively small side of a hash join, and broadcast it. And then a large-scale join would just be a map. So that's a great way to reduce cost. Any questions about that? OK. Accumulators. So accumulators are, if you've worked with Hadoop before, accumulators would be comparable with doing a counter. The idea of an accumulator is you've got some type of value that you can apply an associative operation to, like an addition, and it can be parallelized. So you can have partial aggregates out across the cluster, but then bring them all back down to the driver. So this is really great to be able to do things like counters. And again, it's more out of band. It might be that you're looking through hundreds of millions of customer records, hoping that you have hundreds of millions of customers. Hundreds of millions of customer records, and it might be that less than 1% of the customer records are corrupted, the profiles are corrupted. So when you do hit that kind of edge case, maybe you want to count them or keep a list of what the customer IDs are so that that can be sent off to customer support after the workflow completes. So those would be really good applications for using an accumulator. It might be that you're collecting some sort of metrics about an algorithm, how efficiently it's performing. You might want to keep some counts. This could be good for, again, measuring or debugging some type of algorithm. And it could be also that it just works into the algorithm itself. There could be, certainly in machine learning, there's some great uses for accumulators. By default, these are numeric values, but you can override that. You can put whatever type of data value you want, as long as there are associative operations defined for it. Now, an important thing is that accumulators can be written, updated on the worker side. They can only be read on the driver side. If you try to read them on the worker side, it'll throw an exception. Again, because it's just partials. It's not the full value. So if I wanted to run this then, down here under the Python part, I've got an accumulator specified by saying sc.accumulator 0 as its initial value. And then I'm going to create an RDD of numbers 1 to 4. And then down, I've got a function defined to access the accumulator. What I do is I say RDD for each, apply that function, basically add the numbers together, 1 through 4, and then print out what the value is. Accumulator.value totals up to 10. Again, these are data abstractions that are not RDDs. So it's the two cases outside of RDDs for other distributed data in Spark. Okay. I should probably actually have a line there. If I really wanted to be a Pythonista, I would do it like that. But yeah, global is a keyword in Python. And so the idea is that we're accessing some other variable outside of scope of that function. But probably an even better way to illustrate it is in the Scala, where we just have this value defined, accum, and then do a for each on it. So, other questions about that?
You mentioned that this is not done in an RDD.
Right.
But the parallelize creates an RDD, right?
Well, we're using RDDs here, definitely. But the accumulators themselves are not. They're not parts of RDDs. Yeah. So accumulators and broadcast variables are the two cases outside of RDDs. Yes?
Broadcast variable holds a large amount of data.
Yes.
Can we cache it or put it at disk?
Oh, interesting. No, I don't know of any semantics to be able to manage that. If it's a really large amount of data, you probably better off of thinking of it as some sort of service or something external to Spark. I'm trying to think of some good examples. I've done a lot of text analytics, natural language processing, and there's times when you have resources, like if you're using WordNet, you could have some pretty substantial resources required that you don't want to take and distribute in ways across a cluster. So you might want to have just sort of a singleton pattern and think of it more in terms of like microservice. Definitely in natural language processing, we run into that a lot. So it may or may not fit broadcast because you will be chewing up the memory that's allocated to Spark.
If you do have, say, common set of data that is needed by
All of them, yeah.
how do we, I was thinking broadcast might be a great way.
Yeah, no, well, yeah, and if that works with the resources, that is a great way to go. I would say that, at some point there's diminishing returns. If it gets too large, there may be a better way to handle it. We can talk about that offline. I've got some examples, some code repos for that, especially in natural language, where you kind of hit a breaking point where, you have tens of gigabytes of data and hundreds of gigabytes of metadata, effectively. So you can definitely get upside down. Okay, one thing I will point to is Matei had a really great talk from a few years back about using broadcast variables and accumulators. And I think that some of the design patterns he covers there are really useful to look through. I'm not going to go into too much detail, but that's a good talk. Alrighty. One other point is key value pairs. A lot of what we do, particularly for joins and different types of aggregation, require key value pairs. So we saw that with word count in the exercise this morning. In Python, key value pair is just a tuple or a list. It works out. The semantics of this are very convenient. In Scala, it's using something called tuple2. And so whereas generally we think of this as being zero-based index, tuple2 comes out of, I believe it comes out of Java. It's ones-based. So the left-hand side of a key value pair is going to be _1, dot_1. The right-hand side will be dot_2. If you have a wider tuple in Scala, it'll continue on dot_3, 4, 5, 6, 7, 8, 9. So it's a little bit weird because I usually think of Scala being all zeros indexed, but this is one time when it's not. Any questions about that? Right. So really the definitive docs then, if you go to Python API, this is going to be a little jammed up, but let me drop it down. There's great API here, and let me pull up an example. Python SQL, Python subpackage. There's a lot of good code inside of here. So for instance, yeah, there's some source code. Actually, a lot of the examples that I had in these slides came out of the docs. Looking at either the Python side or the Scala side, there's some great source code in there. By the way, that looks awfully fuzzy, and I don't think it's just my glasses. Is that readable? It's not readable. OK, let me see if this thing is. Goodness. Let's say that's a little bit better, but let me boost the point size. Is that at least more readable? Yeah. We can deal with a better projector here. OK. But if you check this in the browser, it'll be a lot easier to look locally. Alrighty, we've been through lunch, and we wanted to have an Ask Us Anything right after lunch, but the timing of the tutorials upstairs were different. So they were actually kind of running late, and we'll schedule that after the break in the afternoon. I wanted to move forward into Spark SQL. So we're right. OK, great. Half hour up. So Spark SQL has become a real workhorse. And it's a fairly newer part of Spark that was introduced, but it's become part and parcel of it. Yes?
Yeah, like before going to Spark SQL, do you have any slides which tells the architecture of Spark?
Architecture of Spark. Interesting. I don't have a lot of slides about that beyond what I'd shown with like worker cluster manager and executor, driver, that kind of thing. I don't dig into a lot of details, but inside of the Spark docs, there will be more. So if I go back here, actually, one of the better resources is if I go to spark.apache.org. If you look under documentation, latest release, and then inside the programming guides, there's the Spark programming guide. It'll get a bit more into some details of the architecture, along with some sample code. It's in a bit more detail. Realistically, though, if you want to look at the architecture, definitely, Matei and Patrick Wendell and others have done some great talks in much more detail. And all of the talks that we do, like for instance, the Bay Area meetup is pretty popular. We archive all that material. There's a YouTube channel for Apache Spark that has a lot of that material on it. The other thing, too, is there's a DevOps advanced tutorial that goes into much more detail about architecture. There's some complexities. Certainly, working with Python and Spark is interesting because you're having JVM executors talk with the Python process. So architecturally, there's some pretty interesting issues there to cover. Does that cover some?
Yeah, if it's not good.
Yeah. We're not going to get into that much detail, though, but I think that definitely off of the Apache Spark channel is probably a better resource for that. So in particular, there was a talk earlier this year, early part of this year, by Patrick Wendell that was called Where Spark is Going in 2015, and really went into more of the roadmap on the architecture and different changes. And in particular, a lot of that had to do with new things going on with Spark SQL, as well as integration of R. That architecturally gets pretty interesting too, partly because of licensing, but that's a good one. Okay. Let's see here. Alrighty, for SQL, SQL's become a real workhorse. So the thing about SQL is that you have this way of crossing back and forth between a relational table and an RDD, and pretty much a one-for-one transformation between them if you can overlay some schema on top of the RDD. So that gets interesting because now we can take and define an RDD as a table, use it inside of a SQL query as part of the from clause, but then the result set coming out of the query is also an RDD. So this is a way of being able to chain back and forth between something that you're doing in SQL versus functional programming transformations to it. Real powerful metaphor, especially if you're doing ETL. It's generally speaking, you can write less code but perform much more work in SQL. But then downstream from that, after you've performed your ETL to get your data prepared, maybe you want to do some kind of machine learning work. It's going to be a lot easier to do that on the functional programming side. So we like this idea of being able to intermix functional programming with SQL commands. And formally speaking, SQL is a functional programming language. I mean, aside from the relational engines for databases, SQL itself is a declarative functional programming language. I've got a few different deep dive sources on this. Actually, what's coming for Spark in 2015? Patrick Wendell, that's the YouTube talk that I was referencing. Gets into more of the architectural issues. Michael Armbrust is the lead on Spark SQL, and he hopefully will be visiting us after break. He's upstairs right now. But he had a great talk from, a blog post earlier, about a year ago, talking about the directions for Spark SQL. There's been a lot of updates for that as well. The SQL optimizer, we were talking about Catalyst and how queries are optimized, and Michael has a good video about that. And as well, there was a great talk from Renal Shin, Michael, and Davies Liu talking about data frames, which is this new abstraction on top of RDDs that allows for much better SQL optimization. So the blog post and the video from data frames also has some great detail. Yes. So data frames is in Spark 1.3. Spark SQL was introduced, I believe, back in 09. Well, I mean, it was around earlier, but it's definitely been there for a while, before the 1.0 release.
Do you know if there's support for Java? Like to run these Spark SQLs from your Java program?
Oh, yes, yes, definitely, definitely. So you can...
Can you talk about the difference between BlinkDB and Spark SQL?
Yes. Certainly, I covered that. So as far as Java, you have programmatic access. Pretty much whatever you can do with Scala, you could do with Java. And so it may be more syntax. Definitely, when I look at them side by side, Java 7 and earlier, you won't be able to do the anonymous functions or Lambda expressions. So there's definitely more syntax. You don't have the type safety and some other things. But yeah, whatever you're doing with, say, Spark SQL, you can run out of Java. And we'll go into a little bit more detail about programmatic access. To answer the other question, though, there is something called BlinkDB, and Samir Agrawal was one of the leads on that. And he, now an engineer, is actually one of the engineers putting together the clusters for this class. The idea of BlinkDB is it's a layer on top of SQL, and it's a way of doing approximate queries. So there's a few notions for approximate queries. Some of this goes back 30 years or so. I have a friend at HP who's a SQL expert and did some of this for his PhD back in the late 70s. So the ideas have been around for a while, but having them in open source, this is relatively new. And the thing is that you can do approximation algorithms, sketch algorithms, and get approximated results. You can also do things like bootstrap aggregation to help approximate results. But with BlinkDB, the main concept is trading off query time by putting error bounds on what you're measuring. So if you're doing some type of large aggregation in a SQL query to be able to get some kind of metric, like an average, if you can trade off 4% plus or minus, you might be able to cut down the amount of query time by a couple, 3 orders of magnitude. And so we do see this with a large class of queries. You can really drastically cut down the resources needed, either the memory required or the compute time, by doing that trade-off of approximating, putting error bounds on what you need. And frankly, from a data science perspective, most of the big data queries you're doing anyway, you want to put error bounds on them. So it's kind of like killing 2 birds with 1 stone. There are some things where you need exact counts. Doing distinct, that's not going to work with an approximate query. So it doesn't work for everything. But for a lot of large-scale queries, especially doing dashboards and just day-over-day reporting, things like that, it can really drastically change the turnaround time on queries. Again, that's resources for that. Samir is now engineer at Databricks and working on this. But if you do want to look, BlinkDB, there we go, blinkdb.org. No, they're different layers. I mean, the evolution of BlinkDB will be on top of Spark SQL. And so the idea is, Spark SQL is really more about talking about these big data abstractions in SQL. When you're optimizing SQL, you've got, again, the physical plan and a logical plan up above, and you have to optimize both. Spark and RDDs are very much the physical plan. But then the optimizations you apply, that can be the logical plan. Push down predicates out to the edge, things like that. So when you take a look at using Spark SQL with, say, Parquet, you can get some really nice benefits by optimizing. When you have data frames up on top, then you can have a real great convenience of being able to apply a simple transform, something easy to understand, very little bit of code, but a lot of heavy lifting under the hood. Now, the next layer up above that is to be able to do some type of approximation algorithms. So BlinkDB would be a layer up above data frames. Certainly. It's really interesting because it does require more sophistication in terms of query stats, keeping some data around about the queries. Because otherwise, that's That's part of how the bagging is working, the bootstrap aggregation. So it kind of begs the question of how does Spark SQL evolve? And where can you really collect a lot of those stats? So I think in some ways, BlinkDB could be a real driver for that. Yeah. Good question. Other, yeah.
Join data frames with RDBs? Or?
Well, no, data frames are up above RDDs. So the idea is that a data frame is a little bit higher level abstraction. You can always get the RDD out from underneath it. But then, yes, you could do joins across.
On that topic, can you talk a little bit more about the difference between a schema RDD versus a data frame?
Ah, good, yeah. So, well, we'll come in here in a second and take a look at schema RDDs. The short answer, though, is that data frame is an evolution of schema RDD. It's a schema RDD++, basically. Schema RDD is what we're doing right now for the heavy lifting for workflows in Spark. But after 1.3, then data frames really takes over for that. And so there's some benefits of that, is that number one, we can be much smarter about serialization. The data frame has more metadata, and so serialization can be much more efficient. And much more room for doing more automated kinds of optimization, basically. Good questions. Let's see here. I mentioned about Parquet. Before I get into some of the examples, how many folks have used Parquet before? OK, cool. Question?
Yeah.
Okay.
So I'm a little confused on what data source are we using Spark SQL.
What?
I mean, I'm using Spark SQL, but what am I querying from?
Ah, interesting. OK. So with Spark, Spark is really the computation layer, right? It's the elastic compute. Whereas with databases, typically there's, you've got the storage and the management of data at rest, ostensibly. But then you've also got this compute aspect to it as far as the queries. So databases usually have both those notions. Spark is just the compute part. But it also federates to some extent, because you can come and bring together data from a number of sources and be able to do some queries across them. So the idea there is for Spark to be able to define the pipelines, but then also be fairly smart about pushing predicates out. So I believe it was introduced in 1.1, but part of Spark SQL has a fairly general purpose connector, where with just a few lines of code, you can start to define, for instance, filter scans. So I can take logic out of my query in Spark, and if I have the right connector defined, I can push that down into the framework. So then maybe I can, whatever type of framework is underneath, if it understands, for instance, how to do a filter scan, I can do that out at the edge before it ever gets deserialized up into the workflow. So the separation line there is how can I connect in an intelligent way to these different frameworks, and then take and factor the business logic through in optimization. Does that answer?
No. If I'm writing select star from a table, where does that table reside?
Well, the data itself at rest is going to be out. I mean, it depends what type of connector. If it was hitting a flat file, and then you basically created an RDD with a base RDD pointing to some flat file, and you define some schema over the top, and then created a schema RDD out of it, then yes, you could do select star against that. The data would be wherever it was living on disk. So it's going to be brought up lifted into memory, and then you do your processing in memory. But alternatively, if you had a framework that understood how to push predicates down, like Parquet, for instance, can take, and we can do code generation, push predicates down into it, so that it can just deserialize whatever fields you need, but no more. So for instance, there, the data is down there inside of Parquet. We're only going to deserialize the portions that we actually need up into memory. So it really kind of depends where the base data is.
And can I hook it up with the Hive?
Hive. So that's actually where we're leading to here. Very good point. The reason for having Spark SQL was because of Hive being very popular. And so there had been a previous project called Shark. And the idea was to do Hive on Spark. There's actually another one of those now. But the idea was to take Hive and instead of generating MapReduce jobs in Hadoop, instead generate Spark jobs. And so we replaced the backend with Spark. And so that was something called Shark, but Spark SQL has completely subsumed that.
And right, getting to that point, because a lot of organizations already have
Right, yeah.
And they are already using Hive
Right.
intensely. So you can hook this up with Hive, and then you would use Spark as your data processing engine.
Right. So the thing there is that you can reuse the tables. You can reuse the Hive metastore, and basically create a context, a special Spark SQL context that's Hive context, and point to the metastore, and then from there run HQL. So it's pretty much a one-for-one replacement. The only edge cases where you get into trouble would be there are certain types of like user-defined tables and whatnot. Most of the UDFs are handled, but there are some edge cases that aren't yet. But if there are ones that are important, Michael wants to know all about that. So, what are the priorities to fix? But yeah, it's pretty much one-for-one replacement with Hive at this point. Question?
So you mentioned the Spark is just a computational layer, but there is a way you specify how you want to process the data aggregation. So can you advise using that persistence layer as a storage?
It's possible, but it's not. It's not really the kind of system of record storage that we would be familiar with in terms of databases. When we talk about persistence in Spark, that really is about the intermediate data.
Still within that context.
Yeah, still within the context. So it isn't definitely not system of record. There are some blurred areas, some gray areas on this. One is when you do streaming, and there's a way of actually doing updates in memory when you're streaming to avoid garbage collection and just make the process faster. There's something update state by key. And at that point, you actually are using Spark and its memory persistence as a kind of key value store. And there's ways to persist it as well, doing write behinds effectively. So there are some gray areas, but generally speaking, it's just the compute. That's a good point, though. Other questions about that? Yes?
Currently, Spark SQL is a subset of SQL, less so than Hive. Are there plans to expand SQL support further so that this could be a real replacement
Right.
for something like Tableau?
Right. No, that's a great point. It's a little bit more than what HQL has. It's a little closer to ANSI 92. Not quite, though. But that is the goal, is to move it out into more of an ANSI compliant. 92 being the goal, not 99 or later. So I would have to find out from Michael where the current roadmap is for that. But yes, we're trying to handle more SQL. And we have been working with other vendors. I know MicroStrategy was one of the early ones where they came in and wanted to plug in and be able to do queries. So some of the BI frameworks are starting to use this. With Tableau, I forget the firm that implemented it, but there was an ODBC connector for Tableau then. So it's true. It's not going to be enterprise ANSI SQL that you would see out of Oracle or so. But we're trying to move from Hive toward that. Does that answer? Okay, great. Question?
Spark SQL, like how compliant is it?
How compliant? I don't have any sort of a comparison table on that. I'm going to try to get Michael in here a little bit after break and just put him up on stage for a lot of questions, because this is really a very, very much a cornerstone for Spark moving forward, enterprise adoption. I don't know if he has any comparison tables or not for that, but he could probably field most of the questions. Okay. Yes?
Hive-related question. What is the roadmap for supporting OR?
For supporting? Oh. So, yeah, and I know there's been discussion. I don't have any time about org. I will definitely try to get Michael here. I saw a number of people answer about that question, so it sounds like there's a lot of interest on it. Yeah. I don't have that directly. Parquet we covered a bit. It handles column store. And the nice thing about Parquet is that there is a lot of compression built into it. Also some smarts as far as deserializing, deflating, or inflating the data. I've got a link here from Julian in the Dem as far as a good presentation about Parquet if you want to check it out. It's become somewhat of a best practice working with Spark. Complex workflows, you typically want to do your processing, get your data in shape, save it as a Parquet file, and then consume that downstream. OK, so as far as demos go, there's a notebook here under Spark Camp Demos SQL. If you want to clone that, I'll just go ahead and run it. Let me close down a little bit here. So I've got demo SQL visualization. OK. Let me attach this. OK. So to show an example of how Spark SQL works, I've created an array of data. This is actually Scala, but it's very similar in Python. I've created an array here of people data. So each element has a name and an age, and just an array. And in Scala, I'm going to define a case class. There's another way to do this in Python with a row object. But effectively, we're going to create some sort of some object definition to overlay on top of a flat file or on top of some data collection to be able to overlay schema. So here, I've created an object where we have the two fields defined, both the name and the type for the field. And so down here, I'm going to create an RDD by saying parallelize on people data, the array. And then I'm going to map, and for each element, I'm going to instantiate one of those objects. At that point, I've got very well-defined schema for that RDD. So the next step is I could take and register it as a temp table so the catalog knows about it. I'll say, take the RDD and apply register temp table, give it a name, and then I can use that name in the from clause to be able to query against it. So running these, OK. And so now at this point, if I go to query, I can select name from people where age is greater than or equal to 13, less than or equal to 19, and just filter out who the teenagers are. When I run that, again, nothing happens right away. There's lazy evaluation. But it prints out the graph of what will be computed. That's effectively the query plan, physical plan for the query. So you can see that down at the bottom.
How is SQL connected to the Spark context?
Interesting. Let me scroll up here a bit. So far up here, we were just using Spark context. And now another thing that's built into the notebooks is something called SQL context. It basically subclasses that. And this is part of the magic with Scala. But if you're familiar with Scala and implicits, by doing an import of the SQL context, there's implicits. So there's new behaviors that are added to the RDDs. Effectively, automagically, the RDDs turn into schema RDDs. So when we were up here, we were working with Spark context, and then we shifted down here, and implicitly, we're working with SQL context. SQL context being a wrapper for it is really the short answer. And there's a few ways to issue that query. I could, alternatively, I'll show examples of this. I could just go ahead and use %SQL inside of a cell, a code cell. Or I can do this programmatically through the context.
What does the register temp table do? Does it
This one right here.
just creates a temp table and then
Oh, no, it actually doesn't create a table. So the name is a little confusing there. Or it could have a better name, I should say. What it does is to tell the catalog that if I want to create a SQL query, I can use that in the from clause. So now I've given a name that I can query against. Realistically, nothing has happened as far as memory management because of the lazy evaluation. Until you actually go and, even after you perform the query, you don't get the results. I would have to do a collect or some other type of action on the query before all of this gets evaluated. And it'll go all the way back to the base RDD.
nothing gets persisted anywhere to disk or to any database or nothing. It's just the internal, as long as
Right, exactly. So you've got, again, you've got the logical plan coming from the query, parsing the query. You've got the logical plan of the query. And then you've got the RDDs and the functional programming, the transformations and actions that will happen, well, transformations in this case, that are the physical plan. And you can see that broken out down here. If I do an explain on that, it would give it even more. OK, and I go to run this. I could, well, here, let me try this. Just in a simple case, I could say teenagers dot collect. And that'll print out the results. It'll just be an array. There were 3 people in this array. One of them was a teenager, Justin. So by using collect, and then I'm using an action, the whole graph gets evaluated. Alternatively, what I could do is the results of SQL queries are schema RDDs. As I mentioned before, you go back and forth between tables and RDDs. But the results are schema RDDs, and there are some special things you can do with them. If you're working in Databricks Cloud, in the notebooks here, one of the things you can do is use display. And once you display, you can get a table format like this. Or I could take and convert it into, let's see, how about a bar chart? Wow, and for whatever reason, OK. Whatever reason, I need to refresh this. Run all. Wow, interesting. Cannot read property map of null. Interesting. I have no idea. I've never seen this one before. Hey, let me go back to my bar. I don't have any nulls in there. I'm going to chalk that one up to a possible bug. Is that a bug?
If you click plot options, yeah, actually just found this. Yeah, click that, click apply. Click the apply.
Oh, really? Ah, brilliant. Oh, gotcha. It didn't understand when it imported. OK, thank you. My apologies for the bug there. Thank you, Chris. Got to work around. What I was trying to show, though, is if I've got a schema RDD, I can call this display in the notebook context and be able to get some type of, let's see here. Let's get a bar chart. There we go. So I can start to do some visualizations off that, and that's built in. Alternatively, I can also just put the raw SQL in there by doing %SQL and then whatever the query language is. And that has the same problem. Let me fix this. So if I do plot options and apply, great. Same thing, basically. Yes?
So given that's just an RDB or any fiddle, are you able to do updates or inserts?
No. So the notion of an RDD, well, short answer is no. RDDs are supposed to be immutable data. Now, there's a couple cases where that's not quite true. There could be, for instance, the base data could be pointing back to some other type of external storage that's changing. So if you lose a partition, you refresh it, you might get different data. So it's not exactly immutable, but generally speaking. So in that case, then, no, you would not be able to do inserts. However, in terms of Spark SQL and Hive support, actually, Chris might be able to speak to this better. There are ways of doing like deletes and inserts against a table, correct?
Yeah, those are experimental right now.
Yeah.
Yeah, the intelligent data sources like the algorithm and CSV.
So still trying to get better parity there, but still experimental. OK, Parquet serialization. I want to show, OK, for instance, here I've created a string just to define a path. So /temp test Parquet files. And I'm going to use a special function, special library called dbutils. And under that, if you look up inside of Databricks guide, there's a reference section there about this library dbutils. But it's just inside of the notebooks. I'm going to say that for this shared file system, dbutils.fs.remove path. Just make sure that that's clear. One of the things about the Hadoop input-output connectors is, well, the output connectors, is that if a file already exists and they try to write it, they'll throw an exception. So you have to clear out the path first before you try to write. So here, I'm just going to make sure that path is gone, and I'll do save as Parquet file. And so I'll take this data here and save it out as Parquet. And I wrap this in a try-catch. When I run that, okay, so I've written some Parquet files, and now let me take a look at what's under there. I'll display that. And you see under this path, I've got the two parts. I've got part R1, part R2. They'll be compressed, so I can't really show what they are. But then I've also got the metadata. So that's interesting about Parquet is that it will save the schema at that point. Whatever schema is associated with that schema RDD, that will be serialized out. So it's a nice way of preserving the schema and the data at the same time. Now, once I've got that written, then let's go ahead and load that back in. So in this case, I'm going to use the built-in handle SQL context. If you weren't inside of the notebook doing a standalone app instead, you could just create a SQL context by wrapping Spark context. But it's already built in. So here I'm going to say SQL context Parquet file. I'll read in what I just written, and I'll create a new RDD. And then from there, say register temp table, slightly different name. Again, that creates a graph. Nothing really executes. Down here, at any point with a schema RDD, I can say print schema, and it'll print out what it understands as a schema at that point. That's really nice too, because you can take these cells and move them. So if you've got some complex type of table and you want to keep track of what all the field names are and the types, you can just have a cell that does a print schema. And what I find myself doing is just scooting this down further and further as I'm writing code. Okay, now if I want to take and use this Parquet file that I just brought in, I could run a query against it. So select name from Parquet file, ages between 13 and 19, and then I'll collect that and print out the results. And you see the output that it had there. It's printing out Justin. So effectively the same query, but I do have this data serialized as Parquet. All right, any questions about that? Okay, good. Okay, let's try another one. I also want to refer out to the Databricks guide. So if you take a look at Databricks guide, let's see, whoops, go back here. Databricks guide will be a little bit further down. Where do I have this thing? There we go. Under Databricks guide, in particular, taking a look at importing data and Databricks file system. Importing data will have a bit more about how to do Hive integration right here as far as working with external tables. And also working with JSON. Different examples for that. Parquet, et cetera, et cetera. The other part was Databricks file system. So taking a look there, let's see, DBFS in Python. We have this shared file system, a distributed file system that's just inside of this notebook context, inside of the cloud, and that we call that DBFS. Question? Sorry. Question? Oh, sorry. Okay. We call this DBFS. And this is what I was using earlier. I had taken a bucket in S3 and mounted it into DBFS. And so a lot of the data that we've been using in the earlier examples was all running against this. dbutils is a library. That's a lot of convenience functions for manipulating that. For instance, here you could do mkdir to define paths where you want to save some data. You can display it doing an ls. Etc. I had mentioned about mounting S3, and so here's a pattern for doing that. You just have to define what your access key is, what your secret key is, name your bucket, and then give it a mount point, give it a path. All right. And then moving into there, I'd like to show beyond, we'll show more examples of SQL, but I want to show some more visualization of what to do with results. And there's some great built-ins for this. So the first thing is, Chris had pointed this out a little bit earlier, but as you saw when I'd done the SQL query, I wanted to show like a line graph or a bar chart. I was actually getting an error until I hit plot options. And that was just because I'd exported this notebook and re-imported it, and a little bit of a bug. Anytime you have a SQL query, you can take and display the results of the query. And there'll be a few options for this. One is on the bottom left-hand side, there'll be a table format. So it'll format it as an HTML table. Alternatively, you can select from different types of charting, different types of graphic display, and there's a number of options. The options come in pretty handy, in particular for being able to do things like series groupings, if you've got a pivot table or a more complex kind of bar chart. So you can define keys, groupings, and values, similar to what you do in Excel. And this is all built into the notebooks. There is a chapter about this in Databricks Guide, Chapter 5, Visualizations, if you want to drill down into all the different options there. But in particular, I wanted to show the display command does a lot of heavy lifting for visualization. Like I'd shown before, you could take and display a schema RDD or results of a query. It's also useful for being able to work with libraries like matplotlib. If you're doing a figure in matplotlib, you can use display to get the output as a cell. There's another built-in similar to this. It's called display HTML. And so you can render any kind of HTML and JavaScript that you want to put in. This is a great way of being able to leverage some JavaScript for visualization. And one of the best examples is, anybody here worked with D3? Okay. One of my favorites. So if you haven't seen D3 before, I would definitely recommend going to examples under d3js.org. And it'll start to show you some of the types of examples. Hossein Falaki was doing a great data exploration talk yesterday in the data science track and was showing using D3 with force-directed graphs. So the nice thing about this is that some really great interactive data visualization in JavaScript and a lot of different flavors of it, cartograms and whatnot. And all of this can be used with display HTML. So the idea there is that you can take and through the notebooks be able to get some type of a result set. And for instance, you could take a result set, some RDD, and serialize it as JavaScript out to the shared file system. And then read that back in through D3 and visualize it. So it's really rich as far as types of visualizations. It's also very interactive. I'll show some examples of that. So if you go to Spark Camp under Viz D3, right here, Spark Camp and then Viz D3, we've got several examples. First off, I'm just going to define some data to use. I've got letter frequencies, a little bit of text analysis there. But then I've got some HTML that's defined here. And a lot of this is just cut and paste out of a D3 example. And so we'll apply it to that data that we created up above. Ooh, D3 is not defined. Oh, man, they created the shards. OK, I will show this demo after break. I just realized that they redid the shards last night without reinstalling D3. OK, I don't think I have any of this cached. What?
It's probably under just
Let's see what's going on. This was a newer one that Hossein had, and I don't think it's going to have the right libraries, but we'll see. No, I'll have to rework that path. Okay. I'm sure that none of this is cached. None of it's cached. Okay. I promise there was really great interactive visualizations in D3, but I got to get that working. So, but it does?
Yes.
Which shard are you on?
This is what you're supposed to get?
Yes. What shard number?
50?
50. Huh. $50? Okay, well, if your neighbor is on shard 50, check it out. And I'll work this out on the other shards over break. I'll get a better example. That's baffling to me. Somebody upstairs may have run this. They may have run setup. Okay, good stuff. Let's see here. Speaking of which, they say break. We're about an hour in. It's like 2:30. Probably a good time for a break. So why don't we take like a 10-minute break? I can try to get some of this stuff fixed up. We'll also see if we can get a hold of Michael upstairs. And I'll be around up here if I can answer any questions. Let's see, 2:30. So we'll come back at 2:40. Anything? And this is good timing with the other sessions going on upstairs. So I wanted to introduce some of my colleagues here. Pat McDonough is head of customer solutions department there, something like that. What's the official title?
Field engineering.
Field engineering. Okay, excellent. Hossein Falaki. If you may have seen Hossein's demo yesterday with D3 and exploratory visualization. Some of us were just talking about that. Hi, question? Microphone. Oh yeah, let's test this one. It's only got one setting though, if I recall. No, I mean I think they override the switch. So it may have batteries out. I'll also introduce Samir Faruqi is teaching advanced DevOps upstairs. And Chris, Chris Regley has been here in the session. We wanted to open this up as Ask Us Anything. So we wanted to, I know we've had a lot of questions, particularly about Spark SQL. We got into a number of interesting questions about Hive compatibility, what the roadmap looks like, SQL standardization, et cetera. So I wanted to open the floor before we go into some of the other sections. Let's take like a 15-minute segment for this. Sound good? We'll just kind of see how it goes if we want to take longer. So, opening yeah, we need a mic up here, actually. I think we only have one remote mic. Got any questions out there? Yes? Yes?
Can we use Spark as an engine on Hive? I just saw, like right now there's a chance, like opportunity to use, just an engine saying set engine as Spark instead of Hive. Same as we could use as a, Diz as an engine. Can we do that? So it's been somewhat confusing. So this is not surprising to hear this kind of question. There's Spark SQL. You guys should already know what Spark SQL is. It's the SQL library and engine built into the core Spark project. In that scenario, you can run Hive queries. You can run Hive QL. In Databricks Cloud, you're actually using the Hive SQL context to run Hive query language. You can point to a Hive metastore and have access to all the Hive tables. But in that scenario, with Spark SQL, you're running a Spark application with Spark SQL as the library, as the interface. There's a separate project, completely independent of the Spark project, which is sponsored and kind of managed by several other vendors. So there's a separate project that is kind of sponsored and spearheaded mostly by Cloudera, which is known as Hive on Spark. And that might be what you're talking about, which is essentially the same Hive front-end tools, yet they're going to use the Spark, use Spark as the execution layer. But that's kind of an early beta project. I'm actually not really clear what the most recent status is of it, but it's totally separate than what you get in,
Spark from Apache, you download, you unzip it, and there's already this SQL engine inside of the core Spark project.
Alrighty. Other questions? Yes. Yes.
Oh, how compliant is Spark SQL with actually SQL? Like there was the TCP 99 query standard.
Yeah.
So Spark SQL, as far as what we aim for in terms of compatibility, is more or less compatibility with HQL at a certain version. That is most recently up to Hive 13, plus some backports minus window functions, if I'm not mistaken. So more or less, we track the Hive query language, which is different than traditional standards compliant SQL, because like in distributed systems, things change, and we're not necessarily targeting going for like ANSI compliance.
Yes, we support like Hive UDFs and like SerDes and all that stuff, so it's not just totally isolated.
Yes, question.
Yeah, the pandas data frames have, I've noticed like users coming out of college with business degrees really abstracted people from, they can do really complex things quite simply with the pandas language of the
Yeah.
data frame. Do we see that direction with the data frame in the Spark world? Because that seems to be an ability to open quite a complex feature set without removing a lot of the complexity of what RDB is and the magic behind the scenes.
Yeah.
See that evolution?
So for the for the data frame, so Spark's data frame, we have an implementation in Scala, and then one in Python for PySpark, and the Python data frame API is designed to be very similar to pandas. So that's like the goal. We see pandas. We know people are already familiar with pandas, know the API. So we want the API to be parallel and very similar. Now, we're not, like, some of the features that pandas have, you cannot have on data frames because they're immutable. So with pandas, you can update rows and columns and stuff. So those are out of the picture. But some others are possible, but we haven't got there yet. But the goal is eventually the data frame API in PySpark is going to feel very much like pandas. It's kind of an ambitious goal, but we are ambitious people.
Righty. What question? Yes. Yeah, sorry, yes. Close to the light.
So we know of that effort. We have been talking. They've been talking to us. So we are aware of it. The way I see data frames implemented in Spark, they are closely tied to the SQL engine. So basically, when you write a data frame, a line of data frame transformation, that goes to Catalyst, which is a Spark SQL optimizer, and gets optimized. So you end up with a very efficient physical execution plan, and that we have seen in our benchmark. So it's fairly tied to Spark SQL, and in that regard to Spark Core. The Continuum effort is, I don't know a lot of details about it. I don't know exactly if we're gonna, what's gonna happen exactly there. But in terms of the data frame API, I can tell you that the reason it's done in Spark is because it's fairly integrated. That gives us a lot of optimization room.
Well, I mean, I actually didn't get to see Peter Wang was speaking yesterday. I have my own mic. Why do I need this one? Yeah, there you go. Thank you. No, well, so one of the authors of Blaze was speaking yesterday. I actually didn't get to hear him speak because we were preparing some other things. But we definitely do talk with the folks from Continuum, and try to keep in sync there. From what I understand, though, Blaze, I mean, it will be interesting. I'm not sure exactly how much overlap there will be. I'm glad to hear about trying to get tight integration, but I know that they have a different view of package management and very different view of containers. So I'm not exactly sure how tight we'll be able to couple on that. Other questions?
Any performance benchmark against Storm versus Spark streaming?
Ah, yeah.
Yeah, there are some kind of older benchmarks to take a look at. Well, I mean, I wouldn't even call them benchmarks. I'd say performance comparisons that are that you can find kind of on the internet. I mean, I think one thing to always keep in mind is that you're inherently dealing with like different styles of systems here. You know, you've got micro batches versus event based, right? So it really depends. Are you measuring like on an individual event level, looking at latency from that perspective, or are you looking at the kind of entire stream of data and measuring latency kind of in aggregate? So that's, you know, it's not always apples to apples when you compare the two, but there are some published kind of performance comparisons. One other thing to keep in mind when you're trying to compare streaming systems is that you know, the exactly once semantics are pretty important. One of the main features of Spark streaming. Whereas if you want to guarantee those semantics with other systems, you usually have to actually implement some additional infrastructure and whatnot, and that changes the actual performance quite a bit. Specifically with Storm, it involves another system called Trident, and that, you know, makes your latency quite a bit higher. So that's something to keep in mind if you do go look for, you know, trying to do an apples to apples comparison.
Yeah. So yes, I just went to a Storm meetup last night, which is kind of funny because I work on Spark streaming stuff. I felt like I was kind of in the enemy zone. But yeah, Nathan Mars was there, and yeah, so he spent quite a bit of time talking about the like Lambda architecture and that kind of stuff. But yeah, people asked about Spark streaming, and I don't think he actually ever said the word Spark the whole time, which was kind of interesting. Yeah, he kept like deflecting it and just didn't want to talk about it. But yeah, I think like the big thing people always mention too is just the common API, right? So, right, like you're not learning the Storm bolts and that whole topology thing, right? So it's a familiar, right? It's like D streams containing RDDs, and so yeah, that's one of the benefits. But in terms of performance, yeah, we just shored up the Kafka streaming receiver, so that's a direct receiver now. It's actually using Kafka as a write-ahead log itself. Meaning that we don't actually write anything, we just rely on the offsets. So each batch that comes in, we can recover it by starting from the offset for just that batch, start and finish. So yeah, a lot of work's going into Kafka. I work on Kinesis stuff. We're shoring that up pretty soon too. So
that's good.
Also, follow-up,
yes.
Any other languages, any plans for support, like, you know, right now Python, Scala, Java, any other, like, you know, plans?
Well, there is a thing called Flambeau that some folks out of Portland who'd done a lot of closure work had done, Soren Macbeth. And have you seen this? Okay, yeah. So, there is closure support as well, but
also,
I don't know how
Spark
much.
R is slated to be merged with the rest of Spark ecosystem. So in next release 1.4, R is going to be a first-class language.
What languages do you want?
Yeah, that's.
You want C++?
Really?
Wow. You should contribute that.
Interesting. Yeah. Okay. Questions? Yes.
Oddball maybe, but are there folks that are using Spark as a single node processing instead of a big data?
Big cluster.
Yes, like basically the dev, test, deploy kind of life cycle for Spark is often that you do a lot of your initial work, locally on one node, I guess. But would Spark be useful in a single node scenario elsewhere? I mean, probably not, right? You're not really going to get the advantages of the distributed computation, obviously, with one node. Maybe for like making R actually parallel processing on a single node, then maybe that's a use case. But I think mostly in development scenarios, like local mode, which is effectively single node, is where you would see that. Otherwise, like, what's the point of using Spark if it's not distributed?
yeah, for the local mode, yeah, in fact, I was helping this guy right here in the front all the way to your left. Yeah, we just got an OOM, right? You were trying to run something, and yeah, I was trying to figure out why. Yeah, he was trying to run you're trying to pull in an 800 megabyte file or something into, I think the heap only had probably 760 or something like that. But yeah, the thing to note is that in your local mode, like you still have threads that are coming up that simulate the actual workers. So you're still doing serialization. This is like a big thing, or like versus I think Tez and some of the other frameworks they kind of take shortcuts when you're running locally. But here we want to actually catch like serialization exceptions when we go from the from the driver to the workers. So, but you just got to jack up the memory, and it's just going to be threads instead of separate processes.
Question? Yes.
Maybe a question a little bit out of this training is suppose your cloud and an enterprise that might have a lot of data in one of the AWS regions. How would that enterprise, let's say, leverage your cloud if they have their own VPC? And I'm trying to understand whether your cloud actually supports all the AWS regions and how that traffic of data between, let's say, your cloud and someone else's private cloud is going to raise their bill.
Yeah, so we have, I think it's like 5 regions that we support right now, and we're always kind of expanding the list to support additional regions. So at some point, if your region's not already in the list, it will be there soon, right? So that probably helps you address at least part of the question. And then in terms of where it deploys in a VPC in your own account anyway. So we typically end up with like a separate VPC, but it's also possible to stick all the resources in an existing VPC if you wanted to, and then you're, solving that problem.
What are the main challenges to take a Spark solution into production?
Okay. Productionizing.
So would you just a little bit be more specific, a little bit more like what production?
See, the security can be a big problem
Okay.
with this solution, right? Taking this because there are not enough tools right now to make this a secure production level solution.
So for security, Spark supports Hadoop security model.
Right.
So
Even Hadoop isn't that much.
I see. Okay. So yeah, that is a challenge. If you're not if your security requirement aren't satisfied by the Hadoop ecosystem members like Yarn security or HDFS security, then Spark also lives within that boundaries. So yeah, it will be you need to.
That's one example that I gave you already. So what are the other things that you have to face during the
Well, I tried to give it to Hussein because I don't want to like give you a product pitch, right? But if you kind of look at all the things that we talk about solving with Databricks Cloud, essentially we're trying to address this very question, right? So like first of all, getting infrastructure even up and running and managed and optimized, like that's usually a problem for a lot of people. Of course, in Databricks Cloud, we're trying to just make it push button, giving people the actual ability to like come to the, to derive some insights from the data, giving them kind of easy tools to actually make progress in that and figure out what it is they actually want to do, whether it's ad hoc analysis or maybe building modeling, doing some modeling or something like that. So that's why we've come up with the notebook stuff because it gives people the right kind of tools and interfaces to do these things. And then of course actually getting these things to run on a regular basis, like that can actually be a challenge. So you need some sort of scheduling kind of cron type of thing, right? So again, that's where we came up with this whole jobs notion. Providing access to like all the data that you care about. Spark itself is very good at that, but obviously, the infrastructure and kind of, networking and all that type of stuff can be problematic to actually get access to all your different sources with, these fancy data frame data source APIs where, maybe you want to point to a database over here and maybe, Cassandra and also S3 and, bring all those things together. Like setting up that kind of infrastructure can also be a challenge. Those are the things that come to mind. Tuning your job. I mean, so if you're not using something like Databricks Cloud, like actually tuning and optimizing the clusters that you run probably would take some time. Tuning the actual pipeline that you built in of itself, as far as like building it in the most optimized way, that can, you're going to spend some time there. What else?
when you try to migrate a Hadoop solution or a big data solution from whatever the customer might be using to Databricks Cloud, there is absolutely no challenge. Databricks
No, I didn't mean to imply that. Probably they initially spend time thinking about like what's the ideal kind of data pipeline, right? So like I'm going to have my raw data sitting in S3, let's say. It's in whatever file format it might be in. We're going to encourage you very strongly to take build into your process conversion to Parquet, let's say, because that's like the most optimized kind of storage format that within Spark and just in general, it's a fantastic file format. So that's like a challenge, kind of figuring out this pattern. And then you're gonna, next question is saying, okay, how are people accessing this data? What queries are they running? And based on that, which of the data sets should we kind of like put in our second level cache or even on the on-heap cache, depending on what the use case is. Figuring those patterns out can be, that's a challenge for our own customers as well. So that's just all a part of like maturing your kind of data pipeline and understanding what the most kind of optimized, optimal layout and storage scenarios are, such that your end users can be very successful, right? So that's probably, I'd say, some of the bigger challenges, other than the actual work of actually building, writing code, essentially.
Okay, quick question. Yes.
You guys thinking about having formal constructs for testing the logic?
Yeah. Yeah.
Yeah, so there's a project right now. Yeah, right. Like the question is for testing, right? You're like talking about something like like MR unit or something like that. Yeah, your actual Spark application code. In Spark-projects or spark-packages.org, there's a test framework. Yeah, like Holden built it. It's got some goofy name, but it's got test in there, so you can search for it that way. It's like a unit test framework for similar to MR unit. So one thing about the testing too, it's amazing to me. Yes, I come from like a distributed like systems and services kind of background, and yes, I'm really amazed that people don't talk about testing in the like big data world, right? Like when I first discovered MR unit, I was like, oh my god, this is beautiful, and really it's not that good, but it's it's better than nothing, right? So profiling, what do we got on profile?
I don't know if you have dug deep in the Spark UI itself. The Spark UI exposes well, it tries to expose as much as possible, as much as can be exposed in a browser. So we can get a lot of profiling information just by looking at the Spark UI. If anything goes wrong, you see all the exceptions from standard errors, standard out. There's that. Also, another thing you can do, if you really want to dig deep, it boils down to JVM profiling. So you can log into a worker during your profiling. If you're running a job that you want to like tune and profile, log in and then launch your favorite JVM profiler, and get statistics and measurements, and then use those. Also, being familiar with internal implementations of Spark. Spark Core especially would help, because sometimes when you get into details of optimizing, you may figure out, oh, someone has already encountered this problem, and there's this variation of the API or this way of implementing this that will increase the performance. One very simple example: instead of using map, if you use map partition, you can implement your transformation more efficiently. I mean, it's more code, but it's more efficient. Things like that.
I would add a little bit, just before we move on to the next question, that really the amount of information that you get from Spark itself via the UI, but it's also worth noting there's other interfaces available to get the same data, like JMX, and you can use Ganglia. And what is the library that drives this whole thing? I totally forget. Go to the Spark documentation. There's a page for monitoring, and it'll tell you all about it, this library that kind of exposes all these interfaces. So all that information is like available to you either via the UI or via these other tools. It's certainly enough for us to support our own customers, so that's great. With that said, I did see some vendors just yesterday, I think, who are doing some form of profiling tooling for specific to Spark. I think I saw a couple maybe talks or signs about that, so maybe that's an interesting space to keep an eye on. Yeah. Right. Yeah, all of the data that drives the UI that I was just talking about is available via these history logs. So I mean, if you would have to write some code, but you could essentially diff them, more or less.
And like the Spark project itself, this is like one of the only, or right, like one of the, yeah, so I guess like largest projects I've seen that actually does like regular performance testing. Like we've actually held up releases because of small little things. So yeah, I mean, I think we test every night, right? At like a minimum, we do a full suite of performance tests. So the actual core itself, and I think the tests are actually open source as well. So I think you can point them to your code and it'll, yeah, simulate different workloads and yeah, and then tell you if there's anything off.
Question over here?
Yeah. With Spark being storage agnostic and all the advances here with SQL optimization, do you see Spark getting into the MPP database area, or you see it as a complement to it?
I mean, okay, so through the abstraction that we've been talking about, this data sources API, I mean, there's certainly a scenario where you could be querying an MPP database. This is probably not your question, but essentially creating a data frame which is actually backed by an MPP, and pushing down predicates into the where clause to make the queries optimized, right? So that's one.
No, yeah. My question was like, do you see it as something that is a competing area, or do you see it as a complementing area?
I mean, do you consider Impala an MPP, right?
No, I wouldn't consider it.
Okay. So I mean, I think Impala considers themselves an MPP.
Or Aster,
right.
or yeah, all those.
Aster,
Yeah.
no, Aster also is wrong actually. For example, getting the more Teradata or something like that.
Okay.
Right.
Yeah.
Yeah, I mean, I think there are certainly a lot of use cases where you could just use Spark SQL instead of an MPP. I think that's one thing I would say. I'm not trying to. I don't want to like imply that we could do everything that you can do from an MPP. And actually, if you look at the benchmarks that people put out there when they compare things like Impala and Spark SQL and Presto, and Spark is actually really performs really well already, and it's a relatively young project. And we continue to drive optimizations to, like, we just fixed something with serialization, which I think boosted all the TPCDS queries by 20% or something. So there's still room for improvement, and we'll continue to drive that. So it can be fast enough to replace a lot of the queries you might otherwise do in MPPs. But with that said, I mean, MPPs do other things, like they are able to take queries from hundreds of users in parallel, and that would be like something that would probably be hard for us to do in Spark SQL right now. So keep that in mind. But overall, the real strength of Spark SQL, in addition to performance, is the fact that Spark in general is this general execution engine with all these libraries. And when you start combining, like let's say you start by querying something using Spark SQL, it's a select statement, it's optimized, it gives you back a data frame, and then you take your data frame and you transform the data, do some like feature engineering, and then do some learning on that data. That type of use case is where Spark SQL and Spark in general really shines, because there's nothing else out there like it that can make it that easy. Yeah.
Question? Yes.
So, being Spark not a storage layer, it doesn't provide any storage per se. What do you foresee? Let's say if you are building a data lake at the enterprise level, what kind of storage you recommend? Like, is it Parquet, HDFS, or you don't care from a Spark perspective?
Yeah, well, so I mean, what we recommend with people using Databricks Cloud is to use S3 and to get your data in Parquet as soon as you can. There's reasons for that. The Parquet support is much better than other alternatives. Although I know Hortonworks is like working on org file support right now, so like maybe at some point that becomes.
That was a question actually.
Yeah.
Do we have any timeline for org support?
I haven't looked at that Jira lately, but they're getting more and more excited about Spark because their customers are forcing them to, more or less. So that's, I think they want to get that out within. I think actually they already have a version available, but it's not in open source. Or not, it is open source. It's not in the core project. I think that's where the status is right now. So anyway, we definitely call them their file formats for sure. Something like Orc and Parquet are kind of comparable. We just have much richer support for Parquet out of the box right now. Like newer things like kind of dynamic partition discovery. Yeah, there's just seems like there's more contributors to it and whatnot. I mean, I'm sure org file support will get there, but right now we definitely recommend Parquet. And then, of course, where are you deploying? Our customers deploying AWS, S3 makes sense. If your cluster that you need to use has got HDFS, then obviously put it in HDFS. It kind of depends on what infrastructure you have. Could you repeat that? I didn't hear you.
Plans for Databricks to support Google Cloud?
We would love to support Google Cloud, but right now we're focused on AWS.
We announced that last year, didn't we?
It's right now we're focused on AWS. So we're
So currently it's AWS. Other public clouds are planned, haven't been done yet, but there's plans for them, and in future will happen.
Yeah, so we're always designing to be like cloud agnostic, right? We always have the extra layer in there to swap out. But yep. And there's GCE scripts right now for the open source Spark, so so you can go out there and spin them up. They're on Spark packages.
Okay,
What suggestions do you have for start contributing to Spark open source? Like what kind of things can we contribute?
Yeah, there's the starter.
Tensors.
Yeah.
General purpose tensor
Yeah.
factorization. I'd like.
Yeah, streaming random forest, I think, is where you should start. That's right. No, so there's the starter, like Jira's. If you go to the open source and just search for the tag starter. I just asked about that the other day, and I guess we haven't been as good as we have in, like kind of the early days, but we need a lot of Python like contributions, right, to keep parity.
Yeah.
What else?
Well, so let me just high level. The Spark core is like considered stable. So at this point, any contribution to Spark core should be about optimization, stability, and performance, right? How the other packages, the Spark SQL, MLlib, streaming, those are much more active. Spark SQL and MLlib are the two most active sub projects or components in terms of contributions. They've caused a lot of excitement. So if you go to any of those, you'll see a lot of starter tickets that you can start off with if you're interested in those. So there's PySpark, and there's going to be Spark R, and also there's some special code for Java API. The Java and Scala are pretty consistently compatible. I would say I don't think there is any missing features, as far as I know. There might be some small ones. For Python and R, there are cases where there is a feature in Scala or there's something exposed in Scala, the equivalent Python API is missing. Those are also good places to start if you're interested in those languages.
Last but not least, with the push for data sources APIs, we are fully expecting a lot of contributions. Probably not in the Apache Spark project, but in sparkpackages.org. For build a data source for you name the type of database or the type of like MongoDB or like there's so many choices out there or Redis or something. The API is very easy to use. Michael likes to say it would probably it's like a day or two long project to get one of these kind of data source adapters built. So that's actually a pretty easy starting point in which you can contribute to sparkpackages.org with very little kind of bureaucratic overhead, which otherwise comes with Apache processes.
Starter tag, yeah.
It's a tag, right? Is it a tag on the Jira? Yeah. Yeah, for the sources too, keep in mind that there is a JDBC source that's fully optimized and has the like pushdowns in there. Yeah, so it actually rewrites the JDBC with the optimal. So, yeah, I was just dealing with this with Redshift. I was thinking I had to go build like a custom, Redshift adapter, and the product manager is like, dude, just use JDBC. I was like, oh, okay. So, also streaming sources. Yeah, we have Flume and Kinesis, Kafka. I think we're lacking like MQ series and like JMS and some of those. So we're starting to get requests for that stuff. So yeah, that'd be awesome.
Okay. Other questions? Sound good?
Yes. Any kind of like things that you're kind of unsure about with Spark. It's fun listening to people in the bathrooms and stuff. Like, oh yeah, Spark it like requires everything to be in memory. And yeah, I mean, not like I spend a lot of time eavesdropping in the bathroom, but yeah, you get bored. But yeah, I mean, do you have any? I guess FUD would be the term. Yeah, that's Paco's favorite, which I still don't know. Yeah, like, yes, what does that mean? Oh, I thought it was like an F word. And, I never looked into it. Yeah, my mom would get mad.
Excellent.
Anything?
Any other questions? Okay, that rounds out a half hour. Nice round, a half hour. Thank you very much. Thank you all. Pass the thing. Yes. That was very helpful. Thank you very much. Yeah. Alrighty. Let's see here. We'll pick back up. We got Spark SQL. We got Viz. How about MLlib? Alrighty. So to pick back up then, the next section is an introduction, a little bit of overview for MLlib. I didn't really anticipate doing a real deep dive in MLlib. That's probably better for the advanced data science course. But I would like to show some of this, show some workbooks, sorry, some notebooks, and also field any questions. Just to give a few links here for good deep dives, there was an excellent talk by Reza Zadeh. Reza is actually teaching up in the data science course. He's a professor at Stanford in ICME, a machine learning professor, and also he's a consultant for Databricks, one of the leads on MLlib. And we had done a Spark tutorial back at U Maryland latter part of last year. So Reza has some pretty good slides there about it. As well, Amit Talwalkar, another one of my colleagues. Amit had done MLlib as part of the ML-based project at Berkeley. Amit had done this for his PhD. He's now a professor at UCLA and consulting at Databricks. And so Amit has some great talks about this. I've linked to one of them. Amit will also be doing a MOOC that's starting up a little over a month, but it's scalable machine learning. It's an edX MOOC. It's free to the public, and it's all based on MLlib in Spark. Hossein was just up here, and he had another interesting talk back at Maryland. The third link down there, common patterns and pitfalls for implementing algorithms in Spark. So if you are interested in how the algorithms are being implemented and a little bit deeper dive on how we think about that, I think Hossein has some nice case studies there. As well, there's, prior to doing this kind of training, there had been a few years of something called AMP Camp, where the graduate students at AMP Lab were doing trainings and had a lot of exercises. So I've listed those down there for some of the earlier MLlib exercises. Now, as far as MLlib is concerned, I think that Hossein just mentioned it's one of the most active parts of Spark. As far as the number of contributors and the amount of commits that are going in, there's a lot of activity around MLlib. Looking at MLlib, I wanted to stress the fact that when you look at machine learning libraries, they generally fall into a couple general areas. You have convex optimization that's used to create classifiers. You've got learners that are optimizing to create classifiers. And then generally some type of spectral methods, some type of matrix factorization. So for instance, you might have a classifier that's, say, a random forest. So you use some optimization techniques to create a random forest model. Alternatively, you might do some kind of clustering, like k-means. And that falls more into the spectral methods of clustering, PCH, singular value decomposition, et cetera. There's a lot of different types of libraries as far as machine learning is concerned. And a lot of these have great history, and they're very rich. I was interested to learn yesterday that there is now some integration between KNIME and Spark. I just found out about that at one of the data science talks. Of course, H2O and others have some nice integration. But the key point is that they're different. Those are, generally speaking, libraries. And the libraries have a lot of richness about them, a lot of different variations of algorithms, highly tuned. But the point of MLlib is to create requirements for the framework. So MLlib is arguably much more conservative. It's not implementing all kinds of different algorithms as rapidly as possible, largely because MLlib is about leveraging scale, parallelism, and sparsity, and being able to do that within the context of Spark as a framework. So MLlib is a lot about taking the learnings that we have from machine learning algorithms implementation and pushing that down into Spark so that the framework itself can do this in parallel. As a result, it's more about building blocks, and it's more about a long-term approach. I'll describe a bit more about that, but there's a fairly rich roadmap for this. There's also a project called SparkML, which was introduced in the previous release. SparkML is still alpha. It's a higher level abstraction. It's the kind of thing where we're looking at formal methods for describing machine learning pipelines and then being able to optimize them. And I'm talking about that in more detail. As far as MLlib components, there's a nice package that's been introduced for column-wise statistics, so getting summary stats. Like if you were using R, it's very similar to what you'd see in summary stats there, means and medians and things. Definitely, I mentioned about convex optimization. There's a lot of different types of classifiers, the usual suspects, being able to do logistic regression and doing decision trees and these types of things. In terms of collaborative filters, ALS has been implemented. There's other types of collaborative filtering that you could do fairly straightforward just based off of RDDs, but ALS is built in and it is very much used in production. Getting into clustering, there is k-means. I've heard about work towards hierarchical clustering. I haven't seen that introduced just yet, but I've seen it on the charts. Definitely different types of spectral decomposition, matrix factorization, doing singular value decomposition, for instance. The other parts that have been added in MLlib, there's more and more feature engineering types, aspects of the API, coming up with different types of featureizers. And you can change what types of normalizers you want to be using. You can change that out, as well as different types of optimization strategies. So when I talk about doing some type of classifier, typically you've got some supervised learning where you know that your data can be labeled, have different labels. So basically you're trying to fit some sort of loss function to the data and the labels, and then have some type of regularization term to avoid overfitting. A lot of machine learning algorithms fall into this pattern. So you can take your data and split it into your classes, and then do your splits on test and train samples, and then go through the process of using the learners, optimizing to create classifiers, and then evaluating how well they perform. There's features for most of these. We'll show some examples. A lot of times, though, you don't have labels. So if you're trying to explore your data and you don't know the labels to categorize it with, this is where you might go in and do some type of unsupervised learning. Like, for instance, I was mentioning using PCH or SVDs. There's a great overview if you would like to look at a nice general survey paper about machine learning. I would definitely recommend this one from Pedro Domingos out of Washington. It's a few useful things to know about machine learning. Kind of the dirty little secret about machine learning is that it really came out of at least a half dozen different disciplines. So early on, there were the people in control theory, and then later on, there were people in neuroscience, and followed by people in symbolic logic, followed by people in electrical engineering. All these different disciplines have their own perspectives on machine learning, generalization, and they tend to use their own math and their own nomenclature. So trying to understand how these align and trying to see the general patterns across them is really difficult. I think that Pedro Domingos did a really good job of trying to show where the similarities, where the common points are. I like to show sort of an idealized workflow of what goes on in machine learning, and I know this is maybe hard to read up here on the screen, but in the slides, generally speaking, there's a lot of ETL, a lot of data preparation work that goes in. If you've seen some of the writings from data scientists, I could think of DJ Patil in particular, talking about an 80-20 rule where you spend 80% of your time just cleaning up the data. And it's very true. Once you've got your data in shape, doing some type of exploration is generally needed so you can understand what the structure is. Hossein was doing a talk yesterday and quoting from, I believe it was from Tukey or some of the earlier statisticians, about how you really can't do data exploration without visualization. So typically, some type of visualization there. Notebooks are really useful for exploration. Unsupervised learning is also useful too, just to see, hey, how could this possibly cluster? From there, as you move further into pipelines for machine learning, generally a lot of work goes towards feature engineering. It's a hard problem. When you're working with small data sets that only have a few dimensions, people can use spreadsheets and eyeball them and make some good gut decisions. But human intuition really fails beyond about 4 dimensions. So when product managers are looking at a 1,000-dimension data set, there's just no way you can make any kind of intuitive judgment about what the structure of the data is. So that's where feature engineering becomes both really important and also very hard. Being able to work in really high-dimensional spaces. And fortunately, this is a real strength for Spark. Being able to do scalable machine learning is a lot of the rhyme and reason of Spark. When you look at a lot of the libraries, many of them kind of punt on this, where you might sample down your data, run your learners on a sample of the data, generate your classifiers, and then do scoring at scale. But traditionally, a lot of those libraries are not doing the actual learning at scale. So this is one of the areas where Spark is really trying to focus, MLlib is trying to focus. So again, working with high-dimensional spaces, large data, doing featurization at scale, it's a hard problem, but it is one of the areas that Spark is trying to tackle. Moving further into the pipeline, you do more supervised learning. And this is where some knowledge about what kinds of algorithms to apply comes in very handy. But just knowing the algorithms themselves really isn't the hard problem. The hard problem is more about understanding how to explore the data effectively, understanding how to featurize in high-dimensional spaces, and then understanding how to evaluate the results. Evaluation is also a very hard problem. Different types of algorithms will provide different types of bias towards evaluation methods. So I just try to show a generalized workflow when you work in machine learning to create data products. Usually you see most aspects of what's shown up here, and Spark is very good for putting together these kind of pipelines. Now, I want to throw something out. If you haven't seen it, I definitely recommend a little advanced reading here. This is from Stephen Boyd at Stanford, and the idea is that a large amount of the machine learning algorithms that we use to generalize about data, more and more, these can be expressed as an optimization problem. We can build a convex model with a couple of equations and tilt it one way and get logistic regression, tilt it another way and get support vectors. So more and more, we're starting to think of model selection as a compiler problem. And I think that'll be a big change. This work here has been going on since 2011, and Boyd's team has a lot of MATLAB code if you want to run that. But the question is, how could you do it at scale? And so a lot of the rhyme and reason for MLBase, the parent project behind MLlib, was to come up with pipelines where this type of idea could be applied. And so how can we do efficient hyperparameter search and optimize the pipelines and optimize the model selection? Again, using some of the more advanced techniques. So Boyd's paper goes into a lot more detail on it. Now, having said that, I've got some examples. So here, slides. If you look inside of the, well, that is exactly the wrong URL there, definitely. If you look under Spark Camp, and down here I've got a few different examples. One of them, though, is demo iris MLlib 2. Let me see if I've got that. No, let me go to 1. Sorry. So if you go to Spark Camp demo iris MLlib 1, right here, there was a data set that was calculated, written, published, I guess over 80 years ago. But iris data set, I can imagine a lot of people have used it in the room if you've done stats courses based on this. There are 3 flowers in the data set, and there's like 50 measurements per flower. The interesting thing, it's a fairly small data set, 150 measurements, and it has 4 dimensions, so it's fairly compact. But the interesting thing is that 2 of the flowers have a lot of overlap in their measurements. They're fairly similar. One of the other flower species is quite a bit different. So if you try to put together a linear classifier with this data set, you're going to be in trouble. One of the classes is easy to detect. The other 2 are hard to distinguish. So I pulled in the data. We've got under / Databricks datasets, R datasets. We've pulled in a lot of the data that gets shipped with R. It's all public domain. And part of that is the iris dataset. So we read that in, and it's a CSV file. Let me run that. Let me attach it to a bigger cluster. There. OK, so if I read this, I read in the iris data. And first off, let's just display it here. This is going to do a scatter plot. I've got 3 different species of iris. I think I've actually got a photo of them right here. I had a photo of them. Yeah. OK, good. Well, my apologies. My photo is not turning up. Not sure why. If you take a look at Wikipedia, there we go. So there's these 3 species of iris flower. One of them is shaped very differently, and the other 2 have approximately the same shape. So if you go out and measure their dimensions, you get this data set right here. And again, it's very good for looking at multiple classes. OK, so looking at the data, if I say display, and then from display select in the plot options, I have it as a scatter plot. And I've got the species as the key. That'll provide the color. And then the values down here are petal width, sepal width, and petal length. What you can see then is you look at these clusters here, and there's clearly some of the independent variables work really well to distinguish. So for instance, if you look at petal length down here, petal length, you can see there's very clear separation of the different clusters. The blue is the Setosia species of iris, and it's very clearly apart from the others. As opposed to some of these other input variables, independent variables have a lot more overlap. So we know that petal length is pretty good. Just we can eyeball that. A scatter plot is usually a pretty good way of looking at multidimensional data and trying to understand where there's some good predictive strength. Now, typically when we use MLlib, we're working with vectors of data. So I'm going to show here how to take and create a dense vector based off of this. Let's run this. I think that in the interest of time, I'm not going to go through the entire notebook. But if you want to, I've got a couple of variations of this. Reza Zadeh had taken a pass. This is actually his version of it. So here we show what are some basic stats, summary stats out of it, printing out basically variance, mean, different norms. He was also showing correlations. So beyond just taking a look inside of what the data is there, let's try training a model. Since we've got the data organized in vectors, we could take and apply that, do k-means to create a cluster model for this. We already know that there are 3 different classes in this data set, 3 different species of iris flowers. So we'll set k to 3 and give it another parameter, just tell it to run for 20 iterations. And then just call k-means train on our iris data. And that'll be fairly quick. While I'm doing this, I also want to show, let me drill down on Spark UI. I'm going to drop this a little bit. One thing I hadn't shown before is when you're running some type of Spark application in Databricks Cloud, you can always go back to the cluster and take a look and get some of the metrics. I think that Pat and Hossein and Chris had talked about this a bit. But for instance, here, the last thing that I ran was k-means, and I had a couple stages within that. Both of them are represented here. If I want to drill down on one of these, I'll get the metrics then for what I'd run during that stage. You can see here a number of different metrics, such as the duration of the stage, how much time was spent in garbage collection, how much time in terms of task deserialization. These are all really interesting costs to look at, and it's divided up across min, median, max, and different percentiles. Get a little bit different view of it there. Also give you some stats as far as how much time was it spent in terms of shuffling. So this would get back to some of the earlier questions about being able to do some performance modeling. Okay, so back to that. No. Great. All right, so I've created a k-means model. And down here, I want to do some evaluation. I want to figure out how good does this model work out. There's a metric that we use with k-means called within set sum of squared error. And basically, for every different cluster that you create, how much error in aggregate do you get inside for that cluster? How far away is each element from the cluster center? So a way to compute that is clusters compute cost, and that'll give you the WSSC. If I want to try some other things, one is let's take a look at, Reza was showing here dimensionality reduction, doing some matrix factorization. So for instance, here I'm going to import a kind of matrix representation that we have in Spark called row matrix. So we'll take our vectors and basically create a matrix out of them. From that, we can start to programmatically get access to some of its parameters. So how many rows, how many columns. And then we can use that here, for instance, doing a PCA. So how many folks here have done principal component analysis before? Some. So the idea is that you've got this covariance matrix of your data, and you just start peeling off the eigenvectors. And you peel them off in order, and they explain the variance in your data. So the first one you peel off might give you 80% of your variance, and the next one 5%, and on you get diminishing returns. You can take a really high dimensional data set and peel off eigenvectors. Those are your principal components. And it might be that after you get through the first 3 or 4 eigenvectors, you've explained almost all of the variance in your data. So you've gone from a large dimensional space down to like 3 dimensions. This is a technique that gets used if you want to visualize data. You can take high dimensional data, run it through PCA, peel off the first 2 eigenvectors, and use that to transform your data and plot it in a 2-dimensional scatter plot. Typical kind of technique. So here we did a PCA, and we're going to do it in 2 dimensions. Just peel off the first 2 and run that. It's pretty quick. Good. I missed something. Matt. I didn't run this one. My apologies. Great. And so an interesting thing here is the matrix math. A lot of what we want to do with large sparse data sets is with matrices. And particularly when we work with graphs, there's a lot of reasons for wanting to transform into matrices and then do that. Quite a bit of work has been done on MLlib, a number of contributions, particularly from Stanford, taking and improving how to do matrix work. In particular, working with what we call tall and skinny matrices is fairly straightforward with big data tools. So you can see things like QR factorization. Log files, for instance, the width of a log file, you might have, 12 columns or 50 columns, some number of columns, but probably not huge. Probably not millions of columns on a log file. But yet you might have billions of elements out of a collection of log files. So if you were to take all of your log files and represent them as a matrix, it's going to be a very tall and skinny kind of shape. And there's an area of math for this, for being able to take tall and skinny matrices, cut them in chunks, run the chunks in parallel, and then aggregate the results. And that's pretty straightforward. If you have a small matrix and it's square, we have the math to be able to invert matrices, for instance, and do all kinds of work. But if you have a really large matrix and it's square, then you have a problem. So a lot of some of the contributions to Spark out of Stanford recently have been how to handle really large-scale sparse matrices that are relatively square. Question, yes? Sorry. A question or a sneeze, I'm not sure. So the square matrix problem at scale has been very interesting. It's actually reusing some of the Fortran code that's been around for decades and just finding a good way to parallelize it and put it into a JVM-based framework. So there is well, OK, so here Reza is showing how to do a matrix multiply, taking the results of PCA and doing a projection. Let me go a little bit further. Something that would be a little more typical kind of application would be SVDs. So singular value decomposition. I don't have a good graphic for it here, but I can describe. An SVD is a way of taking a large matrix and splitting it into 3 components. So you end up factorizing it. You have one component, a particular matrix. If you multiply the 3 components together, you can recreate an approximation of the first matrix. And the matrix in the middle is your singular values. It's a diagonal matrix. And it has the singular values are ranked in order. So the lowest one on the bottom right has the least significance. And the thinking there is you can take once you factorize as an SVD, you can just start lopping off the bottom right corner and shrinking that down. And the whole system shrinks down. It'll still generate the approximation of the original matrix, but it's factorized it. And so a use case for this, you can think of having a recommender system where you just want to dial down the knob. Maybe you might have 100 million customers and 1,000 different products, but you want to dial this down so that they're clustered into groups. And maybe you only have a customer segmentation problem with like 5 customer segments that you're trying to sell to. So how can you go from 100 million down to 5? You can dial that down. SVDs get used throughout the industry for a lot of cases. And having that kind of general case square SVD in Spark has been a nice boost over the last couple months. All right, that's about all that Reza had prepared off of this notebook. But if you do go to MLlib2, it's got a few more of these added. I'm not going to go into gory details, but it's got examples of doing support vectors, logistic regression, naive Bayes, other types of classifiers, and trying to show some examples of that. I've got other notebooks as well that show use cases of this and visualize. Again, in the interest of time, I'm not going to dig into it too deep, but that's a pretty good overview for what we're trying to do with MLlib. Let me see. Yeah, supervised learning. Any questions about that? Absolutely. Absolutely. We'll keep this up for at least a week. And there's going to be email going out about converting these accounts. I believe there's like a 1-month trial or some sort of period like that. So there's some span of time if you want to go afterwards. We'll keep these up online. We won't keep all the clusters online. We'll dial that back down. But we'll keep some clusters up. Yeah. Yeah. Yes, most certainly. Actually, that's a great point. So again, one of the things I mentioned earlier on was about export. At any point in time, you can go in and let's take a look at this one. I can go in and say export. So if you click on a notebook off to the right, there's a drop-down menu. I'll say export, and this one here I will export as source file. And this was a Scala notebook, so it'll drop out a Scala module. If I go back down here, let's see what kind of trouble I get into. So I've got this file. Let me open it up. Great. And so now I've got an exported version of that notebook. All of the Scala is there, and any of the markdown is as a comment. And you can export this back into another notebook. So that's one way of being able to get access to all of this. Alternatively, if you go to, let's see here, where's a good spot? If I were to go to, let's see the D3 viz that I had, I could take this and export. It's a folder, so it's got several different notebooks inside the folder. If I export then, it's going to be called a DBC archive. And if I download that, let me go to push. Is that readable? Yeah, probably too readable. There we go. And what was this, viz? OK. File. So if you export a folder, it'll be a DBC archive. It's really just a zip archive, a jar file, really. But we use the DBC extension so we can sign it. And if you take a look at that, then what you'll end up having is, in this case, it's a folder, so there's all the different Scala modules that are inside there. Maybe also there'll be some JSON that describes the notebooks. So it's all exchangeable formats. Good question. Other questions? How about machine learning implementations with MLlib and Spark? Any questions about that? Alrighty. Let's see here. Graphics. I'm not going to go through a whole lot of graphics, but there are a couple notebooks here if you want to drill down into this in more detail. The programming guide for graphics is actually quite good. I'll definitely defer to that to some extent. There's a good description of it. The history of graphics, though, is there's another project called GraphLab. Anybody using GraphLab? Or Datto, as they call it now. There's a project called GraphLab, and GraphLab was using a pattern that's called graph parallel system. And there's a link to, I believe I have some of the papers linked here, yeah. So the original paper out of CMU, if you want to check the original GraphLab paper, it's somewhere there. It described the notion of a graph parallel system. And so a certain class of problems that would actually fit pretty well with Spark, as it turns out. There was also another paper that came out of Google. I think that's on the next slide. There was a system called Pregel. And there's a public paper out of Google about their Pregel system, how they handle large-scale graph computing. And so there was work done back at Berkeley. Joseph Gonzalez, who's one of the authors of GraphLab, is doing a postdoc at Berkeley at AmpLab. And he ported the GraphLab API onto Spark. And also there was additional work porting the Pregel algorithm onto Spark. And the two of those together, there's now another component on top of Spark called GraphX that allows both the Pregel abstraction as well as the GraphLab API. There's a few links here about this. Ankur was giving a talk about this yesterday, I believe. But the basic idea is this. If you have a graph, you have a number of nodes, and you have connections between them. So if you can take the nodes and represent them as an RDD, and have another RDD that represents the connections between them, the edges, you can take those two RDDs and compose them together to create a graph. You can apply functions to that graph. For instance, take a look at the triplets, and traverse the triplets. And the results that you get back are RDDs. So much the same as we have with Spark SQL, where there's a one-to-one between RDDs and tables, and the results from a query come back as a schema RDD. Same thing here. We can take and compose RDDs to create a graph, and then get RDDs back from the graph queries. This is a real trivial example here. I've created a couple of arrays. There's some people and their ages. And then for each node in the graph, I've got a unique identifier, a long, as it shows up there. So there's Kim, Pat, Chris, Leslie, et cetera. And then there's an edge that's defining an attribute, a value on the connection between them. So we take those two arrays, and we parallelize them into RDDs. And GraphLab is expecting a certain kind of schema for these RDDs. But you can have a variety of different data on the edges as the attributes, and also various types of data for the nodes. Once you've got the graph, then, you can take and start to apply functions to it. In this case, I just did a very simple traversal, taking a look and grabbing all the triplets where the attribute value was greater than 7. There's only one of those defined up here. And then print it out. So a real simple graph program, but it starts to show how you could do traversals. Now, a more complicated kind of graph processing would be something like Dijkstra's algorithm. So if you've ever done this category of processing, of course, it gets used a whole lot. Things like Google Maps. When you run directions in Google Maps and you look, what's the shortest path between point A and point B, given the current traffic conditions, that's running Dijkstra's algorithm, essentially. And so here I've got 4 nodes and some labels on them. And then I've got some edges between them and the costs associated. I could take and represent that as a couple of RDDs, create a graph, and then run Dijkstra's algorithm, run an SSSP, and find out what's the shortest path between certain nodes. So as an example, if you look at SparkCamp 0x-GraphX, right here, under GraphX, great. And let me attach this. All right, so for the first example, here I've just got 2 arrays, and I create RDDs for both of them. And then if I want to run a query, pretty straightforward. I'll just grab their triplets and print them out. Very simple traversal. If I want to do something more complex, though, here I'm going to look at the shortest route between various points. And again, this is the kind of thing you do in Google Maps when you do directions. It's the kind of thing that delivery services like FedEx and UPS do all day long. So here I've got an array that's describing a few different airports in the world and some edges just describing costs between them. If I take and parallelize those as RDDs, I compose it as a graph and run that. OK, I've got GraphX running for that. And now I'm going to go in and set the initial values, positive infinity. And if I want to take a look at those, I can just do a collect. And it'll show you what the nodes are, and here what the edges are. And now if I want to run Dijkstra on this, I've got a pretty short implementation here in Scala. It'll look for the shortest path between. Great. And essentially what this is telling me is that if I start from node 0, the cost of getting to 0 is trivial. It's 0. The cost of getting to 2 means I can go directly there with a cost of 1. Cost of getting to 1, I can go there directly, cost of 2. And cost of getting to 3, it's best if I go through node 2 to get there with a cost of 2. And that can get a lot more complex. We see this in terms of routing problems, scheduling problems, maintenance scheduling, supply chain, et cetera. We see a lot of very interesting complex graphs. And again, being able to handle this in parallel at scale is one of the benefits of Spark. Just as exercise, here's some data for national parks in California and how much time and distance there is between them if you wanted to run this as an SSSP. Alrighty. There's also a fair amount in GraphX having to do with another class of graph computation that's more of the social network problem, the kind of Facebook problems, where you want to look at communities. And you have a social graph defined, and you want to see how that can be decomposed into cliques, people who have a lot of affinity to each other. There's a lot of use cases for that in social networks, in advertising, anti-fraud, et cetera. How many folks are working with graph databases? I wanted to check about that. Some? How about Neo4j? How about IntelliGraph? Let's see, GraphLab? Any others? Any I'm missing? Titan. OK, awesome. Are you using Titan on Cassandra?
No, Titan HBase and use.
With HBase. And are you using Titan with HBase as well? The other? That's a great question. I'd work some of the Titan folks. So Titan is like a layer on top of various distributed storage frameworks, Cassandra or HBase or Cumulo. And their idea was really more of like the system architecture argument about it. They denormalize the graph. One of the problems with working with graphs is you have to do a lot of memory access. So you go from one node and you check out all the different paths, and you go to that node and get its paths. And it's a lot of memory access. So with Titan, what they said was each node is going to know about its immediate edges, and then each edge is going to know about its immediate nodes. So that way you get a lot better pipelining through. Kind of the simple approach to this. Yeah, so you can get a really nice distribution of this with something like HBase or Cassandra, a very, very large-scale graph. I know. Yeah, or Cumulo too, I believe. There's some pretty large installations on that.
Really high node, counts, it didn't have some of the memory problems that Neo4j.
Right. Neo4j is definitely going to be more of like a single server kind of solution. So yeah, definitely. Yeah, no, this is interesting. We had been talking with them. I don't know if there's really any active work as far as integration, but one of the nice things about Titan is there's a lot of different layers, gremlins and all that, so there could be potential for that. Yeah, very, very large. Apple, Netflix, others, very, very, very active in this. So, alrighty. Any other questions about GraphX? Yes? Representing graphs as sparse matrices, excellent. So yes, you can, by algebraic graph theory, you can go from a graph representation down into either a transition matrix or an adjacency matrix, depending on what directionality you have on the edges. A typical thing like that would be PageRank, right? You've got this web, and you've got all these nodes and the links between them, and you can represent that as a sparse matrix, a transition matrix, and then calculate PageRank by doing some nice eigenvalue tricks on the transition matrix. It's a much more efficient way to converge PageRank than actually doing the graph approach. Going from graphs into matrices is really interesting work because so many business problems are graphs. But yet, when we can get to the point of having a sparse matrix representation, we have excellent libraries. So for instance, one of them that I would point to one that I would definitely point out is Algebird by Twitter. And this is a library that works with Spark. It has a few different parts. In particular, the matrix math part of it is very interesting. There's also a fair amount of support there for sketch algorithms, approximation algorithms. And they're related. Algebird came out of the fact that Twitter didn't want to invest in large social graph problems the way that Facebook had. And instead, they wanted to be a little more advanced in terms of their use of math. And so instead of working with graphs directly, they transformed into matrices and then built very nice sparse matrix libraries. That's where Algebird came out of. And so their revenue analytics team uses this. They started out in Scalding, and it's also very useful for Spark. Reza Zadeh, I'd mentioned, he's up teaching the data science course, but this is his area at Stanford, is working with sparse matrices at ICME. Alrighty. Other questions? Yes? Yes? Well, short answer is we're working on it. It depends what type. If you're working with GraphX, right now it doesn't have a Python binding. And there are things like NetworkX. There's some different types of libraries in Python for visualizing graphs. If you're working in D3, though, there are nice graph representations in D3. Now, the trouble there is if you've got a really huge graph, you don't want to send all that data down to the client and then render it in JavaScript, at least not in terms of the kind of graphics that D3 is using. So typically, you'd want to do something on the server side to start to build up your visualization. We don't have anything like that automated yet. There are systems like Gephi. If you're familiar with using Gephi, Gephi.org, that will do JVM-based large-scale graph visualization. Yes?
Not like exposing my ignorance here, but do graph problems ever go beyond 2 elements or 2 dimensions?
Yes, they do. So I was popping off a little bit earlier, like what to contribute to Spark, and I mentioned tensors, general case tensors, factorization. If you in linear algebra, if you move up from a graph in a matrix, sorry, if you move up from a matrix which is 2D, a general case graph that has multiple dimensions on the connections between them is called a tensor. So you can think of having like a 3D matrix or a 4D matrix, et cetera. So when you get into these really large dimensional data problems, like with anti-fraud security problems, the general case for solving it is to do tensor factorization. There hasn't been a lot of open source software for this until very, very recently. And there's a great talk at Strata. I forget the professor. She's a math professor at UC Irvine. Blanking on her name, but there is beginning to be more and more work in this area of big data and tensor factorization. And the gist of it was, usually tensor factorization was something you had to watch pretty closely. You kind of had to guide it along. It was kind of hard to automate. But by looking at probabilistic techniques, you can take your raw data and reshape it a little bit with some probabilistic techniques so that you can factorize in a much more general way. That's the takeaway. And it would fit well with Spark. We actually had quite a little Twitter storm about that last week. This is something I don't think is very far away because there's a lot of demand for it. A lot of industry problems could use this. Alrighty, other questions? Okay. Alrighty. Let's see, we're up at 4. One of the things I'd like to do is, well, let's see, we're going to case studies. One of the things I'd like to do for the course today, number one, I guess we've been going for about an hour and a half without a break. Is it time to take another break before? Hands in favor, or should I just power through? I should go get some coffee, probably is what I should do. How about this? I was going to, since we started at 9, plan to go through at least like 4:30 and then have more of a Q&A session afterwards. Basically, I'll hang around for a while. I'll probably be here till about 6, and then I think they kick us out at 6. I've got some demos to do, but in the interest of time, if some of you all wanted to beat the commute, we'll definitely try to wrap up the formal part of this at 4:30 and then just shift into Q&A and demos and a lot more one-on-one, if that seems reasonable. Okay, great. So let me wrap up then the last 20 minutes here. We'll go through, I've got some case studies and some other materials that will be good to cover. And that works out for pretty good timing. Okay. So we have a few case studies regarding the actual use of Databricks Cloud and then other case studies for Spark in general. So one of the first public case studies for working with notebooks is from a company called Automatic. They're based in San Francisco. And they actually do a large number of the devices that are being installed in cars. It's being used for UBI, usage-based insurance. But it gives a lot of great signals. It's tied into some of the telemetry on the car. So you can start to correlate between engine control lights coming on and other signals. Another example would be, if people are all slamming on the brakes at a particular intersection where they normally wouldn't, it might be a pretty good signal for the city to go and check and see if a tree has fallen down on a signal light, something like that. So they get some great data. I've seen some pretty humorous analysis coming out of this. Like, for instance, when they take a look at model of car versus sudden acceleration and sudden deceleration, for some reason, Maserati was like topping out the leaderboards for both of those. So a lot of great insurance company data right there. And the thing about it was they had been doing work with large data, of course. This is IoT, Internet of Things. But they wanted to get to better and better dashboards for their customers. So they have all this geospatial data, time series data, based off of what they're collecting from the sensors, and a number of different use cases of how they're commercializing it. The thing was that they were a fairly small company, early stage startup, but yet they still had a lot of penetration in the market. They wanted to jump into using Spark without having to build up an army of DevOps people. And so infrastructure management was one of the key costs they were struggling with. The other thing was really being able to take this data and allow people who were not programmers to jump in and do the analysis, particularly using SQL. So by using the notebooks and SQL in the notebooks, they were able to enable their team without having to double down on the amount of engineering. And so they had been using Redshift, I believe also Tableau and some other types of tools. One of the things was they wanted to bring that into a single platform. They really wanted to use visualization capabilities in notebooks because that was a very short path from notebook to the end product dashboards. And MLlib was giving them a lot of the kinds of algorithms they needed right out of the box. So I believe that Rob was giving a talk here. I didn't get to catch it. He was in a different one. But I ran into Rob at lunch last week, actually. So I'm sure this will be in the video archives. Another company is Radius. Maybe some folks from Radius here I'd run into earlier today. They're a BI company out of San Francisco. They take Salesforce data and other types of data, but they take this anonymized from different sources and can get a much more a broader signal, if you will, a much more enriched signal off the sales data. And so basically taking your CRM data and then using it for a variety of purposes. They had a similar problem. They had implemented previously using Hadoop, and they had a pipeline, but it was taking like 12 hours to run. So they wanted to shrink down their batch window. It was also becoming more and more complex to make any changes on this pipeline. I worked previously on the cascading project, so they were one of our customers where I was working previously. And another thing, too, is they really wanted to make big data open and available, this kind of analysis, to the non-technical people that they had who really understood the use cases without having to bring in programmers all the time. So they were able to go from a 12-hour batch window, drop it down by 10x by shifting over to using notebooks and Spark. And also, of course, using the notebooks allowed their people who were closer to the use cases, more the data scientists and the business people, could jump right in and access the data. We're seeing this as a very common theme for cloud-based notebooks. And I saw Alexis. I don't know if he's here today, but I know he was here yesterday. One of my former coworkers who has done some videos about the Radius case study. Another company, MyFitnessPal, was recently acquired by Under Armour, and they have an IoT device, a wearable device that they couple with data about nutrition. And so they were combining data from mobile apps, really trying to understand more about their monetization strategy. They have some products where they recommend nutrition, diets, et cetera. And so they had a fairly complex pipeline of all these different types of data sources, a lot of scripts that they were running for this. They wanted to simplify that, have a much more unified kind of approach to it. Also really shorten the development, the product development cycle. So this is a case where they were using Redshift and Tableau, but they wanted to pull it back together into a common platform. I think we had some questions about Redshift and Tableau earlier. And also, I think Hassam had a talk earlier. I'd seen Hassam in the hallway yesterday. Oh, yes?
Like, what is the magnitude of data these guys are using?
Interesting. The data rates on MyFitnessPal, I actually had several of their engineers in a class recently. I don't know the data rates, but I could find out more about that.
I mean, do you have any idea what kind of data these guys like? Is it 100 terabytes or 1 terabyte? Is it like
No, it's
1
too much.
petabyte?
It's not that.
Very important, actually, software as a service. There are probably more than 100 million users spread to this, and they generate about, let's say, almost half a megabyte each. Do the math, and you'll see we're talking about probably hundreds of terabytes. Every day?
No, no.
Right now.
Altogether.
So how much are they pumping, like processing every day?
Every day, for example, I generate myself about 1 kilobyte.
Times 100, times many millions of customers.
It is integrated with other fitness programs like
Yeah.
Fitbit, and you have all kinds of Fitbit devices that tracks your weight, tracks your speed, you run your foot.
Yeah.
It generates about, I would say, probably at least 1 kilobyte of data for each user every day.
I've got data rates for some other case studies. They're actually pretty large. I don't have them for this, though.
What was the automatic, are you aware of what is the automatic throughput rate?
I don't have it at the tip of my tongue. I think that they have disclosed some about that, but I don't have it. But I would definitely check out Rob Ferguson's talk. I'm sure we have a video archive of that. We probably have the slides too. Yeah, that's it. These kind of IoT use cases are very, very interesting. They really push the real-time requirements, or they're starting to as well. I have other case studies, and I will point toward another resource. If you go to under my SlideShare, on slideshare.net, Pacoid, let me look at some other case studies here. Let's see, Spark Data Preview. I've got a bunch of these. So for instance, here, we did a talk at the LA user meetup, and there's a great case study here. Let me scoot through a little bit. I must have missed him. That's not it. Yeah, there we go. So there's some case studies here that we had published about Spark Streaming. We don't have Spark Streaming available in Databricks Cloud right now, but I'd like to show a demo of this after we close up officially. I've got a pretty good scale streaming demo to show. And this is a talk I gave off of streaming specifically. Over the next couple of months, we are moving streaming support into Databricks Cloud. We have it internally, but we aren't exposing this yet. Chris has actually also been doing demos on this too, and actually a lot of the integration work. Yeah, I'll do a demo of that as 4:30. But I did have some case studies which start to give a little bit more idea about the magnitude. One company definitely talked with a lot is Stradio. They're out of Madrid and doing very interesting work with Spark Streaming. They put a CEP layer on top. If you're familiar with doing complex event processing, they put the City engine on top. So you can do CEP queries, but then it's running Spark Streaming under the hood. They also paired this up with Kafka and Cassandra. Very nice integration. Pearson is an interesting use case for streaming. It's Pearson Education, and they're doing this for their essentially the marketing funnel, getting a lot of sales metrics, but very much in real time as well. And they have a very large graph that they use for analyzing this. So they're using Kafka and Spark and Cassandra, and then indexing the results, putting that into Apache Blur, kind of like Elasticsearch. But they're also generating graphs downstream to be able to use for GraphX. And they'd done a lot of work with this as far as the Kafka consumer, improving that. Uyala is a pretty interesting use case. I know they do work on video analytics for Bloomberg and others. Some pretty large use cases there as far as the transcoding, the pipelines for video, and the analytics for the consumption. The one that I'd like to point to, I believe that Eric Carr was doing a talk here. I didn't catch it, but Guavus is getting back to data rates. Very interesting. They cover 50% of US mobile data traffic. They do analytics for it. And they're bringing in 2.5 petabytes per day. And so that's 4 out of 5 top mobile network carriers. Very, very sophisticated. Eric's talk was interesting because before, their priority had been get the data, land it, drop it into HDFS, and then as fast as possible, do your analytics, because in this field, with telecom, you're trying to find faults. People are upset if their mobile service is down, so the faster you can identify the fault, the better. And by using Spark, they were able to shift that thinking and instead do the analytics on the fly, land it afterwards. It sounds trivial, but in a large organization, that's not trivial. So very, very interesting insights, but also just looking at this 2.5 million transactions per second. It's definitely enterprise. Share through is an interesting use case. One of the first production use cases for Spark Streaming, they had taken the algebra library that Twitter made and extended that. So they do some fairly sophisticated work with abstract algebra to do sketch algorithms, approximation. And it's an ad tech company, but they're doing some bid system optimization. Oh, on Guavus? No, I don't. I've actually worked with some of their engineers at hackathons before, so I've talked with them. And I've heard that, but I can't remember it reliably. But they were pretty open about that. I'm sure they could probably get some data out of them. That's a good question. Also, the videos from Eric Carr. He's VP of engineering. And we've got his videos from other Spark Summits. Oh, OK. I just want to point out that I have a number of other use cases if you look at some of the other slides on SlideShare. What was it, the URL for that is, it's going to be under, here, let me knock down some of these windows. It's going to be under SlideShare/Pacoid, if you dig that up. And also, other colleagues, we also have SlideShare/Databricks. But I've probably, actually, there was a question about the DevOps class and getting the slides. Somebody had. There's the first one that pops up. But yeah, we've got a nice backlog. I guess we've got about a dozen in there. OK. Another thing I want to point to, we talked about this a little bit during the Q&A, but as far as some other resources, sparkpackages.org. I highly recommend checking this out. One of the things about Apache is it is a pretty interesting process to get code submitted into Apache and approved by committee. So that definitely takes some effort. We wanted to streamline this. So for third parties to be able to do Spark packages and just get them out there as fast as possible. So we put up a community site, sparkpackages.org. And we also have a Maven repo that's coming up along with this, so you can grab the assets right away. There's a number of different types of connectors here. Here's Hossein had Spark CSV. Number of these that have come in. I know that there was a question, Spark testing base. There was a question about unit tests in Spark, and this is from Holden. She had written a very nice library for that. Anyway, lots more there. Let me scoot through here a little bit. Another thing I want to point to, as far as resources, we have a developer certification program. And so we've done this as a partnership with O'Reilly. The first one is Apache Spark Developer Certification. We're working also on a couple other certification exams. One that's more for DevOps, another that's more for data science, analytics. But this first one here, if you have any questions about it, I'd be very happy to answer afterwards. We're putting together some test prep guides at O'Reilly. I'm the author of the exam, so hopefully I can answer some questions about it. It's 40 questions, multiple choice, mostly built around code blocks, showing best practices, understanding how RDDs work, understanding how to minimize the overhead of shuffles, understand problems with partitioning, serialization, etc. And yeah, I've got a little bit more about that. Also, out in the community, there's great resources off of spark.apache.org. And in particular, there's a set of email lists. There are 2 email lists that are the primary point of going and getting help. I wish I could get help for the Wi-Fi, actually. There we go. So there are 2 email lists. There's one, user@spark.apache.org, and the other is dev@spark.apache.org. And the committers for Spark are very active on there daily. And so what we say is that this is the best foot forward. If you have technical questions about Spark, definitely post something on the email list. You'll have responses right away. But more importantly, you'll get a breadth of responses from developers worldwide. So that we usually try to redirect people here as the best resource. And of course, there's archives for this too, if you want to search through and see what may have been answered before. There's an event listing worldwide. So we're trying to track all the different talks. And there'll be actually some others talks here tonight. But we're tracking this across the world. And we've been keeping track of this since last October. We have some nice, pretty interesting summary stats too, seeing what kind of topics and what kind of companies are really involved in the community. There's also the YouTube channel for Apache Spark, where we've been archiving meetup talks, and a lot of great information there. For instance, here's one from Jeremy Freeman, who I saw hanging around the doorway just a moment ago, talking about Thunder and Lightning, the visualization packages. Anyway, more there. We also have a resource page under databricks.com, Spark Training Resources. And there's a number of different things there. There are some reference apps that are on GitHub, as well as some books and videos coming out now. Also a knowledge base. We're trying to collect together a lot of Q&A about Spark. And coming up, Anthony Joseph is on training team. He's a professor at Berkeley, and also putting together a MOOC. It's Intro to Big Data with Apache Spark. This will be starting up next month. And the last estimates I'd heard, we had going toward 40,000 people signed up for it. So it'll be a very large MOOC, and should be pretty popular. And then not long after that, Amit Talwalkar is going to be doing scalable machine learning. And I think the last I heard from Amit, he had upwards of like 20,000 people signed up. So I'm sure more will sign up closer to it. But a couple of free resources here as far as MOOCs if you want to get a lot more background on Spark. And a few conferences coming up. Definitely at Strata, we'll be having Spark Camp. And we'll be having Spark Summit West in San Francisco in June. Should be about a couple thousand people there. Should be a pretty good conference. I'll leave with a few different books here. Definitely Learning Spark has been out now for a bit. And Chris is the author of Spark in Action, Alpha Manning, and Holden, and also Krishna, who's teaching, Krishna Sankar is teaching the data science course up top. They've been working on fast data processing with Spark off of Pact. I think that's the last slide. Yes. And last but not least, we've got a feedback form. We'd love to hear feedback about the workshop. So if you wouldn't mind taking a few moments and filling out the form, it's much appreciated. We'd like to make this better. And we'd love to hear feedback, especially about how well Databricks Cloud does or doesn't work. If there's any feedback about UX or things you'd like to see changed or added, this is a great way to get direct feedback there. And we have a monthly newsletter that we're putting out about the community. Got to sign up for it. Having said that, thank you very much. We're at 4:30. Thanks for being around here today. And I'm going to hang around for the next hour and a half or so, and we'll get into some more demos and more Q&A. Thank you.